What is machine learning? In this video, we will try to define what it is and also try to give you a sense of when you want to use machine learning. Even among machine learning practitioners, there isn't a well-accepted definition of what is and what isn't machine learning. But let me show you a couple of examples of the ways that people have tried to define it. Here's the definition of what is machine learning that is due to Arthur Samuel. He defined machine learning as the field of study that gives computers the ability to learn without being explicitly programmed. Samuel's claim to fame was that back in the 1950s, he wrote a checkers playing program. And the amazing thing about this checkers playing program was that Arthur Samuel himself wasn't a very good checkers player. But what he did was he had the program play tens of thousands of games against itself. And by watching what sorts of board positions tended to lead to wins and what sort of board positions tended to lead to losses, the checkers playing program learned over time what are good board positions and what are bad board positions, and eventually learned to play checkers better than Arthur Samuel himself was able to. This was a remarkable result. Arthur Samuel himself turned out not to be a very good checkers player, but because a computer has the patience to play tens of thousands of games against itself, no human has the patience to play that many games. By doing this, the computer was able to get so much checkers playing experience that it eventually became a better checkers player than Arthur Samuel himself. This is a somewhat informal definition and an older one. Here's a slightly more recent definition by Tom Mitchell, who's a friend out in Carnegie Mellon. So Tom defines machine learning by saying that a well-posed learning problem is defined as follows. He says, a computer program is said to learn from experience E with respect to some task T and some performance measure P, if its performance on T as measured by P improves with experience E. I actually think he came up with this definition just to make it rhyme. For the checkers playing examples, the experience E would be the experience of having the program play tens of thousands of games against itself. The task T would be the task of playing checkers, and the performance measure P would be the probability that it wins the next game of checkers against some new opponent. Throughout these videos, besides me trying to teach you stuff, I'll occasionally ask you a question to make sure you understand the content. Here's one. On top is a definition of machine learning by Tom Mitchell. Let's say your email program watches which emails you do or do not flag as spam. So in an email client like this, you might click this spam button to report some email as spam, but not other emails. And based on which emails you mark as spam, say your email program learns better how to filter spam email. What is the task T in this setting? In a few seconds, the video will pause, and when it does so, you can use your mouse to select one of these four radio buttons to let me know which of these four you think is the right answer to this question. So hopefully you got that this is the right answer. Classifying emails is a task T. In fact, this definition defines a task T, a performance measure P, and this experience E. And so watching you label emails as spam or not spam, this would be the experience E, and the fraction of emails correctly classified, that might be our performance measure P. And so our task performance on the task, our system's performance on the task T on the performance measure P will improve after the experience E. In this class, I hope to teach you about various different types of learning algorithms. There are several different types of learning algorithms. The main two types are what we call supervised learning and unsupervised learning. I'll define what these terms mean more in the next couple videos, but it turns out that in supervised learning, the idea is we're going to teach the computer how to do something, whereas in unsupervised learning, we're going to let it learn by itself. Don't worry if these two terms don't make sense yet. In the next two videos, I'm going to say exactly what these two types of learning are. You might also hear other buzz terms such as reinforcement learning and recommender systems. These are other types of machine learning algorithms that we'll talk about later, but the two most used types of learning algorithms are probably supervised learning and unsupervised learning, and I'll define them in the next two videos, and we'll spend most of this class talking about these two types of learning algorithms. It turns out one of the other things we'll spend a lot of time on in this class is practical advice. for applying learning algorithms. This is something that I feel pretty strongly about, and it's actually something that I don't know if any other university teaches. Teaching about learning algorithms is like giving a set of tools, and equally important or more important than giving you the tools is to teach you how to apply these tools. I like to make an analogy to learning to become a carpenter. Imagine that someone is teaching you how to be a carpenter, and they say, here's a hammer, here's a screwdriver, here's a saw, good luck. Well, that's no good, right? You have all these tools, but the more important thing is to learn how to use these tools properly. There's a huge difference between people that know how to use these machine learning algorithms versus people that don't know how to use these tools well. Here in Silicon Valley, when I live, when I go visit different companies, even at the top Silicon Valley companies, very often I see people trying to apply machine learning algorithms to some problem, and sometimes they'll have been going at it for 6 months. But sometimes when I look at what they're doing, I say, you know, I could have told them, like, gee, I could have told you 6 months ago that you should be taking your learning algorithm and applying it in like this slightly modified way, and your chance of success would have been much higher. So what we're going to do in this class is actually spend a lot of time talking about how, if you're actually trying to develop a machine learning system, how to make those best practices types decisions about the way in which you build your system, so that when you apply a learning algorithm, you're less likely to end up one of those people who end up pursuing some path for 6 months that, you know, someone else could have figured out just wasn't going to work at all, and it's just a waste of time for 6 months. So I'm actually going to spend a lot of time teaching you those sorts of best practices in machine learning and AI, and how to get this stuff to work, and how we do it, or how the best people do it in Silicon Valley and around the world. I hope to make you one of the best people at knowing how to design and build serious machine learning and AI systems. So that's machine learning, and these are the main topics I hope to teach. In the next video, I'm going to define what is supervised learning, and after that, what is unsupervised learning, and also start to talk about when you will use each of them. In this video, I'm going to define what is probably the most common type of machine learning problem, which is supervised learning. I'll define supervised learning more formally later, but it's probably best to explain or start with an example of what it is, and we'll do the formal definition later. Let's say you want to predict housing prices. A while back, a student collected data sets from the city of Portland, Oregon, and let's say you plot the data set and it looks like this. Here on the horizontal axis, the size of different houses in square feet, and on the vertical axis, the prices of different houses in thousands of dollars. So, given this data, let's say you have a friend who owns a house that is, say, 750 square feet, and they're hoping to sell the house, and they want to know how much they can get for the house. So, how can a learning algorithm help you? One thing a learning algorithm might be able to do is put a straight line through the data, or sort of fit a straight line to the data, and based on that, it looks like maybe their house can be sold for maybe about $150,000. But maybe this isn't the only learning algorithm you can use, and there might be a better one. For example, instead of fitting a straight line to the data, we might decide that it's better to fit a quadratic function or a second-order polynomial to this data. And if you do that and make a prediction here, then it looks like, well, maybe they can sell the house for closer to $200,000. One of the things we'll talk about later is how to choose and how to decide, do you want to fit a straight line to the data, or do you want to fit a quadratic function to the data? And there's no fair picking whichever one gives your friend the better house to sell. But each of these would be a fine example of a learning algorithm. So this is an example of a supervised learning algorithm. And the term supervised learning refers to the fact that we gave the algorithm a data set in which the quote right answers were given. That is, we gave it a data set of houses in which for every example in this data set, we told it what is the right price, or what was the actual price that that house sold for. And the task of the algorithm was to just produce more of these right answers, such as for this new house, that your friend may be trying to sell. To define a bit more terminology, this is also called a regression problem. And by regression problem, I mean we're trying to predict a continuous valued output, namely the price. So technically, I guess prices can be rounded off to the nearest cent. So maybe prices are actually discrete value, but usually we think of the price of a house as a real number, or as a scalar value, as a continuous value number. And the term regression refers to the fact that we're trying to predict this sort of a continuous values attribute. Here's another supervised learning examples. Some friends and I were actually working on this earlier. Let's say you want to look at medical records and try to predict if a breast cancer is malignant or benign. If someone discovers a breast tumor, a lump in their breast, a malignant tumor is a tumor that is harmful and dangerous, and a benign tumor is a tumor that's harmless. So obviously people care a lot about this. Let's say you collect a data set, and suppose in your data set you have on your horizontal axis the size of the tumor, and on the vertical axis I'm going to plot 1 or 0, yes or no, whether or not these are examples of tumors we've seen before are malignant, which is 1, or 0, or not malignant, or benign. So let's say your data set looks like this, where we saw a tumor of this size that turned out to be benign, one of this size, one of this size, and so on. And sadly, we also saw a few malignant tumors. So one of that size, one of that size, one of that size, so on. So in this example, I have 5 examples of benign tumors shown down here, and 5 examples of malignant tumors shown with a vertical axis value of 1. And let's say you have a friend who tragically has a breast tumor, and let's say her breast tumor size is maybe somewhere around this value. The machine learning question is, can you estimate what is the probability, what is the chance that the tumor is malignant versus benign? To introduce a bit more terminology, this is an example of a classification problem. The term classification refers to the fact that here we're trying to predict a discrete valued output, 0 or 1, malignant or benign. And it turns out that in classification problems, sometimes you can have more than 2 possible values for the output. As a concrete example, maybe there are 3 types of breast cancers, and so you may try to predict a discrete value output 0, 1, 2, or 3, where 0 may mean benign tumor, so no cancer, and 1 may mean type 1 cancer, if you have 3 types of cancer, whatever type 1 means, and 2 may mean the second type of cancer, and 3 may mean the third type of cancer. But this would also be a classification problem because there's sort of a discrete value set of outputs corresponding to no cancer, or cancer type 1, or cancer type 2, or cancer type 3. In classification problems, there is another way to plot this data. Let me show you what I mean. I'm going to use a slightly different set of symbols to plot this data. So if tumor size is going to be the attribute that I'm going to use to predict malignancy or benignness, I can also draw my data like this. I'm going to use different symbols to denote my benign and malignant, or my negative and positive examples. So instead of drawing crosses, I'm now going to draw O's for the benign tumors, like so. And I'm going to keep using X's to denote my malignant tumors. Okay, I hope this figure makes sense. All I did was I took my data set on top, and I just mapped it down to this real line, like so, and started to use different symbols, circles and crosses, to denote malignant versus benign examples. Now, in this example, we use only one feature or one attribute, namely the tumor size, in order to predict whether tumor is malignant or benign. In other machine learning problems, we may have more than one feature or more than one attribute. Here's an example. Let's say that instead of just knowing the tumor size, we know both the age of the patient and the tumor size. In that case, maybe your data set would look like this, where I may have a set of patients with those ages and that tumor size. It may look like this, and a different set of patients that look a little different, whose tumors turn out to be malignant, as denoted by the crosses. So let's say you have a friend who tragically has a tumor, and maybe their tumor size and age falls around there. So given a data set like this, what the learning algorithm may do is fit a straight line to the data to try to separate out the malignant tumors from the benign ones. And so the learning algorithm may decide to fill a straight line like that to separate out the two classes of tumors. And, with this, hopefully we can decide that your friend's tumor is more likely, so if it was over there, that hopefully the learning algorithm will say that your friend's tumor falls on this benign side and is therefore more likely to be benign than malignant. In this example, we had two features, namely the age of the patient and the size of the tumor. In other machine learning problems, we will often have more features. And my friends that work on this problem, they actually use other features like these, which is clump thickness of the breast tumor, uniformity of cell size of the tumor, uniformity of cell shape of the tumor, and so on, and other features as well. And it turns out one of the most interesting learning algorithms that we'll see in this class is a learning algorithm that can deal with not just 2 or 3 or 5 features, but an infinite number of features. On this slide, I've listed a total of 5 different features, right? 2 on the axis and 3 more up here. But it turns out that for some learning problems, what you really want is not to use like 3 or 5 features, but instead you want to use an infinite number of features, an infinite number of attributes, so that your learning algorithm has lots of attributes or features or cues with which to make those predictions. So how do you deal with an infinite number of features? I mean, sort of, how do you even store an infinite number of things on a computer? I mean, your computer's going to run out of memory. Well, it turns out that when we talk about an algorithm called the support vector machine, there'll be a neat mathematical trick that will allow a computer to deal with an infinite number of features. Imagine that I didn't just write down, 2 features here and 3 features on the right, but imagine that I wrote down an infinitely long list. I just kept writing more and more and more features, like an infinitely long list of features. Turns out we'll be able to come up with an algorithm that can deal with that. So just to recap, in this class we'll talk about supervised learning, and the idea is that in supervised learning, in every example in our data set, we are told what is the, quote, correct answer that we would have quite liked the algorithm to have predicted on that example, such as the price of the house or whether a tumor is malignant or benign. We also talked about the regression problem, and by regression, that means that our goal is to predict a continuous valued output, and we talked about the classification problem, where the goal is to predict a discrete valued output. Here's a quick wrap-up question. Suppose you're running a company and you want to develop learning algorithms to address each of 2 problems. In the first problem, you have a large inventory of identical items. So imagine that you have thousands of copies of some identical item to sell, and you want to predict how many of these items you sell over the next 3 months. In the second problem, in problem 2, you have lots of users and you want to write software to examine each individual of your customers' accounts, so each one of your customers' accounts, and for each account, decide whether or not the account has been hacked or compromised. So for each of these problems, should they be treated as a classification problem or as a regression problem? When the video pauses, please use your mouse to select whichever of these 4 options on the left you think is the correct answer. So hopefully you got that this is the answer. For problem 1, I would treat this as a regression problem, because if I have thousands of items, well, I would probably just treat this as a real value, as a continuous value, and treat therefore the number of items I sell as a continuous value. And for the second problem, I would treat that as a classification problem, because I might say set the value I want to predict to be 0 to denote the account has not been hacked, and set the value 1 to denote an account that has been hacked into. So just like breast cancers, right? 0 are benign, 1 is malignant. So I might set this to be 0 or 1 depending on whether it's been hacked, and have an algorithm try to predict each one of these 2 discrete values. And because that's a small number of discrete values, I would therefore treat it as a classification problem. So that's it for supervised learning. And in the next video, I'll talk about unsupervised learning, which is the other major category of learning algorithm. In this video, we'll talk about the second major type of machine learning problem called unsupervised learning. In the last video, we talked about supervised learning. Back then, we got data sets that look like this, where each example was labeled either as a positive or a negative example, whether it was a benign or a malignant tumor. So for each example in supervised learning, we were told explicitly what is the so-called right answer, whether it's benign or malignant. In unsupervised learning, we're given data that looks different. We're given data that looks like this, that doesn't have any labels, or that sort of all has the same label, or really no labels. So we're given a data set, and we're not told what to do with it, and we're not told what each data point is. Instead, we're just told, here is a data set. Can you find some structure in the data? Given this data set, an unsupervised learning algorithm might decide that the data lives in two different clusters. And so there's one cluster, and there's a different cluster. And the unsupervised learning algorithm may break this data into these two separate clusters. So this is called a clustering algorithm, and this turns out to be used in many places. One example where clustering is used is in Google News. And if you've not seen this before, you can actually go to this URL, news.google.com, to take a look. What Google News does is every day it goes and looks at tens of thousands or hundreds of thousands of news stories on the web, and it groups them into cohesive news stories. For example, let's look here. The URLs here link to different news stories about the BP oil well story. So let's say I click on one of these URLs. I'm going to click on one of these URLs. What I'll get to is a web page like this. Here's a Wall Street Journal article about the BP oil well spill story. So BP kills Macondo, which is the name of the spill. And if you click on a different URL from that group, then you might get a different story. Here's a CNN story about, again, the BP oil spill. And if you click on yet a third link, then you might get, a different story. Here's the UK Guardian story about the BP oil spill. So what Google News has done is looked at tens of thousands of news stories and automatically clustered them together so that news stories that are all about the same topic get to display together. It turns out that clustering algorithms and unsupervised learning algorithms are used in many other problems as well. Here's one on understanding genomics. Here's an example of DNA microarray data. The idea is you have a group of different individuals, and for each of them, you measure how much they do or do not have a certain gene. Technically, you measure how much certain genes are expressed. So these colors, red, green, gray, and so on, they show the degree to which different individuals do or do not have a specific gene. And what you can do is then run a clustering algorithm to group individuals into different categories or into different types of people. So this is unsupervised learning because we're not telling the algorithm in advance that, these are type 1 people, those are type 2 persons, those are type 3 persons, and so on. And instead, what we're saying is, here's a bunch of data. I don't know what's in this data. I don't know who's in what type. I don't even know what the different types of people are. But can you automatically find structure in the data for me? Can you automatically cluster the individuals into these types that I don't know in advance? Because we're not giving the algorithm the right answer for the examples in my data set, this is unsupervised learning. Unsupervised learning or clustering is used for a bunch of other applications. It's used to organize large computer clusters. I had some friends looking at large data centers, that is, large computer clusters, and trying to figure out which machines tend to work together. And if you can put those machines together, you can make your data center work more efficiently. Here's the second application, social network analysis. So given knowledge about which friends you email the most, or given your Facebook friends or your Google Plus circles, can we automatically identify which are cohesive groups of friends, or so which are groups of people that all know each other? Market segmentation. Many companies have huge databases of customer information. So can you look at this customer data set and automatically discover market segments and automatically group your customers into different market segments so that you can automatically and more efficiently sell or market to your different market segments together? Again, this is unsupervised learning because we have all this customer data, but we don't know in advance what are the market segments, and for the customers in our data set, we don't know in advance who is in market segment 1, who's in market segment 2, and so on. But we have to let the algorithm discover all this just from the data. Finally, it turns out that unsupervised learning is also used for, surprisingly, astronomical data analysis, and these clustering algorithms give surprisingly interesting or useful theories of how galaxies are formed. All these are examples of clustering, which is just one type of unsupervised learning. Let me tell you about another one. I'm going to tell you about the cocktail party problem. So you've been to cocktail parties before, right? Where you can imagine there's a party, room full of people, all sitting around, all talking at the same time. And there are all these overlapping voices because everyone's talking at the same time. And it's almost hard to hear the person in front of you. So maybe you have a cocktail party with two people talking at the same time, and a somewhat small cocktail party. And we're going to put two microphones in the room. So there are microphones. And because these microphones are at two different distances from the speakers, each microphone records a different combination of these two speakers' voices. Maybe speaker 1 is a little louder in microphone 1, and maybe speaker 2 is a little bit louder in microphone 2 because the two microphones are at different positions relative to the two speakers. But each microphone records an overlapping combination of both speakers' voices. So here's an actual recording of two speakers recorded by a researcher. Let me play for you what the first microphone sounds like.
1, 2, 3, 4, 5, 6, 7, 8, 9, 10.
All right, maybe not the most interesting cocktail party is two people counting from 1 to 10 in two languages, but there you go. What you just heard was the first microphone recording. Here's the second recording.
1, 2, 3, 4, 5, 6, 7, 8, 9, 10.
So what you can do is take these two microphone recordings and give them to an unsupervised learning algorithm called the cocktail party algorithm, and tell the algorithm, find structure in this data for me. And what the algorithm will do is listen to these audio recordings and say, it sounds like the two audio recordings that are being added together or that are being summed together to produce these recordings that we had. Moreover, what the cocktail party algorithm will do is separate out these two audio sources that were being added or being summed together to form our recordings. And in fact, here's the first output of the cocktail party algorithm.
1, 2, 3, 4, 5, 6, 7, 8, 9, 10.
So it separated out the English voice in one of the recordings, and here's the second output.
1, 2, 3, 4, 5, 6, 7, 8, 9, 10.
Not too bad, huh? To give you one more example, here's another recording of another similar situation. Here's the first microphone.
1, 2, 3, 4, 5, 6, 7, 8, 9, 10.
Okay, so the poor guy's gone home from the cocktail party and he's now sitting in a room by himself talking to his radio. Here's the second microphone recording.
1, 2, 3, 4, 5, 6, 7, 8, 9, 10.
When you give these two microphone recordings to the same algorithm, what it does is again say, it sounds like there are two audio sources, and moreover, the algorithm says, here is the first of the audio sources I found.
1, 2, 3, 4, 5, 6, 7, 8, 9, 10.
So that wasn't perfect. It got the voice, but it also got a little bit of the music in there. Then here's the second output of the algorithm. Not too bad. In that second output, it managed to get rid of the voice entirely and just, cleaned up the music and got rid of the counting from 1 to 10. So you might look at an unsupervised learning algorithm like this and ask, how complicated is it to implement this, right? It seems like in order to build this application, it seems like to do this audio processing, you need to write a ton of code or maybe link into a bunch of C++ or Java libraries to process audio. It seems like a really complicated program to do this audio, separating out audio and so on. It turns out the algorithm to do what you just heard, that can be done with one line of code, shown right here. It did take researchers a long time to come up with this line of code, so I'm not saying this was an easy problem, but it turns out that when you use the right programming environment, many learning algorithms can be really short programs. So this is also why in this class we're going to use the Octave programming environment. Octave is free open source software, and using a tool like Octave or MATLAB, many learning algorithms become just a few lines of code to implement. Later in this class, I'll also teach you a little bit about how to use Octave, and you'll be implementing some of these algorithms in Octave, or if you have MATLAB, you can use that too. Turns out that in Silicon Valley, for a lot of machine learning algorithms, what we do is first prototype our software in Octave, because software like Octave makes it incredibly fast to implement these learning algorithms. Here, each of these functions, like for example, the SVD function, that stands for singular value decomposition, but that turns out to be a linear algebra routine that is just built into Octave. If you were trying to do this in C++ or Java, this would be many, many lines of code linking complex C++ or Java libraries. So you can implement this stuff in C++ or Java or Python, but it's just much more complicated to do so in those languages. What I've seen after having taught machine learning for about a decade now is that you learn much faster if you use Octave as your programming environment. And if you use Octave as your learning tool and as your prototyping tool, it will let you learn and prototype learning algorithms much more quickly. And in fact, what many people will do in the large Silicon Valley companies is in fact use an algorithm like Octave to first prototype the learning algorithm, and only after you've gotten it to work, then you migrate it to C++ or Java or whatever. It turns out that by doing things this way, you can often get your algorithm to work much faster than if you were starting out in C++. So I know that as an instructor, I get to say, trust me on this one, only a finite number of times. But for those of you who have never used these sort of Octave-type programming environments before, I'm going to ask you to trust me on this one and say that you will, I think your time or your developer time is one of the most valuable resources. And having seen lots of people do this, I think you as a machine learning researcher or machine learning developer will be much more productive if you learn this stuff and prototype this stuff in Octave than in some other language. Finally, to wrap up this video, I have one quick review question for you. We talked about unsupervised learning, which is a learning setting where you give the algorithm a ton of data and just ask it to find structure in the data for us. Of the following 4 examples, which of these 4 do you think would be an unsupervised learning algorithm as opposed to a supervised learning problem? For each of the 4 checkboxes on the left, check the ones for which you think unsupervised learning algorithm would be appropriate, and then click the button on the lower right to check your answer. So when the video pauses, please answer the question on the slide. So hopefully you remembered the spam filter problem. If you have labeled data, of spam and non-spam email, we treat this as a supervised learning problem. The news story example, that's exactly the Google News example that we saw in this video. We saw how you can use a clustering algorithm to cluster news articles together. So that's unsupervised learning. The market segmentation example I talked about a little bit earlier. You can do that as an unsupervised learning problem because I'm just going to give my algorithm data and ask it to discover market segments automatically. And the final example, diabetes, well, that's actually just like our breast cancer example from the last video, only instead of, good and bad cancer tumors or benign and malignant tumors, we instead have diabetes or not. And so we will use that as we will solve that as a supervised learning problem, just like we did for the breast tumor data. So that's it for unsupervised learning. And in the next video, we'll delve more into specific learning algorithms and start to talk about just how these algorithms work and how you can go about implementing them. Our first learning algorithm will be linear regression. In this video, you see what the model looks like, and more importantly, you also see what the overall process of supervised learning looks like. Let's use our motivating example of predicting housing prices. We're going to use a data set of housing prices from the city of Portland, Oregon, and here I'm going to plot my data set of a number of houses that were of different sizes that were sold for a range of different prices. Let's say that given this data set, you have a friend that's trying to sell a house, and let's say your friend's house is of size 1,250 square feet, and you want to tell them how much they might be able to sell the house for. Well, one thing you could do is fit a model, maybe fit a straight line to this data. That might something like that. And based on that, maybe you could tell your friend that looks like they can maybe sell the house for around $220,000. So this is an example of a supervised learning algorithm, and it's supervised learning because we're given the quote right answer for each of our examples. Namely, we're told what was the actual house, what was the actual price that each of the houses in our data set was sold for. And moreover, this is an example of a regression problem where the term regression refers to the fact that we're predicting a real valued output, namely the price. And just to remind you, the other most common type of supervised learning problem is called a classification problem, where we predict discrete valued outputs, such as if we are looking at cancer tumors and trying to decide if a tumor is malignant or benign. So there's a 0-1 valued discrete output. More formally, in supervised learning, we have a data set, and this data set is called a training set. So for a housing price example, we have a training set of different housing prices, and our job is to learn from this data how to predict the prices of the houses. Let's define some notation that we're using throughout this course. I'm going to define quite a lot of symbols. It's okay if you don't remember all the symbols right now, but as the course progresses, it'll be useful to have a convenient notation. So I'm going to use lowercase m throughout this course to denote the number of training examples. So in this data set, if I have, let's say 47 rows in this table, then I have 47 training examples and m equals 47. I'm going to use lowercase x to denote the input variables, often also called the features. So that'll be x's here would be our input features. And I'm going to use y to denote my output variables, or the target variable which I'm trying to predict. And so that's this second column here. A little bit more notation. I'm going to use x comma y to denote a single training example. So a single row in this table corresponds to a single training example. And to refer to a specific training example, I'm going to use this notation xi comma yi, and going to use this to refer to the ith training example. Right? So this superscript I over here, this is not exponentiation, right? This xiyi, the superscript I in parentheses, that's just an index into my training set, and it refers to the ith row in this table. Okay, so this is not x to the power of I, y to the power of I. Instead, xiyi just refers to the ith row of this table. So, for example, x1, refers to the input value from the first training example. So that's 2104, right? Because that's x in the first row. x2 would be equal to 1416, right? That's the second x, and y1 will be equal to 460, because that's the y value for my first training example. That's what that 1 refers to. So, as I mentioned, occasionally I'll ask you a question to let you check your own understanding. In a few seconds in this video, a multiple choice question will pop up in the video. When it does, please use your mouse to select what you think is the right answer. We've defined what a training set is, and so here's how a supervised learning algorithm works. We started with a training set, like our training set of housing prices, and we feed that to our learning algorithm. It's the job of a learning algorithm to then output a function, which by convention is usually denoted lowercase h, and h stands for hypothesis. And what the job of the hypothesis is a function that takes as input the size of a house, like maybe the size of a new house that your friend is trying to sell, so it takes in a new value of x, and it tries to output the estimated value of y for their corresponding house. So h is a function that maps from x's to y's. People often ask me, why is this function called a hypothesis? Some of you may know the meaning of the term hypothesis from the dictionary or from science or whatever. It turns out that in machine learning, this is a name that was used in the early days of machine learning, and it kind of stuck. It's maybe not a great name for this sort of function for mapping from sizes of houses to the predictions. But, I think the term hypothesis maybe isn't the best possible name for this, but it's the standard terminology that people use in machine learning now. So don't worry too much about why people call it that. When designing a learning algorithm, the next thing we need to decide is how do we represent this hypothesis H? For this and the next few videos, I'm going to choose our initial choice for representing the hypothesis will be the following. I'm going to represent H as follows. I'm going to write to this H subscript theta of X equals theta 0 plus theta 1 of X. And as a shorthand, sometimes instead of writing, H subscript theta of X, sometimes as a shorthand, I'll just write this as H of X. But more often, I'll write it as a subscript theta over there. And plotting this in pictures, all this means is that we are going to, predict that Y is a linear function of X. Right? So that's a data set. And what this function is doing is it's predicting that Y is some straight line function of X. That's H of X equals theta 0 plus theta 1 X. Okay? And why a linear function? Well, sometimes we'll want to fit more complicated, perhaps nonlinear functions as well. But since this linear case is the simpler building block, we'll start with this example first of fitting linear functions, and we'll build on this to eventually have more complex models and more complex learning algorithms. Let me also give this particular model a name. This model is called linear regression, or this particular example is actually linear regression with one variable, with the variable being X. Right? So predicting housing prices is a function of the one variable X. And another name for this model is univariate linear regression. And univariate is just, a fancy way of saying one variable. So that's linear regression. In the next video, we'll start to talk about just how to go about implementing this model. In this video, we'll define something called the cost function. This will let us figure out how to fit the best possible straight line to our data. In linear regression, we have a training set like that shown here. Remember our notation, M was the number of training examples, so maybe M equals 47. And the form of our hypothesis, which we use to make predictions, is this linear function. To introduce a little bit more terminology, these theta 0 and theta 1, right, these theta i's are what are called the parameters of the model. And what we're going to do in this video is talk about how to go about choosing these two parameter values, theta 0 and theta 1. With different choices of the parameters theta 0 and theta 1, we get different hypotheses, different hypothesis functions. I know some of you will probably be already familiar with what I'm going to do on this slide, but just to review, here are a few examples. If theta 0 is 1.5 and theta 1 is 0, then the hypothesis function will look like this. Right? Because your hypothesis function will be h of x equals 1.5 plus 0 times x, which is this constant value function that's just flat at 1.5. If theta 0 equals 0, theta 1 equals 0.5, then the hypothesis will look like this. And it should pass through this point 2, 1, since you now have h of x, so really h substrate theta of x, but sometimes I'll just omit theta for brevity. So h of x would be equal to just 0.5 times x, which looks like that. And finally, if theta 0 equals 1 and theta 1 equals 0.5, then we end up with a hypothesis that looks like this. Let's see, it should pass through the 2 point like so, and this is my new h of x, or my new h subscript theta of x. All right, well, you remember I said that this is h subscript theta of x, but as a shorthand, sometimes I'll just write this as h of x. In linear regression, we have a training set, like maybe the one I plotted here. What we want to do is come up with values for the parameters theta 0 and theta 1, so that the straight line we get out of this corresponds to a straight line that somehow fits the data well, like maybe that line out there. So how do we come up with values theta 0, theta 1 that corresponds to a good fit to the data? the idea is we're going to choose our parameters theta 0, theta 1, so that h of x, meaning the value we predict on input x, that this is at least close to the values y for the examples in our training set, for our training examples. So in our training set, we're given a number of examples where we know x, the size of the house, and we know the actual price it was sold for. So let's try to choose values for the parameters so that at least in the training set, given the x's in the training set, we make reasonably accurate predictions for the y values. Let's formalize this. So in linear regression, what we're going to do is I'm going to want to solve a minimization problem. So I'm going to write minimize over theta 0, theta 1. And I want this to be small, right? I want the difference between h of x and y to be small. And one thing I might do is try to minimize the squared difference between the output of my hypothesis and the actual price of a house. Okay? So let's fill in some details. You remember that I was using the notation xi comma yi to represent the ith training example. So what I want really is to sum over my training set, sum from I equals 1 to m, of the squared difference between, this is the prediction of my hypothesis when it is input the size of house number I, right, minus the actual price that house number I was sold for. And I want to minimize the sum over my training set, sum from I equals 1 through m, of the difference, of the squared error, squared difference between the predicted price of the house and the price that it was actually sold for. And just to remind you of your notation, m here was the size of my training set, right? So the m there is my number of training examples, right? That hash sign is the abbreviation for number of training examples. Okay, and to make some of our later math a little bit easier, I'm going to actually look at 1 over m times that. So we're going to try to minimize my average error, which is going to minimize 1 over 2m. Putting the 2, the constant 1/2 in front, it just makes some of the math a little bit easier. So minimizing 1/2 of something, right, should give you the same values for the parameters theta 0 and theta 1 as minimizing that function. And just make sure this equation is clear, right? This expression in here, h subscript theta of x, this is our usual, right? That's equal to this plus theta 1 xi. And this notation, minimize over theta 0 and theta 1, this means find me the values of theta 0 and theta 1 that causes this expression to be minimized. And this expression depends on theta 0 and theta 1. Okay? So just to recap, we're posing this problem as, find me the values of theta 0 and theta 1 so that the average, or really 1 over 2m times the sum of squared errors between my predictions on the training set minus the actual values of the houses on the training set is minimized. So this is going to be my overall objective function for linear regression. And just to rewrite this out a little bit more cleanly, what I'm going to do is, by convention, we usually define a cost function, which is going to be exactly this, that formula that I have up here. And what I want to do is minimize over theta 0 and theta 1 my function j of theta 0 comma theta 1. Where just write this out. This is my cost function. So this cost function is also called the squared error function, or sometimes called the squared error cost function. And it turns out that why do we take the squares of the errors? It turns out that the squared error cost function is a reasonable choice and will work well for most problems, for most regression problems. There are other cost functions that will work pretty well, but the squared error cost function is probably the most commonly used one for regression problems. Later in this class we'll talk about alternative cost functions as well, but this choice that we just had should be a pretty reasonable thing to try for most linear regression problems. Okay, so that's the cost function. So far, we've just seen a mathematical definition of this cost function, and in case this function j of theta 0, theta 1, in case this function seems a little bit abstract, and you still don't have a good sense of what it's doing, in the next video, in the next couple of videos, I'm actually going to go a little bit deeper into what the cost function j is doing and try to give you better intuition about what it's computing and why we want to use it. In the previous video, we gave a mathematical definition of the cost function. In this video, let's look at some examples to get better intuition about what the cost function is doing and why we want to use it. To recap, here's what we had last time. We want to fit a straight line to our data, so we had this form as a hypothesis with these parameters theta 0 and theta 1, and with different choices of the parameters, we end up with different straight line fits to the data, h of x like so, and there's a cost function, and that was our optimization objective. For this video, in order to better visualize the cost function j, I'm going to work with a simplified hypothesis function, like that shown on the right. So I'm going to use a simplified hypothesis, which is just theta 1 times x. You can, if you want, think of this as setting the parameter theta 0 equal to 0. So I have only one parameter, theta 1, and my cost function is similar to before, except that now h of x, that is now equal to just theta 1 times x. And I have only one parameter, theta 1, and so my optimization objective is to minimize j of theta 1. In pictures, what this means is that if theta 0 equals 0, that corresponds to choosing only hypothesis functions that pass through the origin, that pass through the point 0, 0 over there. Using the simplified definition of a hypothesis and cost function, let's try to understand the cost function concept better. It turns out there are two key functions we want to understand. The first is the hypothesis function, and the second is the cost function. So notice that the hypothesis, right, h of x, for a fixed value of theta 1, this is a function of x. So the hypothesis is a function of what is the size of the house x. In contrast, the cost function, j, that's a function of the parameter theta 1, which controls the slope of your straight line. Let's plot these functions and try to understand them both better. Let's start with the hypothesis. On the left, let's say here's my training set with 3 points at 1, 1, 2, 2, and 3, 3. Let's pick a value of theta 1. So I'm going to set theta 1 equals 1, and if that's my choice for theta 1, then my hypothesis is going to look like this straight line over here. Okay? And I want to point out, when I'm plotting my hypothesis function, my x-axis, my horizontal axis is labeled x, is labeled, size of the house over here. Now, I've temporarily set theta 1 equals 1. What I want to do is figure out, what is j of theta 1 when theta 1 equals 1. So let's go ahead and compute what the cost function is for, the value 1. Well, as usual, my cost function is defined as follows, right? Sum over my training set of this usual squared error term. And this is therefore equal to this of theta 1 xi minus yi. And if you simplify, this turns out to be that 0 squared plus 0 squared plus 0 squared, which is, of course, just equal to 0. Now, inside the cost function, it turns out each of these terms here is equal to 0 because, for the specific training sets I have, where my 3 training examples are at 1, 1, 2, 2, 3, 3, if theta 1 is equal to 1, then, h of x, right, h of xi is equal to yi exactly. Let me write this better. Right? And so h of x minus y, each of these terms is equal to 0, which is why I find that j of 1 is equal to 0. So we now know that j of 1 is equal to 0. Let's plot that. What I'm going to do on the right is plot my cost function j. And notice, because my cost function is a function of my parameter theta 1, when I plot my cost function, the horizontal axis is now labeled with theta 1. So I have j of 1 is equal to 0. So let's go ahead and plot that. Going to end up with an x over there. Now let's look at some other examples. Theta 1 can take on a range of different values, right? So theta 1 can take on negative values, 0, or positive values. So what if theta 1 is equal to 0.5? What happens then? Let's go ahead and plot that. I'm now going to set theta 1 equals 0.5, and in that case, my hypothesis now looks like this. There's a line with slope equals to 0.5, and let's compute j of 0.5. So that is going to be 1 over 2m of my usual cost function. It turns out that the cost function is going to be the sum of squared values of the height of this line plus the sum of squared of the height of that line plus the sum of squared of the height of that line, right? Because this vertical distance, that's the difference between, y, I, and the predicted value h of xi, right? So the first example, this is going to be 0.5 minus 1 squared, because my hypothesis predicted 0.5, whereas the actual value was 1. For my second example, I get 1 minus 2 squared, because my hypothesis predicted 1, but the actual housing price was 2. And then finally, plus 1.5 minus 3 squared. And so that's equal to 1 over 2 times 3, because m, my training set size, right, I have 3 training examples. And then that's times, simplifying the thing in parentheses, is 3.5. So that's 3.5 over 6, which is about 0.68. So now we know that j of 0.5 is about 0.68. Let's go and plot that. Oh, excuse me, math error. This is actually 0.58. So I'm going to plot that, which is maybe about over there. Okay? Now, let's do one more. How about if theta 1 is equal to 0? What is j of 0 equal to? It turns out that if theta 1 is equal to 0, then h of x is just equal to, this flat line, right? That just goes horizontally like this. And so measuring the errors, we have that j of 0 is equal to 1 over 2m times 1 squared plus 2 squared plus 3 squared, which is 1/6 times 14, which is about 2.3. So let's go ahead and plot that as well. We end up with a value around 2.3. And of course, we can keep on doing this for other values of theta 1. It turns out that you can have negative values of theta 1 as well. So if theta 1 is negative, then h of x would be equal to, say, minus 0.5 times x, right? If theta 1 is minus 0.5. And so that corresponds to a hypothesis, with a slope of negative 0.5. And you can actually keep on computing these errors. This turns out to be, for 0.5, it turns out to have a really high error. It works out to be something like 5.25. And so on. And for different values of theta 1, you can compute these things, right? And it turns out that you compute a range of values, you get something like that. And by computing a range of values, you can actually slowly trace out what this function, j of theta, looks like. And that's what j of theta is. To recap, for each value of theta 1, right, each value of theta 1 corresponds to a different hypothesis or to a different straight line fit on the left. And for each value of theta 1, we could then derive a different value of j of theta 1. And for example, theta 1 equals 1 corresponded to this straight line fit through the data, whereas theta 1 equals 0.5, this point, shown in magenta, corresponded to maybe that line, and theta 1 equals 0, which I'm going to show in blue, that corresponds to this horizontal line, right? So for each value of theta 1, we wound up with a different value of j of theta 1, and we could then use this to trace out this plot on the right. Now, you remember, the optimization objective for our learning algorithm is we want to choose the value of theta 1 that minimizes j of theta 1, right? This was our objective function for linear regression. Well, looking at this curve, the value that minimizes j of theta 1 is, theta 1 equals to 1. And lo and behold, that is indeed the best possible straight line fit through our data. By setting theta 1 equals 1, and just for this particular training set, we actually end up fitting it perfectly. And that's why minimizing j of theta 1 corresponds to finding a straight line that fits the data well. So, to wrap up, in this video, we looked at some plots to understand the cost function. To do so, we simplified the algorithm so that it had only one parameter theta 1, and we set the parameter theta 0 to equal to 0. In the next video, we'll go back to the original problem formulation and look at some visualizations involving both theta 0 and theta 1, that is, without setting theta 0 to 0. And hopefully that will give you an even better sense of what the cost function j is doing in the original linear regression formulation. In this video, let's delve deeper and get even better intuition about what the cost function is doing. This video assumes that you're familiar with contour plots. If you're not familiar with contour plots or contour figures, some of the illustrations in this video may or may not make sense to you, but it's okay, and if you end up skipping this video or if some of it doesn't quite make sense because you haven't seen contour plots before, that's okay, and you still understand the rest of this course without those parts of this. Here's our problem formulation as usual with the hypothesis, parameters, cost function, and our optimization objective. Unlike before, unlike the last video, I'm going to keep both of my parameters theta 0 and theta 1 as we generate our visualizations for the cost function. So, same as last time, we want to understand the hypothesis, h, and the cost function j. So here's my training set of housing prices. And let's pick some hypothesis, like that one. This is not a particularly good hypothesis, but if I set theta 0 equals 50 and theta 1 equals 0.06, then I end up with this hypothesis down here, and that corresponds to that straight line. Now, given these values of theta 0 and theta 1, we want to plot the corresponding, cost function on the right. What we did last time was, right, when we only had theta 1, we were drawing plots that look like this as a function of theta 1. But now we have two parameters, theta 0 and theta 1, and so the plot gets a little more complicated. It turns out that when we had only one parameter, the plots we drew had this sort of bow-shaped function. Now, when we have two parameters, it turns out the cost function also has a similar sort of bow shape. And in fact, depending on your training set, you might get a cost function that maybe looks something like this. So this is a 3D surface plot where the axes are labeled theta 0 and theta 1. So as you vary theta 0 and theta 1, the two parameters, you get different values of the cost function j of theta 0 comma theta 1. And the height of this surface above a particular point of theta 0, theta 1, right, that's the vertical axis, the height of the surface at the point indicates the value of j of theta 0 comma j of theta 1. And you can see it sort of has this bow-like shape. Let me show you the same plot in 3D. So here's the same figure in 3D with axes theta 0, theta 1, and vertical axis j of theta 0, theta 1. And if I rotate this plot around, you kind of get a sense, I hope, of this sort of bow-shaped surface. That's what the cost function j looks like. Now, for the purpose of illustration, in the rest of this video, I'm not actually going to use these sorts of 3D surfaces to show you the cost function j. Instead, I'm going to use contour plots, or what are also called contour figures. I guess they mean the same thing, to show you these surfaces. So here's an example of a contour figure shown on the right, where the axes are theta 0 and theta 1. And what each of these ovals, what each of these ellipses shows is a set of points that takes on the same value for j of theta 0, theta 1. So concretely, for example, let's take that point and that point and that point. All three of these points that I just drew in magenta, they have the same value for j of theta 0, theta 1. Okay, right? This is a theta 0, theta 1 axis, but those three have the same value for j of theta 0, comma, theta 1. And if you haven't seen contour plots much before, imagine, if you will, a bow-shaped function that's coming out of my screen, so that the minimum, so the bottom of the bow is this point right there, right? This middle, the middle of these concentric ellipses. And imagine a bow shape that sort of grows out of my screen like this, so that each of these ellipses, has the same height above my screen, and the minimum of the bow, right, is right down there. And so the contour figures is a way to maybe a more convenient way to visualize my function j. So let's look at some examples. Over here, I have a particular point, right? And so this is with theta 0 equals maybe about 800, and theta 1 equals maybe a minus 0.15. And so this point, right, this point in red corresponds to one particular pair of values of theta 0, comma, theta 1. And they correspond, in fact, to that hypothesis, right? With theta 0, it's about 800, so this intersects the vertical axis around 800, and this is a slope of about minus 0.15. Now, this line is really not such a good fit to the data, right? This hypothesis, h of x, with these values of theta 0, theta 1, it's really not such a good fit to the data, and so you find that its cost is a value that's out here. That's pretty far from the minimum. Right, so it's pretty far, this is a pretty high cost because this is just not that good a fit to the data. Let's look at some more examples. Now here's a different hypothesis that's, still not a great fit to the data, but maybe slightly better. So here, right, that's my point. Those are my parameters, theta 0, theta 1. And so my theta 0 value, right, that's about 360. And my value for theta 1 is equal to 0. So, let's write that out. This theta 0 equals 360, theta 1 equals 0. And this pair of parameters corresponds to that hypothesis, corresponds to a flat line, right? This is h of x equals 360 plus 0 times x. So that's my hypothesis. And this hypothesis, again, has some cost, and that cost is, plotted as the height of the j function at that point. Let's look at just a couple of examples. Here's one more. At this value of theta 0 and at that value of theta 1, we end up with this hypothesis h of x. And again, not a great fit to the data, and we just actually move even further out for the minimum. Last example. This is actually not quite at the minimum, but it's pretty close to the minimum. So this is not such a bad fit to the data, where for a particular value of theta 0, which whatever this value is, and for a particular value of theta 1, we get a particular h of x. And this is not quite at the minimum, but it's pretty close. And so the sum of squares errors, the sum of squares distances between my training examples and my hypothesis, really that's a sum of squared distances, right, of all of these errors. This is pretty close to the minimum, even though it's not quite the minimum. So with these figures, I hope that gives you a better understanding of what values of the cost function j and how they are, and how that corresponds to different hypotheses, as well as how better hypotheses may correspond to points that are closer to the minimum of this cost function j. Now, of course, what we really want is an efficient algorithm, like an efficient piece of software, for automatically finding the value of theta 0 and theta 1 that minimizes the cost function j. Right? And what we don't want to do is to have to write software to plot out this point and then try to manually read off the numbers. That's just not a good way to do it. And in fact, we'll see later that when we look at more complicated examples, we'll have higher dimensional figures with more parameters. That it turns out we'll see later in this course examples where this figure cannot really be plotted and it becomes much harder to visualize. And so what we want is to have software to find the value of theta 0, theta 1 that minimizes this function. And in the next video, we'll start to talk about an algorithm for automatically finding that value of theta 0 and theta 1 that minimizes the cost function j. We previously defined the cost function j. In this video, I want to tell you about an algorithm called gradient descent for minimizing the cost function j. It turns out gradient descent is a more general algorithm and is used not only in linear regression, it's actually used all over the place in machine learning. And later in the class, we'll use gradient descent to minimize other functions as well, not just the cost function j for linear regression. So in this video, we're going to talk about gradient descent for minimizing some arbitrary function j, and then in later videos, we'll take this algorithm and apply it specifically to the cost function j that we had defined for linear regression. So here's the problem setup. We're going to assume that we have some function j of theta 0, comma theta 1. Maybe it's a cost function from linear regression. Maybe it's some other function we want to minimize. And we want to come up with an algorithm for minimizing that as a function of j of theta 0, theta 1. Just as an aside, it turns out that gradient descent actually applies to more general functions. So imagine if you have a function that's a function of j of theta 0, theta 1, theta 2, up to, say, some theta n, and you want to minimize theta 0, you minimize over theta 0 up to theta n of this j of theta 0 up to theta n. It turns out gradient descent is an algorithm for solving sort of this more general problem, but for the sake of brevity, for the sake of succinctness of notation, I'm just going to pretend I have only two parameters throughout the rest of this video. Here's the idea for gradient descent. What we're going to do is we're going to start off with some initial guesses for theta 0 and theta 1. Doesn't really matter what they are, but a common choice would be if we set theta 0 to 0 and set theta 1 to 0. Just initialize them to 0. What we're going to do in gradient descent is we'll keep changing theta 0 and theta 1 a little bit to try to reduce j of theta 0, theta 1 until hopefully we wind up at a minimum, or maybe at a local minimum. So let's see in pictures what gradient descent does. Let's say you're trying to minimize this function. So notice the axes. This is theta 0, theta 1 on the horizontal axis, and j is the vertical axis. And so the height of the surface shows j, and we want to minimize this function. So we're going to start off with theta 0, theta 1 at some point. So imagine picking some value for theta 0, theta 1, and that corresponds to starting at some point on the surface of this function. Okay, so whatever value of theta 0, theta 1 gives you some point here. I didn't initialize them to 0, 0, but sometimes you initialize it to other values as well. Now, I want you to imagine that this figure shows a hill. Imagine this is like the landscape of some grassy park with two hills like so. And I want you to imagine that you are physically standing at that point on the hill, right, on this little red hill in your park. In gradient descent, what we're going to do is we're going to spin 360 degrees around, just look all around us and ask, if I were to take a little baby step in some direction, and I want to go downhill as quickly as possible, what direction do I take that little baby step in if I want to go down, if I sort of want to physically walk down this hill as rapidly as possible? Turns out that if you're standing at that point on the hill and you look all around, you find that the best direction to take a little step downhill is roughly that direction. Okay? And now you're at this new point on your hill. You're going to again look all around and then say, what direction should I step in order to take a little baby step downhill? And if you do that and take another step, you take a step in that direction. And then you keep going. From this new point, you look around, decide what direction will take you downhill most quickly, take another step, and so on, until you converge to this local minimum down here. Gradient descent has an interesting property. This first time we ran gradient descent, we were starting at this point over here, right? Starts at that point over here. Now imagine we had initialized gradient descent just a couple steps to the right. Imagine we initialized gradient descent with that point on the upper right. If you were to repeat this process, so start from that point, look all around, take a little step in the direction of steepest descent, you would do that. Then look around, take another step, and so on. And if you started just a couple steps to the right, gradient descent would have taken you to this second local optimum over on the right. So if you had started at this first point, you would have wound up at this local optima. But if you started just a little bit, in a slightly different location, you would have wound up at a very different local optimum. And this is a property of gradient descent that we'll say a little bit more about later. So that's the intuition in pictures. Let's look at the math. This is the definition of the gradient descent algorithm. We're going to just repeatedly do this until convergence. We're going to update my parameter theta j by taking theta j and subtracting from it alpha times this term over here. Okay, so let's see. There are a lot of details in this equation, so let me unpack some of it. First, this notation here, colon equals, I'm going to use colon equals to denote assignment. So the assignment operator. So concretely, if I write a colon equals b, what this means is it means, in a computer, this means take the value in b and use it to overwrite whatever value is a. So this means, set a to be equal to the value of b. Okay, so it's assignment. And I can also do a colon equals a plus 1. This means take a and increase its value by 1. Whereas in contrast, if I use the equal sign, if I write a equals b, then this is a truth assertion. Okay, so if I write a equals b, then I'm asserting that the value of a equals to the value of b. Right? So the left-hand side, that's a computer operation where you set the value of a to a new value. The right-hand side, this is asserting, I'm just making a claim that the values of a and b are the same. And so whereas I can write a colon equals a plus 1, that means increment a by 1. Hopefully, I won't ever write a equals a plus 1 because that's just wrong, right? A and a plus 1 can never be equal to the same values. Okay, so that's the first part of the definition. This alpha here is a number that is called the learning rate. And what alpha does is it basically controls how big a step we take downhill with gradient descent. So if alpha is very large, then that corresponds to a very aggressive gradient descent procedure where we're trying to take huge steps downhill. And if alpha is very small, then we're taking little baby steps downhill. And I'll come back and say more about this later, about how to set alpha and so on. And finally, this term here, that's a derivative term. I don't want to talk about it right now, but I will derive this derivative term and tell you exactly what this is later. Okay, and some of you will be more familiar with calculus than others, but even if you aren't familiar with calculus, don't worry about it. I'll tell you what you need to know about this term here. Now, there's one more subtlety about gradient descent, which is in gradient descent, we're going to update, theta 0 and theta 1, right? So this update takes place for j equals 0 and j equals 1. So you're going to update theta 0 and update theta 1. And the subtlety of how you implement gradient descent is for this expression, right? For this update equation, you want to simultaneously update theta 0 and theta 1. What I mean by that is that, in this equation, we're going to update theta 0 colon equals theta 0 minus something, and update theta 1 colon equals theta 1 minus something. And the way to implement this is you should compute the right-hand side, right? Compute that thing for theta 0 and theta 1, and then simultaneously, at the same time, update theta 0 and theta 1. Okay? So let me say what I mean by that. This is a correct implementation of gradient descent, meaning simultaneous updates. So I'm going to set temp 0 equals that, set temp 1 equals that, so basically compute the right-hand sides. And then having computed the right-hand sides and stored them into variables temp 0 and temp 1, I'm going to update theta 0 and theta 1 simultaneously. So that's the correct implementation. In contrast, here's an incorrect implementation that does not do a simultaneous update. So in this incorrect implementation, we compute temp 0, and then we update theta 0, and then we compute temp 1, and then we update temp 1. And the difference between the right-hand side and the left-hand side implementations is that if you look down here, if you look at this step, if by this time you've already updated theta 0, then you would be using the new value of theta 0, to compute this derivative term. And so this gives you a different value of temp 1 than the left-hand side, right? Because you've now plugged in the new value of theta 0 into this equation. And so this on the right-hand side is not a correct implementation of gradient descent. Okay? So I don't want to say why you need to do the simultaneous updates. It turns out that, the way gradient descent is usually implemented, which we'll say more about later, it actually turns out to be more natural to implement the simultaneous update. And when people talk about gradient descent, they always mean simultaneous update. If you implement the non-simultaneous update, it turns out it will probably work anyway, but this algorithm on the right is not what people refer to as gradient descent, and this is some other algorithm with different properties. And for various reasons, this can behave in slightly stranger ways. And so, what you should do is really implement the simultaneous update of gradient descent. So that's the outline of the gradient descent algorithm. In the next video, we're going to go into the details of the derivative term, which I wrote out but didn't really define. And if you've taken a calculus class before, and if you're familiar with partial derivatives and derivatives, it turns out that's exactly what that derivative term is. But in case you aren't familiar with calculus, don't worry about it. The next video will give you all the intuitions and will tell you everything you need to know to compute that derivative term, even if you haven't seen calculus or even if you haven't seen partial derivatives before. With the next video, hopefully we'll be able to give you all the intuitions you need to apply gradient descent. In the previous video, we gave a mathematical definition of gradient descent. Let's delve deeper and in this video get better intuition about what the algorithm is doing and why the steps of the gradient descent algorithm might make sense. Here's a gradient descent algorithm that we saw last time. And just to remind you, this parameter or this term alpha is called the learning rate, and it controls how big a step we take when updating my parameter theta j. And this second term here is the derivative term. And what I want to do in this video is give you better intuition about what each of these two terms is doing and why, when put together, this entire update makes sense. In order to convey these intuitions, what I want to do is use a slightly simpler example where we want to minimize a function of just one parameter. So we have we have a cost function j of just one parameter theta 1, like we did a few videos back, where theta 1 is a real number. Okay, so just again, so we can have 1D plots, which are a little bit simpler to look at, and let's try to understand what gradient descent will do on this function. So let's say here's my function j of theta 1, and so that's my, and where theta 1 is a real number, right? Now, let's say I've initialized gradient descent with theta 1 at this location. So imagine that we start off at that point on my function. What gradient descent will do is it will update theta 1, gets updated as theta 1 minus alpha times dd theta 1 j of theta 1, right? And as an aside, this derivative term, right? If you're wondering why I changed the notation from these partial derivative symbols, if you don't know what the difference is between these partial derivative symbols and the dd theta, don't worry about it. Technically, in mathematics, we call this a partial derivative, we call this a derivative, depending on the number of parameters in the function j. But that's a mathematical technicality. So, for the purpose of this lecture, think of these partial symbols and dd theta 1 as exactly the same thing, and don't worry about whether there are any differences. I'm going to try to use the mathematically precise notation, but for our purposes, these two notations are really the same thing. So let's see what this equation will do. So we're going to compute this derivative. I'm not sure if you've seen derivatives in calculus before, but what the derivative at this point does is basically saying, let's take the tangent to that point, like that straight line, that red line, is just touching this function, and let's look at the slope of this red line. That's what the derivative is. It says, what's the slope of a line that is just tangent to the function? Okay, and the slope of a line, of course, is just, right, this height divided by this horizontal thing. Now, this line has a positive slope, so it has a positive derivative, and so my update to theta is going to be theta 1 gets updated as theta 1 minus alpha times some positive number. Okay, and alpha, the learning rate, is always a positive number. And so I'm going to take theta 1 gets updated as theta 1 minus something. So I'm going to end up moving theta 1 to the left. I'm going to decrease theta 1. And we can see this is the right thing to do because I actually want to head in this direction, to get me closer to the minimum over there. So gradient descent so far seems to be doing the right thing. Let's look at another example. So let's take my same function j. Let's try to draw the same function j of theta 1. And now let's say I had instead initialized my parameter over there on the left. So theta 1 is here. I'm going to at that point on the surface. Now my derivative term, dd theta 1, j of theta 1, when evaluated at this point, I'm going to look at the slope of that line. So this derivative term is the slope of this line. But this line is slanting down, so this line has negative slope. Right? Or alternatively, I say that this function has negative derivative, just means negative slope at that point. So this is less than or equal to 0. So when I update theta, I'm going to have theta gets updated as theta minus alpha times a negative number. And so I have theta 1 minus a negative number, which means I'm actually going to increase theta, right? Because this is minus of a negative number. It means I'm adding something to theta. And what that means is that I'm going to end up increasing theta. And so I'm going to start here and increase theta, which again seems like the thing I wanted to do to try to get me closer to the minimum. So this hopefully explains the intuition behind what the derivative term is doing. Let's next take a look at the learning rate term alpha and try to figure out what that's doing. So here's my gradient descent update rule, right? It's this equation. And let's look at what could happen if alpha is either too small or if alpha is too large. So in this first example, what happens if alpha is too small? So here's my function j of theta. Let's say I start here. If alpha is too small, then what I'm going to do is going to multiply my update by some small number. So I end up taking, it's like a baby step like that. Okay? So that's one step you're going to take. Then from this new point, I'm going to take another step, but if alpha is too small, I'm going to take another little baby step. And so if, if my learning rate is too small, I'm going to end up, taking these tiny, tiny baby steps to try to get to the minimum, and I'm going to need a lot of steps to get to the minimum. And so if alpha is too small, gradient descent can be slow because it's going to take these tiny, tiny baby steps, and so it's going to need a lot of steps before it gets anywhere close to the global minimum. Now, how about if alpha is too large? So here's my function j of theta. Turns out if alpha is too large, then gradient descent can overshoot the minimum and may even fail to converge or even diverge. So here's what I mean. Let's say I start off theta there. It's actually pretty close to minimum. So the derivative points to the right, but if alpha is too big, I'm going to take a huge step. Maybe I'll take a huge step like that. Right? So I end up taking a huge step. And now my cost function has actually gotten worse because I start off with this value, but now my value has actually gotten worse. Now my derivative points to the left. It says I should decrease theta. But if my learning rate is too big, I may take a huge step going from here all the way out there. So I end up going out there, right? And if my learning rate is too big, I can take another huge step on the next iteration and kind of overshoot and so on until you notice I'm actually getting further and further away from the minimum. And so if alpha is too large, it can fail to converge or even diverge. Now, I have another question for you. So this is a tricky one, and when I was first learning this stuff, it actually took me a long time to figure this out. What if your parameter theta1 is already at a local minimum? What do you think one step of gradient descent will do? So let's suppose you initialize theta1 at a local minimum. So, suppose this is your initial value of theta1 over here, and is already at a local optimum, at a local minimum. It turns out the local optimum, your derivative will be equal to 0. So let's look at that slope, right? It's that tangent point. So the slope of this line will be equal to 0, and thus this derivative term is equal to 0. And so in your gradient descent update, you have theta1 gets updated as theta1 minus alpha times 0. And so what this means is that if you're already at the local optimum, it leaves theta1 unchanged, because gets updates theta1 equals theta1. So if your parameter is already at the local minimum, one step of gradient descent does absolutely nothing. It doesn't change the parameter, which is what you want, because it keeps your solution at the local optimum. This also explains why gradient descent can converge to local minimum even with the learning rate alpha fixed. Here's what I mean by that. Let's look at an example. So here's a cost function j of theta that maybe I want to minimize. And let's say I initialize my algorithm, my gradient descent algorithm, out there at that magenta point. If I take one step of gradient descent, maybe it'll take me to that point, because my derivative is pretty steep out there, right? Now I'm at this green point, and if I take another step of gradient descent, you notice that my derivative, meaning the slope, is less steep at the green point than compared to at the magenta point out there, right? Because as I approach the minimum, my derivative gets closer and closer to 0 as I approach the minimum. So after one step of gradient descent, my new derivative is a little bit smaller. So when I take another step of gradient descent, I will naturally take a somewhat smaller step from this green point than I did from the magenta point. Now I'm at a new point, the red point, and then now even closer to the global minimum. So the derivative here will be even smaller than it was at the green point. So when I take another step of gradient descent, now my derivative term is even smaller, and so the magnitude of the update to theta1 is even smaller. So take a small step like so. And as gradient descent runs, you will automatically take smaller and smaller steps until eventually you're taking very small steps, and you finally converge to the local minimum. So just to recap, in gradient descent, as we approach a local minimum, gradient descent will automatically take smaller steps, and that's because as we approach the local minimum, by definition, the local minimum is when this derivative is equal to 0. So as we approach the local minimum, this derivative term will automatically get smaller, and so gradient descent will automatically take smaller steps. So this is what gradient descent looks like, and there's so actually no need to decrease alpha over time. So that's the gradient descent algorithm, and you can use it to try to minimize any cost function j, not the cost function j that we defined for linear regression. In the next video, we're going to take the function j and set that back to be exactly linear regression's cost function, the squared cost function that we came up with earlier. And taking gradient descent and the squared cost function and putting them together, that will give us our first learning algorithm. That will give us our linear regression algorithm. In previous videos, we talked about the gradient descent algorithm, and we talked about the linear regression model and the squared error cost function. In this video, we're going to put together gradient descent with our cost function, and that will give us an algorithm for linear regression, for fitting a straight line to our data. So this was what we worked out in the previous videos. There's our gradient descent algorithm, which should be familiar, and here's the linear regression model with our linear hypothesis and our squared error cost function. What we're going to do is apply gradient descent to minimize our squared error cost function. Now, in order to apply gradient descent, in order to write this piece of code, the key term we need is this derivative term over here. So we need to figure out what is this partial derivative term, and plugging in the definition of the cost function j, this turns out to be this, sum from I equals 1 through m of this squared error cost function term. And all I did here was I just plugged in the definition of the cost function there. And simplifying a little bit more, this turns out to be equal to this, sum from I equals 1 through m of theta 0 plus theta 1 xi minus yi squared. And all I did there was I took the definition for my hypothesis and plugged it in there. And turns out we need to figure out what is this partial derivative for two cases, for j equals 0 and for j equals 1. So we want to figure out what is this partial derivative for both the theta 0 case and the theta 1 case. And I'm just going to write out the answers. It turns out this first term is simplifies to 1 over m sum from over my training set of just that, xi minus yi. And for this term, partial derivative with respect to theta 1, it turns out I get this term, minus yi times xi. Okay? And computing these partial derivatives, sort of, going from this equation, right, going from this equation to either of the equations down there, computing those partial derivative terms requires some multivariate calculus. If you know calculus, feel free to work through the derivations yourself and check that if you take the derivatives, you actually get the answers that I got. But if you are less familiar with calculus, don't worry about it, and it's fine to just take these equations that were worked out, and you won't need to know calculus or anything like that in order to do the homework or to implement gradient descent and get that to work. But so armed with these definitions, or armed with what we worked out to be the derivatives, which is really just the slope of the cost function j, we can now plug them back into our gradient descent algorithm. So here's gradient descent for linear regression. We're just going to repeat until convergence. Theta 0 and theta 1 get updated as, this thing minus alpha times the derivative term. So this term here. So here's our linear regression algorithm. This first term here, that term is, of course, just the partial derivative with respect to theta 0 that we worked out on the previous slide. And this second term here, that term is just the partial derivative with respect to theta 1 that we worked out on the previous slide. And just as a quick reminder, you must, when implementing gradient descent, there's actually this detail that you should be implementing it so the update theta 0 and theta 1 simultaneously. So let's see how gradient descent works. One of the issues we saw with gradient descent is that it can be susceptible to local optima. So when I first explained gradient descent, I showed you this picture of it, going downhill on the surface, and we saw how, depending on where you initialize it, you can end up at different local optima. You end up, here or here. But it turns out that the cost function for linear regression is always going to be a bow-shaped function like this. The technical term for this is that this is called a convex function. And I'm not going to give the formal definition for what is a convex function, C-O-N-V-E-X, but informally, a convex function means a bow-shaped function, kind of like a bow-shaped. And so this function doesn't have any local optima except for the one global optimum. And thus gradient descent on this type of cost function, which you get whenever you're using linear regression, it will always converge to the global optimum because there are no other local optima other than the global optimum. So now let's see this algorithm in action. As usual, here are plots of the hypothesis function and of my cost function j. And so let's say I've initialized my parameters at this value. Let's say usually you initialize your parameters at 0, 0, theta 0, and theta 1 equals 0. But for illustration, in this particular implementation of gradient descent, I've initialized theta 0 at about 900 and theta 1 at about minus 0.1. Okay, and so this corresponds to h of x equals minus 900 minus 0.1x is this line. And so we're out here on the cost function. Now, if we take one step of gradient descent, we end up going from this point out here, a little bit to the down and left, to that second point over there. And you notice that my line changed a little bit. And as I take another step of gradient descent, my line on the left will change, right? And I've also moved to a new point on my cost function. And as I take further steps of gradient descent, I'm going down in cost, right? So my parameters is sort of following this trajectory. And if you look on the left, this corresponds to hypotheses that, seem to be getting to be better and better fits to the data, until eventually I've now wound up at the global minimum, and this global minimum corresponds to this hypothesis, which gives me a good fit to the data. And so that's gradient descent, and we've just run it and gotten a good fit to my data set of housing prices, and you can now use it to predict, if your friend has a house that costs of size 1250 square feet, you can now read off the value and tell them that, I don't know, maybe they can get $250,000 for their house. Finally, just to give this another name, it turns out that the algorithm that we just went over is sometimes called batch gradient descent. And it turns out in machine learning, I don't know, I feel like us machine learning people, we're not always great at giving names to our algorithms. But the term batch gradient descent means that refers to the fact that in every step of gradient descent, we're looking at all of the training examples. So in gradient descent, when computing derivatives, we're computing these sums, right? This sum of. So in every step of gradient descent, we end up computing something like this that sums over all m training examples. And so the term batch gradient descent refers to the fact that we're looking at the entire batch of training examples. And again, this is really maybe not a great name, but this is what machine learning people call it. And it turns out that there are sometimes other versions of gradient descent that are not batch versions, but that instead do not look at the entire training set, but look at small subsets of the training set at a time. And we'll talk about those versions later in this course as well. But for now, using the algorithm you just learned about, or using batch gradient descent, you now know how to implement gradient descent for linear regression. So that's linear regression with gradient descent. If you've seen advanced linear algebra before, so some of you may have taken a class in advanced linear algebra, you might know that there exists a solution for numerically solving for the minimum of the cost function j without needing to use an iterative algorithm like gradient descent. Later in this course, we'll talk about that method as well, that just solves for the minimum of the cost function j without needing just multiple steps of gradient descent. That other method is called the normal equations method, but in case you've heard of that method, it turns out that gradient descent will scale better to larger data sets than that normal equation method. And now that we know about gradient descent, we'll be able to use it in lots of different contexts, and we'll use it in lots of different machine learning problems as well. So, congrats on learning about your first machine learning algorithm. We'll later have exercises in which we'll ask you to implement gradient descent and hopefully see these algorithms work for yourselves. But before that, I first want to tell you in the next set of videos, I first want to tell you about a generalization of the gradient descent algorithm that will make it much more powerful. And I guess I'll tell you about that in the next video. You now know about linear regression and gradient descent. The plan from here on out is to tell you about a couple important extensions of these ideas. Concretely, here they are. First, it turns out that in order to solve this minimization problem, Turns out there's an algorithm for solving for theta 0 and theta 1 exactly without needing an iterative algorithm, without needing this algorithm like gradient descent that we had to iterate, multiple times over. So it turns out there are advantages and disadvantages of this algorithm that lets you just solve for theta 0 and theta 1, so basically just in one shot. One advantage is that there's no longer a learning rate alpha that you need to worry about and set, and so it can be much faster for some problems. We'll talk about its advantages and disadvantages later. Second, we'll also talk about algorithms for learning with a larger number of features. So far we've been learning with just one feature, the size of the house, and using that to predict the price. So we're trying to take X and use that to predict Y. But for other learning problems, we may have a larger number of features. So for example, let's say that you know not only the size, but also the number of bedrooms, number of floors, and the age of home of these houses, and you want to use that to predict the price of the houses. In that case, maybe we'll call these features x1, x2, x3, and x4. So now we have 4 features. We want to use these 4 features to predict Y, the price of the house. It turns out with all of these features, and 4 of them in this case, it turns out that with multiple features it becomes harder to plot or to visualize the data. So for example, we try to plot this type of data set. Maybe we'll have the vertical axis be the price, and maybe we can have one axis here and another one here where this axis is the size of the house and that axis is the number of bedrooms. But this is just plotting, right? My first 2 features, size and number of bedrooms, and when we have these additional features, I don't know, I just don't know how to plot all of these data, right? Because I need like a 4-dimensional or a 5-dimensional figure. I don't really know how to plot, something more than like a 3-dimensional figure, like what I have over here. Also, as you can tell, the notation starts to get a little more complicated, right? So rather than just having XR features, we now have X1 through X4, and we're using these subscripts to denote my 4 different features. It turns out the best notation to keep all of this straight and to understand what's going on with the data, even when we don't quite know how to plot it, it turns out that the best notation is the notation of linear algebra. Linear algebra gives us a notation and a set of things, or a set of operations that we can do with matrices and vectors. For example, here's a matrix where the columns of this matrix are, the first column is the sizes of the 4 houses, the second column was the number of bedrooms, that's the number of floors, and that was the age of the home. And so a matrix is this block of numbers that lets me take all of my data, all of my x's, all of my features, and organize them efficiently into sort of one big block of numbers like that. And here is what we call a vector in linear algebra, where the 4 numbers here are the prices of the 4 houses that we saw on the previous slide. So in the next set of videos, what I'm going to do is do a quick review of linear algebra. If you haven't seen matrices and vectors before, so if all of this, everything on this slide is brand new to you, or if you've seen linear algebra before, but it's been a while, so you aren't completely familiar with it anymore, then please watch the next set of videos, and I'll quickly review the linear algebra you need in order to implement and use the more powerful versions of linear regression. It turns out linear algebra isn't just useful for linear regression models, but these ideas of matrices and vectors will be useful for helping us to implement and actually get computationally efficient implementations for many later machine learning models as well. And as you can tell, these sorts of matrices and vectors will give us an efficient way to start to organize large amounts of data when we work with larger training sets. So in case you're not familiar with linear algebra, or in case linear algebra seems like a complicated little scary concept because we've never seen it before, don't worry about it. It turns out in order to implement machine learning algorithms, we need only the very, very basics of linear algebra, and you'll be able to very quickly pick up everything you need to know in the next few videos. Concretely, to decide if you should watch the next set of videos, here are the topics I'm going to cover. Talk about what are matrices and vectors, and talk about how to add, subtract, multiply matrices and vectors, and talk about the ideas of matrix inverses and transposes. And so if you're not sure if you should watch the next set of videos, take a look at these 2 things. So if you think you know how to compute this quantity. That's a matrix transpose times another matrix. If you think you know, if you've seen this stuff before, if you know how to compute the inverse of a matrix times a vector minus a number times another vector, if these two things look completely familiar to you, then you can safely skip the optional set of videos on linear algebra. But if these concepts, if you're just slightly uncertain what these blocks of numbers, what these matrices and numbers mean, then please take a look at the next set of videos, and it will very quickly teach you what you need to know about linear algebra in order to program machine learning algorithms and deal with large amounts of data. Let's get started with our linear algebra review. In this video, I want to tell you what are matrices and what are vectors. A matrix is a rectangular array of numbers written between square brackets. So for example, here is a matrix. I'm going to write a left square bracket and then write in a bunch of numbers. And these could be features for a machine learning problem, or it could be data from somewhere else. But for example, the specific values don't matter. And then I'm going to close it with another right bracket on the right. And so that's one matrix. And here's another example of a matrix. I'm just going to write 1, 2, 3, 4, 5, 6. So a matrix is just another way for saying is a 2D or a two-dimensional array. And the other piece of terminology we need is that the dimension of a matrix is going to be written as the number of rows times the number of columns in the matrix. So concretely, this example on the left, this has 1, 2, 3, 4 rows, and it has 2 columns. And so this example on the left, I'm going to say this is a 4 by 2 matrix, okay? Because it's number of rows by number of columns, so 4 rows, 2 columns. This one on the right, this matrix has 2 rows. So that's the first row, that's the second row, and it has 3 columns, right? That's the first column, that's the second column, that's the third column. So this second matrix, we say it is a 2 by 3 matrix, or we say that the dimension of this matrix is 2 by 3. And sometimes you also see this written out as, in the case of the left, you see this written out as R4 by 2. Or concretely, what people will sometimes say is that this matrix is an element of the set R4 by 2. So this thing here, this just means a set of all matrices that are of dimension 4 by 2. And this thing on the right, sometimes this is written out as a matrix that's an R2 by 3. So if you ever see, 2 by 3. So if you ever see something like this, R4 by 2 or R2 by 3, people are just referring to matrices of a specific dimension. Next, let's talk about how to refer to specific elements of the matrix. And by matrix elements of the matrix, I just mean the entries or the numbers inside the matrix. So in the standard notation, if A is this matrix here, then A subscript ij is going to refer to the I comma j entry, meaning the entry in the matrix is in the ith row and the jth column. So for example, A11 is going to refer to the entry in the first row and the first column. So that's the first row and the first column. And so, A11 is going to be equal to 1402. Another example, A12 is going to refer to the entry in the first row and the second column. And so A12 is going to be equal to 191. Just a couple more quick examples. Let's see, let's say A32 is going to refer to the entry in the third row and the second column, right? Because that's 3, 2, so that's equal to 1, 4, 3, 7. And finally, A41 is going to refer to, this one, right? Fourth row, first column is equal to 147. And if, hopefully you won't, but if you were to write, say, what is A43? Well, that refers to the fourth row and the third column, but, this matrix has no third column, so this is undefined. Or you can think of this as an error. So there's no such element as a A43, so, shouldn't be referring to A43. So the matrix gives you a way of letting you quickly organize, index, and access lots of data. And in case I seem to be tossing up a lot of concepts, a lot of new notation very rapidly, you don't need to memorize all this, but on the course website, where we have posted the lecture notes, we also have all of these definitions written down. So you can always refer back, either to these slides posted on the course website or to the lecture notes if you forget, like, well, A41 is that, which row, which column is that. Don't worry about memorizing everything now. You can always refer back to the written materials on the course website, use that as a reference. So that's what a matrix is. Next, let's talk about what is a vector. A vector turns out to be a special case of a matrix. A vector is a matrix that has only one column. So if you have an n by 1 matrix, then that's remember, right? N is the number of rows, and 1 here is the number of columns. So a matrix with just one column is what we call a vector. So here's an example of a vector, right? With, I guess I have n equals 4 elements here. So we also call this thing, another term for this is that this is a 4-dimensional vector. It just means that this is a vector with 4 elements, with 4 numbers in it. And just as earlier for matrices, you saw this notation like R3 by 2 to refer to 3 by 2 matrices, right? For this vector, we're going to refer this to this as a vector in the set R4. So this R4, again, just means a set of all 4-dimensional vectors. Next, let's talk about how to refer to elements of the vector. We're going to use the notation yi to refer to the ith element of the vector y. So if y is this vector, y subscript I is the ith element. So y1 is the first element, is equal to 460. Y2 is equal to the second element, right? 232 is the first, is the second. Y3 is equal to 315, and so on. And only y1 through y4 are defined because this is a 4-dimensional vector. Also, it turns out that there are actually 2 conventions for how to index into a vector. And here they are. Sometimes people will use 1 index and sometimes 0 index vectors. So this example on the left is a 1 index vector where the elements we write as y1, y2, y3, y4. And this example on the right is an example of a 0 index vector where we start the indexing of the elements from 0. So the elements go from y0 up to y3. And this is a little bit like the arrays of some programming languages, right, where the arrays can either be indexed starting from 1, so the first element of an array is sometimes say y1, this is kind of C++ notation, I guess, and sometimes is 0 index, depending on what programming language you use. So it turns out that in most of math, the 1 index version is more common, but for a lot of machine learning applications, 0 index vectors gives us a more convenient notation. So what you should usually do is, unless otherwise specified, you should assume that we're using 1 index vectors. In fact, throughout the rest of these videos on linear algebra review, I will be using 1 index vectors. But just be aware that when we talk about machine learning applications, sometimes I'll explicitly say when we need to use 0 index vectors as well. Finally, by convention, usually when writing matrices and vectors, most people will use uppercase to refer to matrices. So when we use capital letters like A, B, C, X to refer to matrices, and usually we'll use lowercase like A, B, X, Y to refer to either numbers, just real numbers or scalars, or to vectors. But this isn't always true, but this is the more common notation where we use lowercase y to refer to vector, and we usually use uppercase to refer to a matrix. So you now know what are matrices and vectors. Next, we'll talk about some of the things you can do with them. In this video, we'll talk about matrix addition and subtraction, as well as how to multiply a matrix by a number, also called scalar multiplication. Let's start with an example. Given 2 matrices like these, let's say I want to add them together. How do I do that? And so what does addition of matrices mean? It turns out that if you want to add 2 matrices, what you do is you just add up the elements of these matrices one at a time. So my result of adding two matrices is going to be itself another matrix. And the first element I get just by taking 1 and 4 and multiplying them and adding them together. So I get 5. The second element I get by taking 2 and 2 and adding them. So I get 4. 3 plus 0 is 3, and so on. I'm going to stop changing colors, I guess. And on the right is 0.5, 10, and 2. And it turns out you can add only two matrices that are of the same dimension. So this example is a 3 by 2 matrix because this has 3 rows and 2 columns, so it's 3 by 2. This is also a 3 by 2 matrix, and the result of adding these two matrices is a 3 by 2 matrix again. So you can only add matrices of the same dimension, and the result will be another matrix that's of the same dimension as the ones you just added. Whereas in contrast, if we were to take these two matrices, so this one is a 3 by 2 matrix, so again 3 rows, 2 columns. This here is a 2 by 2 matrix. And because these two matrices are not of the same dimension, you know, this is an error. So you cannot add these two matrices, and you know their sum is not well defined. So that's matrix addition. Next, let's talk about multiplying matrices by a scalar number. And a scalar is just maybe an overly fancy term for, you know, a number or a real number. Right? The scalar just means real number. So let's take the number 3 and multiply it by this matrix. If you do that, the result is pretty much what you'd expect. You just take your elements of the matrix and multiply them by 3 one at a time. So, you know, 1 times 3 is 3. 2 times 3 is 6. 3 times 3 is 9. And let's see, I'm going to stop changing colors again. 0 times 3 is 0. 3 times 5 is 15. And 3 times 1 is 3. And so this matrix is the result of multiplying that matrix on the left by 3. And you notice, again, this is a 3 by 2 matrix, and the result is a matrix of the same dimension. This is a 3 by 2. Both of these are 3 by 2 dimensional matrices. And by the way, you can write multiplication, you know, either way. So I had 3 times this matrix. I could also have written this matrix 1, 0, 2, 5, 3, 1, right? I just copied this matrix over to the right. I can also take this matrix and multiply this by 3. So whether it's, you know, 3 times the matrix or the matrix times 3 is the same thing, and this thing here in the middle is the result. You can also take a matrix and divide it by a number. So turns out taking this matrix and dividing it by 4, this is actually the same as taking the number 1/4 and multiplying it by this matrix, 4063. And so, you know, you can figure the answer. The result of this product is, you know, 1/4 times 4 is 1, 1/4 times 0 is 0, 1/4 times 6 is, 3 halves. That 6 over 4 is 3 halves, and 1/4 times 3 is 3/4. And so that's the result of computing, you know, this matrix divided by 4. That gives you the result. Finally, for a slightly more complicated example, you can also take these operations and combine them together. So in this calculation, I have 3 times a vector plus a vector minus another vector divided by 3. So just make sure we know what these are, right? This multiplication, this is an example of scalar multiplication, because I'm taking 3 and multiplying it. And this is, you know, another scalar multiplication, or I'm going to write scalar division, I guess. This really just means 1/3 times this. And so if we evaluate these two operations first, then what we get is this thing is equal to, let's see, so 3 times that vector is 3, 12, 6, plus my vector in the middle, which is a 0, 0, 5, minus 1, 0, 2/3, right? And again, just to make sure we understand what's going on here, this plus symbol, that is matrix addition, right? Already, since these are vectors, remember vectors are special cases of matrices, right? We can also call this vector addition. And this minus sign here, this is again matrix subtraction, but because this is a n by 1, really a 3 by 1 matrix, that this is actually a vector, so this is also vector. Just call this matrix a vector subtraction as well. Okay, and finally, to wrap this up, this therefore gives me a vector whose first element is going to be 3 plus 0 minus 1, so that's 3 minus 1, which is 2. The second element is 12 plus 0 minus 0, which is 12. And the third element of this is, 6 plus 5 minus 2/3, which is 11 minus 2/3, so that's 10 and 1/3. And I'm going to close my square bracket. And so this gives me a 3 by 1 matrix, which is also just called a 3-dimensional vector, right? Which is the outcome of this calculation over here. So that's how you add and subtract matrices and vectors and multiply them by scalars, or by real numbers. So far, I've only talked about how to multiply matrices and vectors by scalars, by real numbers. In the next video, we'll talk about a much more interesting step of taking two matrices and multiplying two matrices together. In this video, I'd like to start talking about how to multiply together two matrices. We'll start with a special case of that, of matrix vector multiplication, of multiplying a matrix together with a vector. Let's start with an example. Here's a matrix, and here's a vector, and let's say we want to multiply together this matrix with this vector. What's the result? Let me just work through this example, and then we will step back and look at just what the steps were. It turns out the result of this multiplication process is going to be itself a vector. And I'm just going to work through this first, so later we'll come back and see, just what I did here. To get the first element of this vector, I'm going to take these two numbers and multiply them with the first row of the matrix and add up the corresponding numbers. I'm going to take 1 multiplied by 1, and take 3 and multiply by 5, and that's what? That's 1 plus 15, so that gives me 16. I'm going to write 16 here. Then for the second element, I'm going to take the second row and multiply it by this vector. So I have 4 times 1 plus 0 times 5, which is equal to 4. So I get a 4 there. And finally, for the last one, I have 2, 1 times 1, 5. So I have 2 by 1 plus 1 by 5, which is equal to 7. And so I get a 7 over there. Okay? And it turns out that the result of multiplying that's a 3 by 2 matrix by a 2 by 1 matrix, this is also just a 2-dimensional vector. The result of this is going to be a 3 by 1 matrix. So that's why I get a 3 by 1 matrix. In other words, a 3 by 1 matrix is just a 3-dimensional vector. So I realized that I did that pretty quickly, and you're probably not sure if you can repeat this process yourself, but let's look in more detail at what just happened and what this process of multiplying a matrix by a vector looks like. Here are the details of how to multiply a matrix by a vector. Let's say I have a matrix A and I want to multiply that by a vector X. The result is going to be some vector Y. So the matrix A here is an m by n dimensional matrix, so m rows and n columns, and I'm going to multiply that by a n by 1 matrix, so in other words by an n-dimensional vector. It turns out this n here has to match this n here. In other words, the number of columns in this matrix, so the number of columns, they're going to be n columns. Number of columns here has to match the number of rows here, or it has to match the dimension of this vector. And the result of this product is going to be an m-dimensional vector y. Okay, so in other words, the number of rows here, m, is going to be equal to the number of rows in this matrix A. So how do you actually compute this vector y? Well, it turns out to compute this vector y, the process is to get yi, multiply a's ith row with the elements of the vector x and add them up. So here's what I mean. In order to get the first element of y, that first number, whatever that turns out to be, we're going to take the first row of the matrix A and multiply them one at a time with the elements of this vector x. So we're going to take this first number, multiply by this first number, then take the second number, multiply by this second number, take this third number, whatever that is, multiply the third number, and so on until we get to the end. And then we're going to add up the results of these products, and the result of adding that up is going to give us this first element of y. Then when we want to get the second element of y, like say this element, the way we do that is we take the second row of A and we repeat the whole thing. So we take the second row of A and multiply elements y, so the elements of x, and add up the results of the products, and that would give me the second element of y. And you keep going to get, and then I'm going to take the third row of A, multiply elements y's, with the vector x, sum up the results, and then I get the third element, and so on until I get down to the last row, like so. Okay, so that's the procedure. Let's do one more example. Here's the example. So let's look at the dimensions. Right here, this is a 3 by 4-dimensional matrix. This is a 4-dimensional vector, or a 4 by 1 matrix. And so the result of this product is going to be a 3-dimensional vector. So I'm going to write, a vector with room for 3 elements. Let's carry out the products. So for the first element, I'm going to take these 4 numbers and multiply them with the vector x. So I have 1 times 1 plus 2 times 3 plus 1 times 2 plus 5 times 1, which is equal to, that's 1 plus 6 plus 2 plus 6, which gives me 14. And then for the second element, I'm going to take this row now and multiply it with this vector. So I start with 0 times 1 plus 3, right? So 0 times 1 plus 3 times 3 plus 0 times 2 plus 4 times 1, which is equal to, let's see, that's 9 plus 4, which is 13. And finally, for the last element, I'm going to take this last row. So I have minus 1 times 1, minus 2, or really this is plus negative 2, I guess, times 3 plus 0 times 2 plus 0 times 1. And so that's going to be minus 1 minus 6, which is going to be negative 7. And so that's negative 7. Okay, so my final answer is this vector 14, just to write it out without the colors, 14, 13, negative 7. And as promised, the result here is a 3 by 1 matrix. So that's how you multiply a matrix and a vector. I know that a lot just happened on this slide, so if you're not quite sure where all these numbers went, feel free to pause the video and sort of take a slow, careful look at this big calculation that we just did and try to make sure that you understand the steps of what just happened to get us these numbers 14, 13, and 7. Finally, let me show you a neat trick. Let's say we have a set of 4 houses, so 4 houses with 4 sizes like these, and let's say I have a hypothesis for predicting what is the price of a house. And let's say I want to compute, h of x for each of my 4 houses here. It turns out there's a neat way of posing this, applying this hypothesis to all of my houses at the same time. It turns out there's a neat way to pose this as a matrix vector multiplication. So here's how I'm going to do it. I'm going to construct a matrix as follows. My matrix is going to be 1, 1, 1, 1 times, and I'm going to write down the sizes of my 4 houses here. And I'm going to construct a vector as well. And my vector is going to be this vector of 2 elements. That's these minus 40 and 0.25. That's these two coefficients, theta 0 and theta 1. And what I'm going to do is take this matrix and that vector and multiply them together. Right? That times is this multiplication symbol. So what do I get? Well, this is a 4 by 2 matrix. This is a 2 by 1 matrix. So the outcome is going to be a 4 by 1 vector. Right? So let me, so this is going to be a 4 by 1 matrix is the outcome, or really a 4-dimensional vector. So let me write in one of my 4 elements. I'm going to have 4 real numbers here. Now it turns out the first element of this result, right, the way I'm going to get that is I'm going to take this and multiply it by this vector. And so this is going to be minus 40 times 1 plus 0.25 times 2104. By the way, on the earlier slides I was writing 1 times minus 40 and 2104 times 0.25, right? But the order doesn't matter, right? Minus 40 times 1 is the same as 1 times minus 40. And this first element, of course, is h applied to 2104. So it's really the predicted price of my first house. Well, how about the second element? Hope you can see where I'm going. To get the second element, right, I'm going to take this and multiply it by my vector, and so that's going to be minus 40 times 1 plus 0.25 times 1416, and so this is going to be h of 1416, right, and so on for the third and the and so on for the third and the fourth elements of this 4 by 1 vector. And just be clear, right? This thing here that I just drew the green box around, that's a real number, okay? That's a single real number. And this thing here that I drew the magenta box around, the purple magenta color box around, that's a real number, right? And so this thing on the right, this thing on the right overall, this is a 4 by 1 dimensional matrix with a 4-dimensional vector. And the neat thing about this is that when you're actually implementing this in software, so when you have 4 houses and when you want to use your hypothesis to predict the prices, to predict the price y of all of these 4 houses, what this means is that you can write this in one line of code. When we talk about Octave and programming languages later, you can actually write this in one line of code. You write prediction equals my data matrix times parameters, right? Where data matrix is this thing here and parameters is this thing here, and this times is a matrix vector multiplication. And if you just do this, then this variable prediction, sorry about my bad handwriting, but if you just implement this one line of code, assuming you have an appropriate library to do a matrix vector multiplication, if you just do this, then prediction becomes this 4 by 1 dimensional vector on the right that just gives you all the predicted prices. And the alternative, to doing this as a matrix vector multiplication would be to write something like, for I equals 1 to 4, right? And you have, say, 1,000 houses, it'd be for I equals 1 to 1,000 or whatever. But then you have to write a prediction, of I equals, and then do a bunch more work over there. And it turns out that when you have a large number of houses, if you were trying to predict the prices of not just 4, but maybe of 1,000 houses, then it turns out that when you implement this in a computer, implementing it like this, in any of various languages, this is not true only for Octave, but for C++, Java, Python, other languages as well. It turns out that by writing code in this style on the left, it allows you to not only simplify the code, because now you're just writing one line of code rather than a for loop with a bunch of things inside, but for subtle reasons that we'll see later, it turns out to be much more computationally efficient to make predictions on all of the prices of all of your houses, doing it the way on the left than the way on the right, than if you were to write your own for loop. And I'll say more about this later when we talk about vectorization. But so by posing prediction this way, you get not only a simpler piece of code, but a more efficient one. So that's it for matrix vector multiplication, and we'll make good use of these sorts of operations as we develop the linear regression and other models further. But in the next video, we're going to take this and generalize this to the case of matrix-matrix multiplication. In this video, we'll talk about matrix-matrix multiplication, or how to multiply two matrices together. When we talk about the method in linear regression for how to solve for the parameters theta 0 and theta 1 all in one shot, so that without needing an iterative algorithm like gradient descent, when we talk about that algorithm, it turns out that matrix-matrix multiplication is one of the key steps that you need to know. So let's, as usual, start with an example. Let's say I have two matrices and I want to multiply them together. Let me again just work through this example and then I'll tell you a little bit what happened. So the first thing I'm going to do is I'm going to pull out the first column of this matrix on the right. And I'm going to take this matrix on the left and multiply it by, a vector that's just this first column. Okay? And it turns out if I do that, I'm going to get the vector 11, 9. So this is the same matrix vector multiplication as you saw in the last video. I worked this out in advance, so I know it's 11, 9. And then the second thing I'm going to do is I'm going to pull out the second column of this matrix on the right, and I'm then going to take this matrix on the left, right? So take that matrix and multiply it by that second column on the right. So again, this is a matrix vector multiplication step, which you saw from the previous video. And it turns out that if you multiply this matrix and this vector, you get 10, 14. And by the way, if you want to practice your matrix vector multiplication, feel free to pause the video and check this product yourself. Then I'm just going to take these two results and put them together, and that'll be my answer. So it turns out the outcome of this product is going to be a 2 by 2 matrix, and the way I'm going to fill in this matrix is just by taking my elements 11, 9 and plugging them here, and taking 10, 14 and plugging them into the second column. Okay, so that was the mechanics of how to multiply a matrix by another matrix. You basically look at the second matrix one column at a time, and then you assemble the answers. And again, we'll step through this much more carefully in a second. But just want to point out also, this first example is a 2 by 3 matrix. I'm multiplying that by a 3 by 2 matrix, and the outcome of this product, it turns out to be a 2 by 2 matrix. And again, we'll see in a second why this was the case. All right, that was the mechanics of the calculation. Let's actually look at the details and look at what exactly happened. Here are the details. I have a matrix A, and I want to multiply that with a matrix B, and the result will be some new matrix C. And it turns out you can only multiply together matrices whose dimensions match. So A is an n by n matrix, so m rows, n columns. And I'm going to multiply that with an n by o matrix. And it turns out this n here must match this n here. So the number of columns in the first matrix must equal to the number of rows in the second matrix. And the result of this product will be a m by o matrix, like the matrix C here. And in the previous video, everything we did corresponded to the special case of O being equal to 1. Okay, that was to the case of B being a vector. But now we're going to deal with the case of values of O larger than 1. So here's how you multiply together the two matrices. In order to get, what I'm going to do is I'm going to take the first column of B and treat that as a vector, and multiply the matrix A with the first column of B. And the result of that will be a m by 1 vector, and I'm going to put that over here. Then I'm going to take the second column of B, right? So this is another n by 1 vector. So this column here, this is right n by 1. It was an n-dimensional vector. Going to multiply this matrix with this n by 1 vector. The result will be a m-dimensional vector, which I'm going to put there, and so on. Okay, and so and then I'm going to take the third column, multiply it by this matrix. I get a m-dimensional vector, and so on until you get to the last column times the matrix times the last column gives you the last column of C. Just to say that again, the ith column of the matrix C is obtained by taking the matrix A and multiplying the matrix A with the ith column of the matrix B for the values of I equals 1 to up through O. Okay, so this is just a summary of what we did up there in order to compute the matrix C. Let's look at just one more example. Let's say I want to multiply together these two matrices. So what I'm going to do is first pull out the first column of my second matrix. That was my matrix B on the previous slide, and I therefore have this matrix times that vector. And so let's do this calculation quickly. This is going to be equal to, right, 1 3 times 0 3, so that gives 1 times 0 plus 3 times 3, and the second element is going to be 2 5 times 0 3, so that's going to be 2 times 0 plus 5 times 3, and that is 9 15. Okay, oh, actually let me write that in green. So this is 9 15, and then next I'm going to pull out the second column of this and do the corresponding calculation. So that's this matrix times this vector 1 2. Let's also do this quickly. So that's 1 times 1 plus 3 times 2. So just that was that row. And let's do the other one. So let's see. That gives me what? 2 times 1 plus times 2. And so that is going to be equal to, let's see, 1 times 1 plus 3 times 1 is 4. And 2 times 1 plus 5 times 2 is 12. So now I have these two, and so my outcome, so the product of these two matrices is going to be, this goes here, and this goes here. So I get 9, 15, and 4, 12. And you may notice also that the result of multiplying a 2 by 2 matrix with another 2 by 2 matrix, the resulting dimension is going to be that first 2 times that second 2. So the result is itself also a 2 by 2 matrix. Finally, let me show you one more neat trick that you can do with matrix-matrix multiplication. Let's say as before that we have 4 houses whose prices we want to predict. Only now we have 3 competing hypotheses shown here on the right. So if you want to apply all 3 competing hypotheses to all 4 of your houses, it turns out you can do that very efficiently using a matrix-matrix multiplication. So here on the left is my usual matrix, same as from the last video, where these values are my housing prices, and I've put ones here on the left as well. And what I'm going to do is construct another matrix where here the first column is this minus 40 and 0.25, and the second column is this 200, 0.1, and so on. Okay? And it turns out that if you multiply these two matrices, what you find is that this first column, let me draw that in blue. Well, how do you get this first column, right? Our procedure for matrix-matrix multiplication is, the way you get this first column is you take this matrix and you multiply it by this first column. And we saw in the previous video that this is exactly the predicted housing prices of the first hypothesis, right, of this first hypothesis here. And how about the second column? Well, how do you get the second column? The way you get the second column is, well, you take this matrix and you multiply it by this second column. And so the second column turns out to be the predictions of the second hypothesis up there. And similarly for the third column. And so I didn't step through all the details, but hopefully you feel free to pause the video and check the math yourself and check that what I just claimed really is true. But it turns out that by constructing these two matrices, what you can therefore do is very quickly apply all 3 hypotheses to all 4 house sizes to get, all 12 predicted prices output by your 3 hypotheses on your 4 houses. So with just one matrix multiplication step, you manage to make 12 predictions. And even better, it turns out that in order to do that matrix multiplication, there are lots of good linear algebra libraries in order to do this multiplication step for you. And no matter pretty much any reasonable programming language that you might be using, certainly all the top 10 most popular programming languages will have great linear algebra libraries. And there'll be good linear algebra libraries that are highly optimized in order to do that matrix multiplication very efficiently, including taking advantage of any sort of parallel computation that your computer may be capable of, whether your computer has multiple cores or multiple processors, or within a processor sometimes there's parallelism as well, called SIMD parallelism, that your computer can take care of. And you should be able to, and there are very good free libraries that you can use to do this matrix multiplication very efficiently, so that you can very efficiently make lots of predictions of lots of hypotheses. Matrix multiplication is really useful since you can pack a lot of computation into just one matrix multiplication operation. But you should be careful of how you use them. In this video, I want to tell you about a few properties of matrix multiplication. When working with just real numbers, or when working with scalars, multiplication is commutative. And what I mean by that is if you take 3 times 5, that is equal to 5 times 3. And the ordering of this multiplication doesn't matter. And this is called the commutative property of multiplication of real numbers. It turns out this property that you can reverse the order in which you multiply things, this is not true for matrix multiplication. So concretely, if A and B are matrices, then in general A times B is not equal to B times A. So just be careful of that. It's not okay to arbitrarily reverse the order in which you multiply matrices. So we say that matrix multiplication is not commutative. It's a fancy way of saying it. As a concrete example, here are 2 matrices. This matrix 1100 times 0020, and if you multiply these 2 matrices, you get this result on the right. Now let's swap around the order of these 2 matrices. So I'm going to have taken these 2 matrices and just reverse them. It turns out if you multiply these 2 matrices, you get this second answer on the right. And well, clearly, right, these 2 matrices are not equal to each other. So in fact, in general, if you have a matrix operation like A times B, if A is an m by n matrix and B is an n by m matrix, just as an example, then it turns out that the matrix A times B, right, is going to be an m by m matrix, whereas the matrix B times A is going to be an n by n matrix. So the dimensions don't even match, right? So if A times B and B times A may not even be the same dimension. In the example on the left, I had all 2 by 2 matrices, so the dimensions were the same, but in general, reversing the order of the matrices can even change the dimension of the outcome. So matrix multiplication is not commutative. Here's the next property I want to talk about. So when talking about real numbers or scalars, let's say I have 3 times 5 times 2. I can either multiply 5 times 2 first, and I can compute this as 3 times 10, or I can multiply 3 times 5 first, and I can compute this as 15 times 2, and both of these give you the same answer, right? Both of these is equal to 30. So if it doesn't matter whether I multiply 5 times 2 first, or whether I multiply 3 times 5 first, because well, 5 times 2 is equal to 3 times 5 times 2. And this is called the associative property of row number multiplication. It turns out that matrix multiplication is associative. So concretely, let's say I have a product of 3 matrices, A times B times C. Then I can compute this either as A times B times C, or I can compute this as A times B times C, and these will actually give me the same answer. I'm not going to prove this, but you can just take my word for it, I guess. So just to be clear what I mean by these two cases, let's look at the first one, right? This first case. What I mean by that is if you actually want to compute A times B times C, what you can do is you can first compute B times C, so that D equals B times C, then compute A times D. And so this is really computing A times B times C. Or for this second case, you can compute this as you can set E equals A times B, then compute E times C, and this is then the same as A times B times C, and it turns out that both of these options will give you, is guaranteed to give you the same answer. And so we say that matrix multiplication does enjoy the associative property. Okay? And don't worry about the terminology associative and commutative. That's what it's called, but I'm not really going to use this terminology later in this class, so don't worry about memorizing those terms. Finally, I want to tell you about the identity matrix, which is a special matrix. So let's again make the analogy to what we know of real numbers. So when dealing with real numbers or with scalar numbers, the number 1 is, you can think of it as the identity of multiplication. And what I mean by that is that for any number z, the number 1 times z is equal to z times 1, and that's just equal to the number z, right, for any real number z. So 1 is the identity operation, and sort of satisfies this equation. So it turns out that in the space of matrices, there's an identity matrix as well, and is usually denoted I, or sometimes we write it as I of n by n. We want to make explicit the dimension. So I subscript n by n is the n by n identity matrix. And so there's a different identity matrix for each dimension n. And here are a few examples. Here's the 2 by 2 identity matrix. Here's the 3 by 3 identity matrix. Here's the 4 by 4 identity matrix. So the identity matrix has the property that it has 1s along the diagonals, right, and so on, and 0 everywhere else. And so, by the way, the 1 by 1 identity matrix, is just the number 1. It's the 1 by 1 matrix with just 1 in it. So it's not a very interesting identity matrix. And informally, when I or others are being sloppy, very often we'll write the identity matrix using the following notation. Like draw, square brackets, just write 1, 1, 1, dot, 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 1, and then we'll maybe somewhat sloppily write a bunch of zeros there, and these zeros on this big 0 and this big 0, that's meant to denote that this matrix is 0 everywhere except for the diagonal. So this is just how I might sloppily write the identity matrix. And it turns out that the identity matrix has this property that for any matrix A times identity equals I times A equals A. So that's a lot like this equation that we had up here, right? So 1 times z equals z times 1 equals z itself. So I times A equals A times I equals A. Just to make sure we have the dimensions right. So if A is an m by n matrix, then this identity matrix here, that's an n by n identity matrix. And if A is n by n, then this identity matrix, right, for matrix multiplication to make sense, that has to be an m by m matrix, because this m has to match up that m. And in either case, the outcome of this process is you get back the matrix A, which is m by n. So whenever we write the identity matrix I, very often the dimension, right, will be implicit from the context. So these two i's, they're actually different dimension matrices. One may be n by n, the other is n by m. But when we want to make the dimension of the matrix explicit, then sometimes we'll write it as I subscript n by n, kind of like we had up here. But very often the dimension will be implicit. Finally, I just want to point out that earlier I said that A times B is not, in general, equal to B times A, right? That, that for most matrices A and B, this is not true. But when B is the identity matrix, this does hold true. That A times the identity matrix does indeed equal to identity times A. It's just that, this is not true for other matrices B in general. So that's it for the properties of matrix multiplication and special matrices like the identity matrix I want to tell you about. In the next and final video on our linear algebra review, I'm going to quickly tell you about a couple of special matrix operations, and after that you need everything you need to know about linear algebra for this class. In this video, I'm going to tell you about a couple special matrix operations called the matrix inverse and the matrix transpose operation. Let's start by talking about matrix inverse. And as usual, we'll start by thinking about how it relates to real numbers. In the last video, I said that the number 1 plays the role of sort of the identity, right, in the space of real numbers because 1 times anything is equal to itself. It turns out that real numbers have this property that every number have, and that each number has an inverse. For example, given the number 3, there exists some number, which happens to be 3 inverse, so that that number times 3 gives you back the identity element 1. Right? And so, 3 inverse, of course, this is just 1/3, right? And given some other number, maybe 12, there's some number which is the inverse of 12, written as 12 to the minus 1, or really this is just 1/12. So that when you multiply these two things together, right, the product is equal to the identity element 1 again. Now, it turns out that in the space of real numbers, not everything has an inverse. For example, the number 0 does not have an inverse, right? Because sort of 0 inverse, so 1 over 0, that's undefined, right? Because 1 over 0 is not well defined. And what we want to do in the rest of the slide is figure out what does it mean to compute the inverse of a matrix. Here's the idea. If A is an m by m matrix, and if it has an inverse, I'll say a little bit more about that later, then the inverse is going to be written a to the minus 1, and a times its inverse, a to the minus 1, is going to equal to a inverse times a, is going to give us back the identity matrix. Okay? Only matrices that are m by m for some value of m have an inverse. So a matrix that is m by m, this is also called a square matrix. And it's called square because the number of rows is equal to the number of columns. Right? And it turns out only square matrices have inverses. So if A is a square matrix, so it's m by m, and if it is inverse, then it satisfies this equation over here. Let's look at a concrete example. So let's say I have a matrix 3, 4, 2, 16. So this is a 2 by 2 matrix. So it's a square matrix, and so this matrix could have an inverse. And it turns out that I happen to know the inverse of this matrix is 0.4 minus 0.1 minus 0.05, 0.075. And if I take this matrix and multiply these together, it turns out what I get is the 2 by 2 identity matrix, I. I can write this as I 2 by 2. Okay? And so on this slide, this matrix is the matrix A, and this matrix is the matrix A inverse. And it turns out that here I've computed A times A inverse. It turns out if you compute A inverse times A, you also get back the identity matrix. So how did I find this inverse? How did I come up with this inverse over here? It turns out that sometimes you can compute inverses by hand, but almost no one does that these days. And it turns out there's very good numerical software for taking a matrix and computing its inverse. So again, this is one of those things where there are lots of open source libraries that you can link to from any of the popular programming languages to compute inverses of matrices. Let me show you a quick example how I actually computed this inverse. And what I did was I used software called Octave. So let me bring that up. We'll see a lot more about Octave later. But let me just quickly show you an example. I'm going to set my matrix A to be equal to that matrix on the left. So I'm going to type 3, 4, 2, 16. So that's my matrix A, right? It's this matrix 3, 4, 2, 16 that I have down here on the left. And the software lets me compute the inverse of A very easily. When you type P inv of A equals this. And so this is, right, this matrix here, 0.4 minus 0.1, and so on. This is giving me a numerical solution to what is the inverse of A. So actually, let me just write inverse of A equals P inv of A. So I've set inverse of A equal to that. I can now just verify that A times A inverse the identities. And type A times inverse of A, and the result of that is this matrix. And this is 1, 1 on the diagonal, and you know, essentially what, 10 to the minus 17, 10 to the minus 16. So up to numerical precision, up to a little bit of round-off error that my computer had in multiplying these two matrices. So up to little numerical round-off, these numbers off the diagonals are essentially 0. And so A times the inverse is essentially the identity matrix. And you can also verify inverse of A times A is also equal to the identity with one set of diagonals and, you know, values that are essentially 0 except for a little bit of round-off error on the off diagonals. In my definition of the inverse of a matrix, I had this caveat, right? First, A must always be a square matrix, but I had this caveat of if A has an inverse. Exactly what matrices have an inverse is beyond the scope of this linear algebra review, but one intuition you might take away is that just as this number 0 doesn't have an inverse, it turns out that if A is, say, the matrix of all zeros, then this matrix A also does not have an inverse because, you know, there's no matrix, or there's no A inverse matrix, so that this matrix times some other matrix would give you the identity matrix of this matrix of all zeros. And there are a few other matrices with properties similar to this that also don't have an inverse. But it turns out that in this review, I don't want to go too deeply into what it means for a matrix to have an inverse, but it turns out that for our machine learning applications, this shouldn't be an issue. Or more precisely, for the learning algorithms where this may be an issue, namely whether or not an inverse appears, I'll tell you when we get to those learning algorithms just what it means for an algorithm to have or not have an inverse and how to fix it in case we end up working with matrices that don't have inverses. But the intuition, if you want, is that you can think of matrices as not having an inverse if it's somehow too close to 0 in some sense. And to give just to wrap up the terminology, matrices that don't have an inverse are sometimes called a singular matrix or degenerate matrix. And so, you know, this matrix over here is an example. The 0, 0, 0 matrix is an example of a matrix that's singular or a matrix that's degenerate. Finally, the last special matrix operation I want to tell you about is the matrix transpose. So suppose I have matrix A. If I compute the transpose of A, that's what I get here on the right. This is A transpose, which is written A superscript T. And the way you compute the transpose of a matrix is as follows. To get a transpose, I'm going to first take the first row of A, 1 to 0. That becomes this first column of the transpose. And then I'm going to take the second row of A, 3, 5, 9, and that becomes the second column of the matrix A transpose. And another way of thinking about how to compute the transpose is as if you're taking this sort of 45-degree, you know, axis and you're mirroring or you're flipping the matrix along that 45-degree axis. Okay? So here's the more formal definition of a matrix transpose. Let's say A is an M by N matrix, and let's let B equal A transpose. So let me say B equals A transpose like so. Then B is going to be an N by M matrix with the dimensions reversed. So here we had a 2 by 3 matrix, and so the transpose becomes a 3 by 2 matrix. And moreover, Bij is equal to Aj. So the Ij element of this matrix B is going to be the Ji element of that earlier matrix A. So for example, B12 is going to be equal to, look at this matrix B, B12 is going to be equal to this element 3, right? First row, second column. And that's equal to this, which is A21, second row, first column, right? And, well, which is equal to 2. And as another example, B32, right? That's B32 is this element 9, and that's equal to A23, which is this element up here, 9. And so that wraps up the definition of what it means to take the transpose of a matrix, and in fact that concludes our linear algebra review. So by now, hopefully you know how to add and subtract matrices as well as multiply them, and you also know how what are the definitions of the inverses and transposes of a matrix. And these are the main operations you need in linear algebra for this course. In case this is the first time you're seeing this material, I know this was a lot of linear algebra material, all presented very quickly, and this is a lot to absorb. But but there's no need to memorize all the definitions we just went through. And if you download a copy of either these slides or of the lecture notes from the website, from the course website, and use either the slides or the lecture notes as a reference, then you can always refer back to the definitions to figure out, what are these multiplication, transpose, and so on definitions. And the lecture notes on the course website also has pointers to additional resources on linear algebra, which you can use to learn more about linear algebra by yourself. And next, with these new tools, we'll be able, in the next few videos, to develop more powerful forms of linear regression that can deal with a lot more data, a lot more features, and a lot more training examples. And later on, after linear regression, we'll actually continue using these linear algebra tools to derive more powerful learning algorithms as well. In this video, we will start to talk about a new version of linear regression that's more powerful, one that works with multiple variables or with multiple features. Here's what I mean. In the original version of linear regression that we developed, we had a single feature x, the size of the house, and we wanted to use that to predict y, the price of the house, and this was our form of our hypothesis. But now imagine what if we had not only the size of the house as a feature or as a variable with which to try to predict the price, but that we also knew the number of bedrooms, the number of houses, and the age of the home in years. It seems like this would give us a lot more information with which to predict the price. To introduce a little bit of notation, and we sort of started to talk about this earlier, I'm going to use the variables x subscript 1, x subscript 2, and so on to denote my, in this case, 4 features, and I'm going to continue to use y to denote the variable, the output variable price that we're trying to predict. Let's introduce a little bit more notation. Now that we have 4 features, I'm going to use lowercase n to denote the number of features. So in this example, we have n equals 4 because we have 1, 2, 3, 4 features, and n is different from our earlier notation where we were using m to denote the number of examples. So if you have 47 rows, m is the number of rows in this table or the number of training examples. So I'm also going to use x superscript I to denote the input features of the ith training example. As a concrete example, let's say x2 is going to be a vector of the features for my second training example, and so x2 here is going to be a vector 1, 4, 1, 6, 3, 2, 40, since those are my 4 features that I have to try to predict the price of the second house. So in this notation, the superscript, the superscript 2 here, that's an index into my training set, right? This is not x to the power of 2. Instead, this is, an index that says, look at the second row of this table. This refers to my second training example. With this notation, x2 is a 4-dimensional vector. In fact, more generally, this is an n-dimensional feature vector. With this notation, x2 is now a vector, and so I'm going to use also xi subscript j to denote the value of the j of feature number j in the ith training example. So concretely, x2 subscript 3, let's say, will refer to feature number 3 in this vector, which is equal to 2. right? That was a 3 over there, just to fix my handwriting. So x2 subscript 3 is going to be equal to 2. Now that we have multiple features, let's talk about what the form of our hypothesis should be. Previously, this was the form of our hypothesis where x was our single feature. But now that we have multiple features, we aren't going to use this simple representation anymore. Instead, our form of the hypothesis in linear regression is going to be this. It's going to be theta 0 plus theta 1 x1 plus theta 2 x2 plus theta 3 x3 plus theta 4 x4. And if we have n features, then rather than summing up over our 4 features, we would have a sum over our n features. Concretely, for a particular setting of our parameters, we may have h of x equals 80 plus 0.1 x1 plus 0.01 x2 plus 3x3 minus 2 x4. This would be one example of a hypothesis. And remember, a hypothesis is trying to predict the price of the house in thousands of dollars. This is saying that, you know, the base price of a house is maybe 80,000 plus another 0.1. So that's an extra, what, $100 per square feet. Yeah, plus the price goes up a little bit for each additional floor that the house has. So x2 was number of floors. And it goes up further for each additional bedroom the house has, because x3 was the number of bedrooms, and the price goes down a little bit with each additional age of the house, with each additional year of the age of the house. Here's the form of our hypothesis rewritten on this slide, and what I'm going to do is introduce a little bit of notation to simplify this equation. For convenience of notation, let me define x subscript 0 to be equal to 1. Concretely, this means that for every example I have a feature vector x superscript I, and x superscript I subscript 0 is going to be equal to 1. You can think of this as defining an additional 0 feature. So whereas previously I had n features, features x1, x2 through xn, I'm now defining an additional sort of 0 feature vector that always takes on the value of 1. So now my feature vector x becomes this n plus 1 dimensional vector that is 0 indexed. So this is now a n plus 1 dimensional feature vector, but I'm going to index it from 0. And I'm also going to think of my parameters as a vector. So my parameters here, right, that would be this theta 0, theta 1, theta 2, and so on up to theta n. I'm going to gather them up into a parameter vector written theta 0, theta 1, theta 2, and so on, down to theta n. This is another 0 index vector, so if index starting from 0, that is another n plus 1 dimensional vector. So my hypothesis can now be written theta 0 x0 plus theta 1 x1 plus dot 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 up to theta n xn. And this equation is the same as this one on top because, you know, x0 is equal to 1. And the neat thing is I can now take this form of the hypothesis and write this as theta transpose x. Depending on how familiar you are with inner products of vectors, if you write out what theta transpose x is, what theta transpose x is this theta 0, theta 1 up to theta n. So this thing here is theta transpose, and this is actually a n plus 1 by 1 matrix. It's also called a row vector. And we take that and multiply it with the vector x, which is x0, x1, and so on down to xn. And so the inner product, that is theta transpose x, is just equal to this. This gives us a convenient way to write the form of the hypothesis as just the inner product between our parameter vector theta and our feature vector x, and it is this little bit of notation, this little extra bit of notational convention that let us write this in this compact form. So that's the form of our hypothesis when we have multiple features. And just to give this another name, this is also called multivariate linear regression. And the term multivariate is just maybe a fancy term for saying that we have multiple features or multiple variables with which to try to predict the value y. In the previous video, we talked about the form of the hypothesis for linear regression with multiple features, with multiple variables. In this video, let's talk about how to fit the parameters of that hypothesis. In particular, let's talk about how to use gradient descent for linear regression with multiple features. To quickly summarize our notation, this is a form of hypothesis in multivariate linear regression where we'd adopted the convention that x0 equals 1. The parameters of this model are theta 0 through theta n, but instead of thinking of this as n separate parameters, which is valid, I'm instead going to think of the parameters as theta, where theta here is a n plus 1 dimensional vector. So I'm just going to think of the parameters of this model as itself being a vector. Our cost function is j of theta 0 through theta n, which is given by this usual sum squared error term. But again, instead of thinking of j as a function of these n plus 1 numbers, I'm going to more commonly write j as just a function of the parameter vector theta, so that theta here is a vector. Here's what gradient descent looks like. We're going to repeatedly update each parameter theta j according to theta j minus alpha times this derivative term. And once again, let me just write this as j of theta. So theta j is updated as theta j minus the learning rate alpha times the derivative or partial derivative of the cost function with respect to the parameter theta j. Let's see what this looks like when we implement gradient descent, and in particular, let's go see what that partial derivative term looks like. Here's what we have for gradient descent for the case of when we had n equals 1 feature. We had two separate update rules for the parameters theta 0 and theta 1, and hopefully these look familiar to you. And this term here was, of course, the partial derivative of the cost function with respect to the parameter theta 0. And similarly, we had a different update rule for the parameter theta 1. There's one little difference, which was that when we previously had only one feature, we would call that feature xi, but now in our new notation, we would of course call this x superscript I subscript 1 to denote our one feature. So that was for when we had only one feature. Let's look at the new algorithm for we have more than one feature, when the number of features n may be much larger than 1. We get this update rule for gradient descent. And maybe for those of you that know calculus, if you take the definition of the cost function and take the partial derivative of the cost function j with respect to the parameter theta j, you find that that partial derivative is exactly that term that I've just drawn the blue box around. And if you implement this, you will get a working implementation of gradient descent for multivariate linear regression. The last thing I want to do on this slide is give you a sense of why these new and old algorithms are, sort of the same thing, or why they're both similar algorithms, or why they're both gradient descent algorithms. Let's consider a case where we have two features, or maybe more than two features. So we have three update rules for the parameters theta 0, theta 1, theta 2, and maybe other values of theta as well. If you look at the update rule for theta 0, what you find is that this update rule here is the same as the update rule that we had previously for the case of n equals 1. And the reason that they're equivalent is, of course, because in our notational convention, we had this x0 equals 1 convention, which is why these two terms that I've drawn the magenta boxes around are equivalent. Similarly, if you look at the update rule for theta 1, you find that this term here is equivalent to the term we previously had, or the equation, the update rule we previously had for theta 1, where of course we're just using this new notation, x subscript 1, to denote our new notation for denoting the first feature. And now that we have more than one feature, we can have similar update rules for the other parameters like theta 2 and so on. There's a lot going on the slides, so so I definitely encourage you, if you need to pause the video and look at all the math on the slide slowly to make sure you understand everything that's going on here. But if you implement the algorithm written up here, then you will have a working implementation of linear regression with multiple features. In this video and in the video after this one, I want to tell you about some of the practical tricks for making gradient descent work well. In this video, I want to tell you about an idea called feature scaling. Here's the idea. If you have a problem where you have multiple features, if you make sure that the features are on a similar scale, by which I mean make sure that the different features take on similar ranges of values, then gradient descent can converge more quickly. Concretely, let's say you have a problem with two features where x1 is the size of a house and takes on values between, say, 0 to 2000, and x2 is the number of bedrooms, and maybe that takes on values between 1 and 5. If you plot the contours of the cost function j of theta, then the contours may look like this, where, let's see, j of theta is a function of parameters theta 0, theta 1, and theta 2. I'm going to ignore theta 0, so let's forget about theta 0 and pretend it's a function of only theta 1 and theta 2. But if x1 can take on a much larger range of values than x2, it turns out that the contours of the cost function j of theta can take on this sort of a very, very skewed elliptical shape. Except that with a sort of 2000 to 5 ratio, it can be even more skewed. So this very, very tall and skinny ellipses, or these very tall, skinny ovals, can form the contours of the cost function j of theta. And if you run gradient descent on this sort of cost function, your gradients may end up taking a long time and can sort of oscillate back and forth, and it can take a long time before it can finally find its way to the global minimum. In fact, you can imagine if these contours were exaggerated even more, if we were to draw incredibly skinny, tall, skinny contours, and it can be even more extreme than that, then gradient descent can just, well, it turns out gradient descent will just have a much harder time taking its way, meandering around. It can take a long time to find its way to the global minimum. In these settings, a useful thing to do is to scale the features. Concretely, if you instead define the feature x1 to be the size of the house divided by 2000, and define x2 to be maybe the number of bedrooms divided by 5, then the contours of the cost function j can become much less skewed, so that the contours may look more like circles. And if you run gradient descent on a cost function like this, then gradient descent, you can show mathematically, can find a much more direct path to the global minimum rather than taking a much more convoluted path where it's sort of trying to follow a much more complicated trajectory to get to the global minimum. So by scaling the features so that they take on similar ranges of values, in this example we end up with both features x1 and x2 between 0 and 1. You can wind up with an implementation of gradient descent that can converge much faster. More generally, when we're performing feature scaling, what we often want to do is get every feature into approximately a -1 to +1 range. And concretely, your feature x0, that's always equal to 1, so that's already in that range. But you may end up dividing other features by different numbers to get them into this range. And the numbers -1 and +1 aren't too important. So if you have a feature x1 that winds up being between 0 and 3, say, that's not a problem. Or if you end up having a different feature that winds up being between -2 and positive 0.5, again, this is close enough to -1 and +1 that that's fine. I think that's fine. It's only if you have a different feature, say x3, that is between, say, that ranges from -100 to +100, then this is a very different range of values than -1 and +1. So this might be a less well-scaled feature. And similarly, if your features take on a very, very small range of values, so if x4 takes on values between -0.0001 and positive 0.0001, then again, this takes on a much smaller range of values than the -1 to +1 range. And again, I would consider this feature poorly scaled. So you want the range of values, it can be a bit bigger than +1, a bit smaller than +1, but just not much bigger like +100 here, and not too much smaller like 0.001 over there. Different people have different rules of thumb, but the one that I use is that if a feature takes on a range of values from, say, -3 to +3, I usually think that should be just fine. But maybe if it takes on much larger values than +3 or -3, I might start to worry. And if it takes on values from, say, -1/3 to 1/3, I think that's fine too. Or 0 to 1/3, or -1/3 to 0. Or just that's typical range of values I consider okay. But if it takes on a much tinier range of values like x4 here, then again I might start to worry. So the take-home message is don't worry if your features are not exactly on the same scale or exactly in the same range of values, but so long as they're all close enough to this, gradient descent should work okay. In addition to dividing by sort of the maximum value, when performing feature scaling, sometimes people will also do what's called mean normalization. And what I mean by that is that you might take a feature xi and replace it with xi minus mu I to make your features have approximately 0 mean. And obviously we won't apply this to the feature x0 because the feature x0 is always equal to 1, so it cannot have an average of value of 0. But concretely, for other features, if the range of sizes of a house takes on values between 0 to 2000, and if the average size of a house is equal to 1000, then you might use this formula, set the feature x1 to be the size minus the average value divided by 2000. And similarly, if on average, if your houses have 1 to 5 bedrooms, and if on average a house has, say, 2 bedrooms, then you might use this formula to mean normalize your second feature x2. In both of these cases, you therefore wind up with features x1 and x2 that can take on values roughly between -0.5 and +0.5. It's actually not true. x2 can actually be slightly larger than 0.5, but close enough. And the more general rule is that you might take a feature x1 and replace it with x1 minus mu1 over s1, where to define these terms, mu1 is the average value of x1 in the training set, and s1 is the range of values of that feature. And by range I mean, let's say, the maximum value minus the minimum value. Or for those of you that know what the standard deviation of a variable is, setting s1 to be the standard deviation of the variable would be fine too, but taking this max minus min would be fine. And similarly for the second feature x2, you replace x2 with this sort of subtract the mean of the feature and divide it by the range of values, meaning the max minus min. And this sort of formula will get your features, maybe not exactly, but maybe roughly into these sorts of ranges. And by the way, for those of you that are being super careful, technically, if we're taking the range as max minus min, this 5 here would actually become a 4. So if max is 5, min is 1, then the range of bedroom values is actually equal to 4. But all of these are approximate, and any value that gets the features into anything close to these sorts of ranges will do fine. And the feature scaling doesn't have to be too exact in order to get gradient descent to run quite a lot faster. So now you know about feature scaling, and if you apply this simple trick, it can make gradient descent run much faster and converge in a lot fewer iterations. That was feature scaling. In the next video, I'll tell you about another trick to make gradient descent work well in practice. In this video, I want to give you more practical tips for getting gradient descent to work. The ideas in this video will center around the learning rate alpha. Concretely, here's the gradient descent update rule. And what I want to do in this video is tell you about what I think of as debugging and some tips for making sure that gradient descent is working correctly. And second, I want to tell you how to choose the learning rate alpha, or at least how I go about choosing it. Here's something that I often do to make sure that gradient descent is working correctly. The job of gradient descent is to find the value of theta for you that hopefully minimizes the cost function j of theta. What I often do is therefore plot the cost function j of theta as gradient descent runs. So the x-axis here is the number of iterations of gradient descent, and as gradient descent runs, you hopefully get a plot that maybe looks like this. Notice that the x-axis is number of iterations. Previously, we were looking at plots of j of theta where the x-axis, where the horizontal axis, was the parameter vector theta. But this is not what this is. Concretely, what this point is I'm going to run gradient descent for 100 iterations, and whatever value I get for theta after 100 iterations, I'm going to get some value theta after 100 iterations, and I'm going to evaluate the cost function j of theta for the value of theta I get after 100 iterations, and this vertical height is the value of j of theta for the value of theta I got after 100 iterations of gradient descent. And this point here, that corresponds to the value of j of theta for the theta that I get after I've run gradient descent for 200 iterations. So what this plot is showing is it's showing the value of your cost function after each iteration of gradient descent, and if gradient descent is working properly, then j of theta should decrease after every iteration. And one useful thing that this sort of plot can tell you also is that if you look at the specific figure that I've drawn, it looks like by the time you've gotten out to maybe 300 iterations, between 300 and 400 iterations in this segment, it looks like j of theta hasn't gone down much more. So by the time you get to 400 iterations, it looks like this curve has flattened out here. And so way out here at 400 iterations, it looks like gradient descent has more or less converged because your cost function isn't going down much more. So looking at this figure can also help you judge whether or not gradient descent has converged. By the way, the number of iterations that gradient descent takes to converge for a particular application can vary a lot. So maybe for one application, gradient descent may converge after just 30 iterations. For a different application, gradient descent may take 3,000 iterations. For another algorithm, for another learning algorithm, it may take 3 million iterations. It turns out to be very difficult to tell in advance how many iterations gradient descent needs to converge, and is usually by plotting this sort of plot, plotting the cost function as we increase the number of iterations, is usually by looking at these plots that I try to tell if gradient descent has converged. It's also possible to come up with automatic convergence tests, namely to have an algorithm try to tell you if gradient descent has converged. And here's maybe a pretty typical example of an automatic convergence test. And such a test may declare convergence if your cost function j of theta decreases by less than some small value epsilon, some small value 10 to the minus 3 in one iteration. But I find that usually choosing what this threshold is pretty difficult, and so in order to check if gradient descent is converged, I actually tend to look at plots like these, like this figure on the left, rather than rely on an automatic convergence test. Looking at this sort of figure can also tell you or give you an advance warning if maybe gradient descent is not working correctly. Concretely, if you plot j of theta as a function of the number of iterations, then, if you see a figure like this where j of theta is actually increasing, then that gives you a clear sign that gradient descent is not working. And a figure like this usually means that you should be using a learning rate alpha. If j of theta is actually increasing, the most common cause for that is if you're maybe trying to minimize a function that maybe looks like this. But if your learning rate is too big, then if you start off there, gradient descent may overshoot the minimum and send you there. And if the learning rate is too big, you may overshoot again and then send you there, and so on. So that, what you really wanted was for it to start here and for it to slowly go downhill, right? But if the learning rate is too big, then gradient descent can instead, keep on overshooting the minimum, so that you actually end up getting worse and worse, so sort of getting to higher values of the cost function j of theta, so that you end up with a plot like this. And if you see a plot like this, the fix usually is to just use a smaller value of alpha. Oh, and also, of course, make sure that your code does not have a bug in it. But usually, too large a value of alpha is the most common. Could be a common problem. Similarly, sometimes you may also see j of theta do something like this. It may go down for a while, then go up, then go down for a while, then go up, go down for a while, go up, and so on. And the fix for something like this is also to use a smaller value of alpha. I'm not going to prove it here, but under mild assumptions about the cost function j, which does hold true for linear regression, you can show, or mathematicians have shown, that if your learning rate alpha is small enough, then j of theta should decrease on every single iteration. So if this doesn't happen, it probably means alpha is too big and you should set it smaller. But of course, you also don't want your learning rate to be too small, because if you were to do that, then gradient descent can be slow to converge. And if alpha were too small, you might end up starting out here, say, and end up taking just minuscule baby steps, right? And just taking a lot of iterations before you finally get to the minimum. And so if alpha is too small, gradient descent can make very slow progress and be slow to converge. To summarize, if the learning rate is too small, you can have a slow convergence problem. And if the learning rate is too large, j of theta may not decrease on every iteration, and it may not even converge. In some cases, if the learning rate is too large, slow convergence is also possible. But the more common problem you see is that j of theta may not decrease on every iteration. And in order to debug all of these things, often plotting that j of theta as a function of the number of iterations can help you figure out what's going on. Concretely, what I actually do when I run gradient descent is I would try a range of values. So just try running gradient descent with a range of values for alpha, like 0.001, 0.01. So these are a factor of 10 differences. And for these different values of alpha, just plot j of theta as a function of number of iterations. And then pick the value of alpha that seems to be causing j of theta to decrease rapidly. In fact, what I do actually isn't these steps of 10. So this is a scale factor of 10 if each step up. What I actually do is try this range of values, and so on, where this is 0.01. I'll then increase the learning rate threefold to get 0.03, and then this step up, this is another roughly threefold increase from 0.03 to 0.01, and so these are roughly trying out gradient descent with each value I try being about 3x bigger than the previous value. So what I'll do is try a range of values until I've made sure that I found one value that's too small and make sure I found one value that's too large, and then I sort of try to pick the largest possible value or just something slightly smaller than the largest reasonable value that I found. And when I do that, usually this gives me a good learning rate for my problem. And if you do this too, hopefully you'll be able to choose a good learning rate for your implementation of gradient descent. You now know about linear regression with multiple variables. In this video, I want to tell you a bit about the choice of features that you have and how you can get different learning algorithms, sometimes very powerful ones, by choosing appropriate features. And in particular, I also want to tell you about polynomial regression, which allows you to use the machinery of linear regression to fit very complicated, even very nonlinear functions. Let's take the example of predicting the price of a house. Suppose you have two features, the frontage of the house and the depth of the house. So here's a picture of the house we're trying to sell. The frontage is defined as this distance. It's basically the width or the length of how wide your lot is, of this plot of land that you own. And the depth of the house is how deep your property is. So there's a frontage, that's the depth. So you have two features called frontage and depth. You might build a linear regression model like this, where frontage is your first feature x1 and depth is your second feature x2. But when you're applying linear regression, you don't necessarily have to use just the features x1 and x2 that you're given. What you can do is actually create new features by yourself. So if I want to predict the price of a house, what I might do instead is decide that what really determines the size of a house is the area, really the land area that I own. So I might create a new feature, I'm just call this feature x, which is frontage times depth. This is a multiplication symbol, right? So frontage times depth, because this is the land area that I own, and I might then select my hypothesis as that, using just one feature, which is my land area, right? Because the area of a rectangle is, the product of the length of the size. So depending on what insight you might have into a particular problem, rather than just taking the features frontage and depth that we happen to have started off with, sometimes by defining new features, you might actually get a better model. Closely related to the idea of choosing your features is this idea called polynomial regression. Let's say you have a housing price data set that looks like this. Then there are a few different models you might fit to this. One thing you could do is fit a quadratic model like this. It doesn't look like a straight line fits this data very well. So maybe you want to fit a quadratic model like this, where you think the price is a quadratic function, and maybe that will give you, a fit to the data that looks like that. But then you might decide that quadratic model doesn't make sense because with a quadratic function, eventually this function comes back down, and well, we don't think housing prices should go down when the size goes up too high. So then maybe we might choose a different polynomial model and choose to use instead a cubic function, and where we have now a third order term, and if we fit that, maybe we would get this sort of model. And maybe the green line is a somewhat better fit to the data because it doesn't eventually come back down. So how do we actually fit a model like this to our data? Using the machinery of multivariate linear regression, we can do this with a pretty simple modification to our algorithm. The form of the hypothesis we know how to fit looks like this, where we say that h of x is theta 0 plus theta 1 x1 plus theta 2 x2 plus theta 3 x3. And if we want to fit this cubic model that I have boxed in green, what we're saying is that the predicted price of a house is theta 0 plus theta 1 times the size of the house, plus theta 2 times the square size of the house, so this term is equal to that term, and then plus theta 3 times the cube of the size of the house, right? So it's that third term. In order to map these two definitions to each other, well, the natural way to do that is to set the first feature x1 to be the size of the house, and set the second feature x2 to be the square of the size of the house, and set the third feature x3 to be the cube of the size of the house. And just by choosing my three features this way and applying the machinery of linear regression, I can fit this model and end up with a cubic fit to my data. I just want to point out one more thing, which is that if you choose your features like this, then feature scaling becomes increasingly important. So if the size of a house ranges from 1 to 1,000, so from 1 to 1,000 square feet, say, then the size squared of the house will range from 1 to 1 million. That's the square of 1,000. And your third feature x cubed, your third feature x3, which is the size cubed of the house, will range from 1 to 10 to the 9. And so these three features take on very different ranges of values, and it's important to apply feature scaling if you're using gradient descent to get them into comparable ranges of values. Finally, here's one last example of how you really have broad choices in the features you use. Earlier we talked about how a quadratic model like this might not be ideal because maybe a quadratic model fits the data okay, but the quadratic function goes back down, and we really don't want housing prices that go down to predict that as the size of the house increases. But rather than going to a cubic model, you have maybe other choices of features, and there are many possible choices. But just to give you another example of a reasonable choice, another reasonable choice might be to say that the price of a house is theta 0 plus theta 1 times the size, and then plus theta 2 times the square root of the size, right? So the square root function is this sort of function, and maybe there will be some value of theta 1, theta 2, theta 3 that will let you take this model and fit a curve that looks like that, and goes up but doesn't, but sort of flattens out a bit and doesn't ever come back down. And so by having insight into, in this case, the shape of the square root function and into the shape of the data by choosing different features, you can sometimes get better models. In this video, we talked about polynomial regression, that is, how to fit a polynomial like a quadratic function or a cubic function to your data. And we talked about this idea that you have a choice in what features to use, such as that instead of using the frontage and the depth of a house, maybe you can multiply them together to get a feature that captures the land area of a house. In case this seems a little bit bewildering, that, wow, we have all these different feature choices, so how do I decide what features to use? Later in this class, we'll talk about some algorithms for automatically choosing what features to use, so that you can have an algorithm look at the data and automatically choose for you whether you want to fit a quadratic function or a cubic function or something else. But until we get to those algorithms, for now, I just want you to be aware that you have a choice in what features to use. And by designing different features, you can fit more complex functions to your data than just fitting a straight line to the data. And in particular, you can fit polynomial functions as well. And sometimes by appropriate insights into the features, you can get a much better model for your data. In this video, we'll talk about the normal equation, which for some linear regression problems will give us a much better way to solve for the optimal value of the parameters theta. Concretely, so far, the algorithm that we've been using for linear regression is gradient descent, where in order to minimize the cost function j of theta, we would take this iterative algorithm that takes many steps, so multiple iterations of gradient descent, to converge to the global minimum. In contrast, the normal equation will give us a method to solve for theta analytically, so that rather than needing to run this iterative algorithm, we can instead just solve for the optimal value for theta all in one go, so that in basically one step, you get to the optimal value right there. It turns out the normal equation method has some advantages and some disadvantages, but before we get to that and talk about when you should use it, let's get some intuition about what this method does. For this explanatory example, let's take a very simplified cost function j of theta that's just a function of a row number theta. So for now, imagine that theta is just a scalar value, or that theta is just a row value. It's just a number rather than a vector. Imagine that we have a cost function j that's a quadratic function of this row-valued parameter theta. So j of theta looks like that. Well, how do you minimize a quadratic function? For those of you that know a little bit of calculus, you may know that the way to minimize a function is to take derivatives and to set derivatives equal to 0. So if you take the derivative of j with respect to the parameter theta, you get some formula, which I'm not going to derive, and then you set that derivative equal to 0, and this allows you to solve for the value of theta that minimizes j of theta. That was the simpler case of when theta is just a row number. In the problem that we're interested in, theta is no longer just a row number, but instead is this n+1 dimensional parameter vector. And our cost function j is a function of this vector value of theta 0 through theta m, and the cost function looks like this sum squared cost function on the right. How do we minimize this cost function j? Calculus actually tells us that one way to do so is to take the partial derivative of j with respect to every parameter theta j in turn, and then to set all of these to 0. If you do that and you solve for the values of theta 0, theta 1 up to theta n, then this will give you the values of theta that minimize the cost function j. Well, if you actually work through the calculus and work through the solution to the parameters theta 0 through theta n, the derivation ends up being somewhat involved. And what I'm going to do in this video is actually to not go through the derivation, which is kind of long and kind of involved. But what I want to do is just tell you what you need to know in order to implement this process, so that you can solve for the values of the thetas that corresponds to where the partial derivative is equal to 0, or alternatively, or equivalently, the values of thetas that minimize the cost function j of theta. And I realize some of the comments I may have made more sense only to those of you that are a little more familiar with calculus. So, but if you don't know, if you're less familiar with calculus, don't worry about it. I'm just going to tell you what you need to know in order to implement this algorithm and get it to work. For the example that I want to use as a running example, let's say that I have m equals 4 training examples. In order to implement this normal equation method, what I'm going to do is the following. I'm going to take my data set. So here are my 4 training examples. In this case, let's assume that these 4 examples is all the data I have. Okay. What I'm going to do is take my data set and add an extra column that corresponds to my extra feature x0 that's always takes on this value of 1. What I'm going to do is I'm then going to construct a matrix called capital X. That's a matrix that basically contains all of the features for my training data. So concretely, here are all my features. I'm going to take all those numbers and put them into this matrix X. Okay, so just copy the data over one column at a time. And then I'm going to do something similar for y. So I'm going to take the values I'm trying to predict and construct now a vector like so, and call that a vector y. So x is going to be a m by n plus 1 dimensional matrix, and y is going to be a m dimensional vector, where m is the number of training examples and n is the number of features, and I have n plus 1 because of this extra feature x0 that I added. Finally, if you take your matrix X and you take your vector Y, and if you just compute this and set theta to be equal to x transpose x inverse times x transpose y, this will give you the value of theta that minimizes your cost function. There was a lot that happened on this slide, and I worked through it using one specific example of one data set. Let me just write this out in a slightly more general form, and then later on in this video, let me explain this equation a little bit more in case it's not yet entirely clear how to do this. In the general case, let's say we have m training examples, so x1, y1 up to xm, ym, and n features. So each of our training examples, xi, may look like a vector like this. There's an n plus 1 dimensional feature vector. The way I'm going to construct the matrix X, this is also called the design matrix, is as follows. Each training example gives me a feature vector like this. That's this sort of n plus 1 dimensional vector. The way I'm going to construct my design matrix X is I'm going to construct a matrix like this. And what I'm going to do is take the first training example, so that's a vector, take its transpose, so it ends up being this long flat thing, and make x1 transpose the first row of my design matrix X. Then I'm going to take my second training example, x2, take the transpose of that, and put that as the second row of X, and so on, down until my last training example, take the transpose of that, and that's my last row of my matrix X. And so this makes my matrix X an m by n plus 1 dimensional matrix. As a concrete example, let's say I have only one feature, only one feature other than x0, which is always equal to 1. So if my feature vectors xi are equal to this 1, which is x0, and then some row feature like maybe the size of the house, then my design matrix X would be equal to this. For the first row, I'm going to basically take this and take its transpose. So I'm going to end up with 1, and then x1, 1. For the second row, I'm going to end up with 1, and then x1, 2, and so on down to 1, and then x1, m. And thus, this will be a m by 2-dimensional matrix. So that's how I construct the matrix X. And the vector Y, sometimes I might write an arrow on top to denote that it's a vector, but very often I'll just write this as Y either way. The vector Y is obtained by taking all the labels, all the correct prices of houses in my training set, and just stacking them up into an m-dimensional vector, and that's Y. Finally, having constructed the matrix X and the vector Y, we then just compute theta as x transpose x inverse times x transpose y. I just want to make sure that this equation makes sense to you and that you know how to implement it. So, concretely, what is this X transpose X inverse? Well, X transpose X inverse is the inverse of the matrix X transpose X. Concretely, if you were to say set A to be equal to X transpose times X, so X transpose is a matrix, X transpose times X gives you another matrix, and we'll call that matrix A, then, X transpose X inverse is just, you take this matrix A and you invert it, right? It's equal to, let's say, A inverse. And so that's how you compute this thing. You compute X transpose X and then you compute its inverse. We haven't yet talked about octave. We'll do so in a later set of videos, but in the octave programming language, or similarly in also the MATLAB programming language is very similar. The command to compute this quantity, I guess really this quantity, X transpose X inverse times X transpose Y, is as follows. In octave, X prime is the notation that you use to denote X transpose. And so this expression that's boxing in red, that's computing X transpose times X. P_inv is a function for computing the inverse of a matrix. So this computes X transpose X inverse. And then you multiply that by X transpose and you multiply that by Y. So you end up computing that formula, which I didn't prove, but it is possible to show mathematically, even though I'm not going to do so here, that this formula gives you the optimal value of theta, in the sense that this, if you set theta equal to this, that's the value of theta that minimizes the cost function j of theta for linear regression. One last detail. In an earlier video, I talked about feature scaling and the idea of getting features to be on similar ranges of scales or similar ranges of values of each other. If you're using this normal equation method, then feature scaling isn't actually necessary and is actually okay if, say, some feature x1 is between 0 and 1, and some feature x2 is between, ranges from 0 to 1000, and some feature x3 ranges from 0 to 10 to the minus 5. And if you're using the normal equation method, this is okay, and there's no need to do feature scaling. Although, of course, if you were using gradient descent, then feature scaling is still important. Finally, when should you use gradient descent and when should you use the normal equation method? Here are some of their advantages and disadvantages. Let's say you have m training examples and n features. One disadvantage of gradient descent is that you need to choose the learning rate alpha, and often this means running it a few times with different learning rate alphas and then seeing what works best. And so that's a lot of extra work and extra hassle. Another disadvantage of gradient descent is that it needs many iterations, and so depending on the details, that could make it slower, although there's more to the story, as we'll see in a second. As for the normal equation, you don't need to choose any learning rate alpha, so that makes it really convenient, makes it simpler to implement, and you just run it, and it usually just works. And you don't need to iterate, so you don't need to plot j of theta, check for convergence, and take all those extra steps. So far, the balance seems to favor the normal equation. Here are some disadvantages of the normal equation and some advantages of gradient descent. Gradient descent works pretty well even when you have a very large number of features. So even if you have millions of features, you can run gradient descent and it'll be reasonably efficient and it'll do something reasonable. In contrast, the normal equation, in order to solve for the parameters theta, we need to solve for this term. We need to compute this term X transpose X inverse. This matrix X transpose X, that's an n by n matrix if you have n features, because if you look at the dimensions of X transpose dimensions of X, you figure out what the dimension of the product is. The matrix X transpose X is an n by n matrix, where n is the number of features. And on most computer implementations, the cost of inverting a matrix grows roughly as the cube of the dimension of the matrix. So computing this inverse costs roughly order n cubed time. Sometimes it's slightly faster than n cubed, but it's close enough for our purposes. So if n is the number of features is very large, then computing this quantity can be slow, and the normal equation method can actually be much slower. So if n is large, then I might usually use gradient descent because we don't want to pay this order n cubed time. But as n is relatively small, then the normal equation might give you a better way to solve the parameters. What does small and large mean? Well, if n is on the order of 100, then inverting a 100 by 100 matrix is no problem by modern computing standards. If n is 1,000, I would still use the normal equation method. Inverting a 1,000 by 1,000 matrix is actually really fast in a modern computer. If n is 10,000, then I might start to wonder. Inverting a 10,000 by 10,000 matrix starts to get kind of slow, and I might then start to maybe lean in the direction of gradient descent, but maybe not quite. N equals 10,000, you can sort of invert a 10,000 by 10,000 matrix. But if it gets much bigger than that, then I would probably use gradient descent. So if n equals 10 to the 6, if you have 1,000,000 features, then inverting a 1,000,000 by 1,000,000 matrix, it's going to be very expensive, and I would definitely favor gradient descent if you have that many features. So exactly how large your set of features has to be before you convert to gradient descent, I don't know. It's hard to give a strict number, but for me, it's usually around 10,000. But I might start to consider switching over to gradient descent, or maybe to some other algorithms that we'll talk about later in this class. To summarize, so long as the number of features is not too large, the normal equation gives us a great alternative method to solve for the parameters theta. Concretely, so long as the number of features is less than 1,000, I would usually just use the normal equation method rather than gradient descent. To preview some ideas that we'll talk about later in this course, as we get to the more complex learning algorithm, for example, when we talk about classification algorithms like a logistic regression algorithm, we'll see that those algorithms actually, the normal equation method actually do not work for those more sophisticated learning algorithms, and we will have to resort to gradient descent for those algorithms. So gradient descent is a very useful algorithm to know, both for linear regression when we have a large number of features, and for some of the other algorithms that we'll see in this course, because for them the normal equation method just doesn't apply, it doesn't work. But for the specific model of linear regression, the normal equation can give you a alternative that can be much faster than gradient descent. And so depending on the details of your algorithm, depending on the details of your problem and how many features you have, both of these algorithms are well worth knowing about. In this video, I want to talk about the normal equation and non-invertibility. This is a somewhat more advanced concept, but it's something that I've often been asked about, and so I want to talk about here and address it here. But this is a somewhat more advanced concept, so feel free to consider this optional material, and it's a phenomenon that you may run into that's maybe somewhat useful to understand, but even if you don't understand the normal equation and linear regression, you should really get that to work okay. Here's the issue. For those of you that are maybe somewhat more familiar with linear algebra, what some students have asked me is, when computing this theta equals x transpose x inverse x transpose y, what if the matrix x transpose x is non-invertible? So for those of you that know a bit more linear algebra, you may know that only some matrices are invertible and some matrices do not have an inverse. We call those non-invertible matrices singular or degenerate matrices. The issue or the problem of x transpose x being non-invertible should happen pretty rarely. And in Octave, if you implement this to compute theta, it turns out that this will actually do the right thing. I'm getting a little technical now, and I don't want to go into the details, but Octave has two functions for inverting matrices. One is called pinv, and the other is called inv. And the differences between these two are somewhat technical. One's called the pseudo-inverse, one's called the inverse. But you can show mathematically that so long as you use the pinv function, then this will actually compute the value of theta that you want, even if x transpose x is non-invertible. The specific details between what is the difference between pinv and what is inv, that's somewhat advanced numerical computing concepts that I don't really want to get into. But I thought in this optional video, I'll try to give you a little bit of intuition about what it means for x transpose x to be non-invertible, for those of you that know a bit more linear algebra and might be interested. I'm not going to prove this mathematically, but if x transpose x is non-invertible, there are usually two most common causes for this. The first cause is if somehow in your learning problem you have redundant features. Concretely, if you're trying to predict housing prices, and if x1 is the size of the house in feet, in square feet, and x2 is the size of the house in square meters, then 1 meter is equal to 3.28 feet, rounded to 2 decimals. And so your two features will always satisfy the constraint that x1 equals 3.28 squared times x2. And you can show, for those of you that are somewhat advanced linear algebra now, but if you're an expert in linear algebra, you can actually show that if your two features are related via a linear equation like this, then the matrix X transpose X will be non-invertible. The second thing that can cause X transpose X to be non-invertible is if you're trying to run a learning algorithm with a lot of features. Concretely, if M is less than or equal to N. For example, if you imagine that you have M equals 10 training examples, but you have N equals 100 features, then you're trying to fit a parameter vector theta, which is n plus 1 dimensional, so it's 101 dimensional. You're trying to fit 101 parameters from just 10 training examples. And this turns out to sometimes work, but to not always be a good idea, because as we'll see later, you might not have enough data if you have only 10 examples to fit 100 or 101 parameters. We'll see later in this course why this might be too little data to fit this many parameters. But commonly what we do then, if M is less than N, is to see if we can either delete some features or to use a technique called regularization, which is something that we'll talk about later in this course as well, that will kind of let you fit a lot of parameters, use a lot of features, even if you have a relatively small training set. But this regularization will be a later topic in this course. But to summarize, if ever you find that X transpose X is singular, or alternatively you find it is non-invertible, what I would recommend you do is first look at your features and see if you have redundant features like this x1, x2, being linearly dependent or being a linear function of each other like so. And if you do have redundant features, and if you just delete one of these features, you really don't need both of these features. If you just delete one of these features, that would solve your non-invertibility problem. And so I would first think through my features and check if any are redundant, and if so, then keep deleting redundant features until they're no longer redundant. And if your features are not redundant, I would check if I might have too many features, and if that's the case, I would either delete some features if I can bear to use fewer features, or else I would consider using regularization, which is this topic that we'll talk about later. So that's it for the normal equation and what it means for if the matrix X transpose X is non-invertible. But this is a problem that that hopefully you run into pretty rarely. And if you just implement it in Octave using the pin function, which is called the pseudo-inverse function. So if you use a different linear algebra library, it's called a pseudo-inverse. But that implementation should just do the right thing, even if X transpose X is non-invertible, which should happen pretty rarely anyway, so this should not be a problem for most implementations of linear regression. You now know a bunch about machine learning. In this video, I'd like to teach you a programming language, Octave, in which you'll be able to very quickly implement the learning algorithms we've seen already and the learning algorithms we'll see later in this course. In the past, I've tried to teach machine learning using a large variety of different programming languages, including C++, Java, Python, NumPy, R, and also Octave. And what I found is that students were able to learn the most productively, learn the most quickly, and prototype your algorithms most quickly using a relatively high-level language like Octave. In fact, what I often see in Silicon Valley is that even if you want to build a large-scale deployment of a learning algorithm, what people will often do is prototype in a language like Octave, which is a great prototyping language, so you can sort of get your learning algorithms working quickly. And then only if you need a very large-scale deployment of it, only then spend your time re-implementing the algorithms in C++ or Java or some other language like that. Because one of the lessons we've learned is that programmer time or developer time, that is your time, the machine learning expert's time, is incredibly valuable. And if you can get your learning algorithms to work more quickly in Octave, then overall you have a huge time savings by first developing the algorithms in Octave and then implementing in like maybe C++ or Java only after we have the ideas working. The most common prototyping languages I see people use for machine learning are Octave, MATLAB, Python, NumPy, and R. Octave is nice since it's free open source, and MATLAB works well too, but it's expensive to many people. But if you have access to a copy of MATLAB, you can also use MATLAB for this class. If you know Python NumPy or if you know R, I do see some people use it, but what I see is that people usually end up developing somewhat more slowly in these languages because the Python NumPy syntax is just slightly clunkier than the Octave syntax. And so because of that, and because we're releasing starter code in Octave, I strongly recommend that you not try to do the programming exercises in this class in NumPy or R, but that I do recommend that you instead do the programming exercises for this class in Octave instead. What I'm going to do in this video is go through a list of commands fairly quickly, and the goal is to quickly show you the range of commands and the range of things you could do in Octave. The course website will have a transcript of everything I do, and so after watching this video, you can refer to the transcript posted on the course website when you want to find a command. Concretely, what I recommend you do is first watch the tutorial videos, and after watching to the end, then install Octave on your computer. And finally, go to the course website, download the transcript of the things you see in the session, and type in whatever commands seem interesting to you into Octave, so running on your own computer, so that you can see it work for yourself. And with that, let's get started. Here's my Windows desktop, and I'm going to start up Octave. And I'm now in Octave, and there's my Octave prompt. Let me first show you the elementary operations you can do in Octave. So you type in 5 plus 6, that gives you the answer of 11. 3 minus 2, 5 times 8, 1 over 2, 2 to the power of 6 is 64. So those are the elementary math operations. You can also do logical operations. So 1 equals 2, this evaluates the false. The percent command here is means a comment. So 1 equals 2 evaluates the false, which is represented by 0. 1 not equals to 2. This is true, so that returns 1. Note that the not equal sign is this tilde equals symbol, and not bang equals, which is what some other programming languages use. Let's see, logical operations 1 and 0. Use a double ampersand sign to denote the logical and that evaluates the false. 1 or 0. This is the OR operation, and that evaluates the true. And I can XOR 1 and 0, and that evaluates the 1. This thing over on the left, this Octave 324.exe:11, this is the default Octave prompt. It shows the version of Octave and so on. If you don't want that prompt, this is somewhat cryptic command, ps quote greater than and so on, that you can use to change the prompt. And I guess this quoted string in the middle, quote greater than space, that's what I prefer my Octave prompt to look like. So if I hit enter, like so, PS1, like so, now my Octave prompt has changed to the greater than sign, which looks quite a bit better. Next, let's talk about Octave variables. I can take the variable a and assign it to 3 and hit enter, and now a is equal to 3. If you want to assign a variable but you don't want it to print out the result, if you put a semicolon, the semicolon suppresses the print output. So if I do that, enter, it doesn't print anything, whereas a equals 3 makes it print it out, whereas a equals 3 semicolon doesn't print anything. I can do string assignment, b equals high. Now, if I just enter b, it prints out the variable b. So b is the string high. C equals 3 greater than or equal to 1. So now C evaluates to true. If you want to print out or display a variable, here's how you go about it. Let me set a equals pi. And if I want to print a, I can just type a like so, and I'll print it out. For more complex printing, there's also the disp command, which stands for display. So when I display a, it just prints out a like so. You can also display strings. So disp sprintf, 2 decimals, and %0.2 f, comma a, like so. and this will print out the string 2 decimals colon 3.14. This is kind of a old style C syntax. For those of you that have programmed C before, this is essentially the syntax you use to print strings. So the sprintf generates a string that is this 2 decimals 3.14 string. This %0.2f means substitute a into here, showing it with 2 digits after the decimal point, and disp takes the string that's generated by the sprintf command, sprintf, or the string printf command, and disp actually displays the string. And to show you another example, sprintf 6 decimals %0.6f comma a, and this should print pi with 6 decimal to 6 decimal places. Finally, I was displaying a like so, and it looked like this. You can actually, there are useful shortcuts. You type format long. It causes strings to, by default, be displayed to a lot more decimal places, and format short is a command that restores the default of just printing a small number of digits. Okay, that's how you work with variables. Now let's look at vectors and matrices. Let's say I want to assign A to a matrix. Let me show you an example. 1, 2, semicolon, 3, 4, semicolon, 5, 6. This generates a 3 by 2 matrix A, whose first row is 1, 2, second row is 3, 4, third row is 5, 6. What the semicolon does is essentially say, go to the next row of the matrix. There are other ways to type this. You can type A equals 1, 2, semicolon, 3, 4, semicolon, 5, 6. Like so, and that's another equivalent way of assigning A to be the values of this 3 by 2 matrix. Similarly, you can assign vectors. So V equals 1, 2, 3. This is actually a row vector, or this is a 3 by 1 vector, right? This is a fat Y vector. This is a 1 by 3 matrix, right? Not 3 by 1. If I want to assign this to a column vector, what I would do is instead do V equals 1 semicolon 2 semicolon 3, and this will give me a 3 by 1 instead of 1 by 3 vector. So this gives me a column vector. Here's some more useful notation. I can also set V equals 1 colon 0.1 colon 2. What this does is it sets V to the bunch of elements that start from 1 and increments in steps of 0.1 until you get up to 2. So if I do this, V is going to be this row vector, or this is a 1 by 11 matrix really. That's 1.1, 1.1, 1.2, 1.3, and so on until we get up to 2. Now, I can also set V equals 1 colon 6, and that sets V to be these numbers 1 through 6. Okay. Now, here are some other ways of generating matrices. Ones, 2 by 3, is a command that generates a matrix that is a 2 by 3 matrix that is the matrix of all ones. So if I set C equals 2 times ones, 2 by 3, this generates a 2 by 3 matrix that is all 2s. And this is, you can think of it as a shorter way of writing this than C equals 2, 2, 2, semicolon, 2, 2, 2, which will also give you the same result. Let's set W equals ones, 1 by 3. So this is going to be a row vector, or a row of 3 runs. And similarly, you can also set W equals zeros, 1 by 3, and this generates a matrix, a 1 by 3 matrix of all zeros. Just a couple more ways to generate matrices. If I do W equals rand 1 by 3, this gives me a 1 by 3 matrix of all random numbers. If I do rand 3 by 3, this gives me a 3 by 3 matrix of all random numbers drawn from the uniform distribution between 0 and 1. So every time I do this, I get a different set of random numbers drawn uniformly between 0 and 1. For those of you that know what a Gaussian random variable is, or for those of you that know what a normal random variable is, you can also set W equals rand n, 1 by 3, and so these are going to be 3 values drawn from a Gaussian distribution with mean 0 and variance or standard deviation equal to 1. And you can set more complex things like W equals -6 plus square root 10 times let's say rand n 1 by 10,000, and I'm going to put a semicolon at the end because I don't really want this printed out. This is going to be a this is going to be a vector with 100,000, excuse me, 10,000 elements. So, well, actually, you know what? Let's print it out. So this will generate a matrix like this, right, with 10,000 elements. So that's what W is. And if I now plot a histogram of W with the hist command, I can now, and Octave's print hist command, it takes a couple seconds to bring this up, but this is a histogram of my random variable for W that was -6 plus square root 10 times this Gaussian random variable. And I can plot a histogram with more buckets, with more bins, with say 50 bins. And this is my histogram of a Gaussian with mean -6 because I have a -6 there plus square root 10 times this. So the variance of this Gaussian random variable is 10, or the standard deviation is square root of 10, which is about, what, 3.1. Finally, one special command for generating a matrix, which is the I command. So I stands for, this is maybe a pun on the word identity, but so if I set I4, this is the 4x4 identity matrix. So set I equals I4, this gives me a 4x4 identity matrix, and I equals I6, that gives me a 6x6 identity matrix, and I3 is the 3x3 identity matrix. Lastly, to wrap up this video, there's one more useful command, which is the help command. So you can type help I, and this brings up the help function for the identity matrix. Hit Q to quit, and you can also type help rand, brings up documentation for the rand, or the random number generation function, or even help, which shows you, help on the help function. So those are the basic operations in Octave, and with this you should be able to generate a few matrices, multiply, add things, and use the basic operations in Octave. In the next video, I'd like to start talking about more sophisticated commands and how to move data around and start to process data in Octave. In this second tutorial video on Octave, I'd like to start to tell you how to move data around in Octave. So if you have data for a machine learning problem, how do you load that data into Octave? How do you put it into a matrix? How do you manipulate these matrices? How do you save the results? How do you move data around and operate with data? Here's my Octave window as before, picking up from where we left off in the last video. If I type A, that's the matrix that we generated, right, with this command equals 1, 2, 3, 4, 5, 6, and this is a 3x2 matrix. The size command in Octave lets you, tells you what is the size of a matrix. So size A returns 3, 2. It turns out that the size command itself is actually returning a 1x2 matrix. So you can actually set sz equals size of A, and sz is now a 1x2 matrix where the first element of this is 3 and the second element of this is 2. So you can type size of sz. This sz is a 1x2 matrix whose two elements contain the dimensions of the matrix A. You can also type size A1 to give you back the first dimension of A, the size of the first dimension of A, so that's the number of rows, and size A2 to give you back 2, which is the number of columns in the matrix A. If you have a vector V, so let's say V equals 1, 2, 3, 4, and you type length V, what this does is it gives you the size of the longest dimension. So you can also type length A, and because A is a 3x2 matrix, the longer dimension is of size 3, so this should print out 3. But usually we apply length only to a vector, so length 1, 2, 3, 4, 5, rather than apply length to matrices, because that's a little more confusing. Now, let's look at how to load data and find data on a file system. When we start up Octave, we're often in a path that is the location of where the Octave program is. So the pwd command shows the current directory or the current path that Octave is in. So right now we're in this maybe somewhat obscure directory. The cd command stands for change directory, so I can go to c:/user/ang/desktop, and now I'm in my desktop. And if I type ls, ls comes from a Unix or Linux command, but ls will list the directories on my desktop, and so these are the files that are on my desktop right now. In fact, on my desktop are two files, features x and price y, that maybe come from a machine learning problem we want to solve. So here's my desktop. Here's features x, and features x is this window, is this file with two columns of data. This is actually my housing prices data. So I think I have 47 rows in this data set, and so the first house had size 2104 square feet, has 3 bedrooms. Second house has 1600 square feet, has 3 bedrooms, and so on. And price y is this file that has the prices of the data in my training set. So features x and price y are just text files with my data. How do I load this data into Octave? Well, let's type the command load features x.dat, and if I do that, I load the features x and can load price y.dat. And by the way, there are multiple ways to do this. This command, if you put features x.dat in strings and load it like so, this is a oops, typo there. This is a equivalent command. So you can, but this way I'm just putting the file name of the string in a string, and in Octave you use single quotes to represent strings, like so. So that's a string, and I can load the file whose name is given by that string. Now, the who command now shows me what variables I have in my Octave workspace. So who shows me what are the variables that Octave has in memory currently. Features x and price y are among them, as well as the variables that we created earlier in the session. So I can type features x to display features x, and there's my data. And I can type size features x, and that's my 47 by 2 matrix. And similarly, size price y, that gives me my 47 by 1 vector. This is a 47-dimensional vector, this tall column vector that has all the prices y in my training set. Now, the who function shows you what are the variables that in the current workspace. There's also the who s variable that gives you the detailed view. And so this also, with an s at the end, this also lists my variables, except that it now lists the sizes as well. So A is a 3 by 2 matrix, and features x is a 47 by 2 matrix, price y is a 47 by 1 matrix, meaning this is just a vector. And it shows how many bytes of memory is taking up, as well as what type of data this is. Double means double precision floating point, so that just means these are real values, so floating point numbers. Now, if you want to get rid of a variable, you can use the clear command. So clear features x, and type who's again. You notice that the features x variable has now disappeared. And how do we save data? Let's see. Let's take the variable v and set it to price y 1:10. This sets v to be the first 10 elements of the vector y. So let's type who or whose. Whereas y was a 47 by 1 vector, v is now 10 by 1 because v equals price y 1:10. This sets it to just the first 10 elements of y. Let's say I want to save this to disk. The command save hello.mat_v. This will save the variable v into a file called hello.mat. So let's do that. And now a file has appeared on my desktop, called hello.mat. I happen to have MATLAB installed in this Windows, which is why this icon looks like this, because Windows has recognized this as a MATLAB file. But don't worry about it if this file looks like it has a different icon on your machine. And let's say I clear all my variables. So if you type clear without anything, then this actually deletes all the variables in your workspace. So if I type whos, there's now nothing left in my workspace. And if I load hello.mat, I can now load back my variable v, which is my the data that I previously saved into the hello.mat file. So hello.mat, what we did just now, the save hello.mat to v, this saves the data in a binary format, in a somewhat more compressed binary format, so that if v is a lot of data, this will be somewhat more compressed and will take up less disk space. If you want to save your data in a human readable format, then you type save hello.text, the variable v, and then dash ASCII. So this will save it as a text, or as ASCII formatted text. And now, once I've done that, I have this file, hello.text, has just appeared on my desktop. And if I open this up, you see that this is a text file with my data saved away. So that's how you load and save data. Now let's talk a bit about how to manipulate data. Let's set A equals to that matrix again. So it's my 3 by 2 matrix. Let's talk about indexing. So if I type A 3, 2, this indexes into the 3, 2 element of the matrix A. So this is normally we would write this as A subscript 3, 2, or A subscript 3, 2. And so that's the element in the third row and second column of A, which is the element 6. I can also type A 2, colon to fetch everything in the second row. So the colon means every element along that row or column. So A of 2, colon is this second row of A. Right? And similarly, if I do A colon, 2, then this means get everything in the second column of A. So this gives me 2, 4, 6. Right? This means of A, everything, second column. So this is my second column of A, which is 2, 4, 6. Now, you can also use somewhat more sophisticated indexing operations. So I'll just quickly show you an example. You do this maybe less often, but let me do A 1, 3, colon. This means get all the elements of A whose first index is 1 or 3. This means get everything from the first and third rows of A and from all columns. So this was the matrix A, and so A 1, 3, colon means get everything from the first row and from the second row and from the third row. And colon means I want both the first and the second columns. And so this gives me this 1, 2, 5, 6. Although you use these sorts of more sophisticated indexing operations maybe somewhat less often. To show you what else we can do, here's the A matrix, and this was A colon, 2 gave me the second column. You can also use this to do assignment. So I can take the second column of A and assign that to 10, 11, 12. And if I do that, I'm now taking the second column of A and I'm assigning this column vector 10, 11, 12 to it. So now A is this matrix that's 1, 3, 5, and the second column has been replaced by 10, 11, 12. And here's another operation. Let's set A to be equal to A, 100, 101, 102, like so. And what this will do is append another column vector to the right. So now, oops, I think I made a mistake. Should have put semicolons there. And now, A is equal to this. Okay, I hope that makes sense. So this 100, 101, 102, this is a column vector. And what we did was we take A and set it to the original definition, and then we put that column vector to the right. And so we ended up taking the matrix A, and which was these 6 elements on the left. So we took the matrix A and we appended another column vector to the right, which is now why now A is a 3 by 3 matrix that looks like that. And finally, one neat trick that I sometimes use, if you do A and then just a colon like so. This is a somewhat special case syntax. What this means is that puts all elements of A into a single column vector, and this gives me a 9 by 1 vector that just has all the elements of A concatenated together. Just a couple more examples. I can also, let's say I set A to be equal to 1, 2, 3, 4, 5, 6 again. And let's say I set B to be equal to 11, 12, 13, 14, 15, 16. I can create a new matrix C as A, B. And this just means, so here's my matrix A, here's my matrix B, and if I set C to be equal to A, B, what I'm doing is I'm taking these two matrices and just concatenating them onto each other. So the left matrix A on the left, and I have the matrix B on the right, and that's how I form this, this matrix C by putting them together. I can also do C equals A semicolon B. The semicolon notation means that means I go put the next thing at the bottom. So if I do C equals A semicolons B, it also puts the matrices A and B together, except that it now puts them on top of each other. So now I have A on top and B at the bottom, and C here is now a 6 by 2 matrix. So just say again, the semicolon thing usually means go to the next line. So C is comprised by A, and then go to the bottom of that, and then put B at the bottom. And by the way, this AB is the same as A comma B, and so either of these gives you the same result. So with that, hopefully you now know how to construct matrices, and hopefully this starts to show you some of the commands that you can use to quickly put together matrices, and take matrices and slam them together to form bigger matrices. And with just a few lines of code, Octave is very convenient in terms of how quickly we can assemble complex matrices and move data around. So that's it for moving data around. In the next video, we'll start to talk about how to actually do complex computations on our data. So hopefully that gives you a sense of how, with just a few commands, you can very quickly move data around in Octave. You can load and save vectors and matrices, or load and save data, put together matrices to create bigger matrices, index into or select specific elements of the matrices. I know I went through a lot of commands, but so I think the best thing for you to do is afterward to look at the transcript of the things I was typing. Look at the course website and download the transcript of the session from there, and look through the transcript and type some of those commands into Octave yourself, so that you can start to play with these commands and get it to work. And obviously, there's no point at all to trying to memorize all these commands. It's just, but what you should do is hopefully from this video you have gotten a sense of the sorts of things you could do, so that when later on, when you're trying to program a learning algorithm just yourself, if you are trying to find a specific command that maybe you think Octave can do because you think you might have seen it here, you should refer to the transcript of the session and look through that in order to find the commands you want to use. So that's it for moving data around, and in the next video what I'd like to do is start to tell you how to actually do complex computations on our data, and how to compute on our data and actually start to implement learning algorithms. Now that you know how to load and save data in Octave, put your data into matrices and so on, in this video I'd like to show you how to do computational operations on data. And later on we'll be using these sorts of computational operations to implement our learning algorithms. Let's get started. Here's my Octave window. Let me just quickly initialize some variables to use for our example. So set A to be a 3 by 2 matrix, and set B to a 3 by 2 matrix, and let's set C to a 2 by 2 matrix, like so. Now, let's say I want to multiply two of my matrices. So let's say I want to compute A times C. I just type A times C. So it's a 3 by 2 matrix times a 2 by 2 matrix. This gives me this 3 by 2 matrix. You can also do element-wise operations and do A dot times B. And what this will do is it'll take each element of A and multiply it by the corresponding element of B. So that's A, that's B, that's A dot times B. So for example, the first element gives 1 times 11, which gives 11. The second element gives 2 times 12, which gives 24, and so on. So this is the element-wise multiplication of two matrices. And in general, the period is usually used to denote element-wise operations in octave. So here's the matrix A, and if I do A dot caret 2, this gives me the element-wise squaring of A. So 1 squared is 1, 2 squared is 4, and so on. Let's set V to a vector. Let's set V as 1, 2, 3 as a column vector. You can also do 1 dot over V to do the element-wise reciprocal of V. So this gives me 1 over 1, 1 over 2, and 1 over 3. And this works too for matrices. So 1 dot over A gives me that element-wise inverse of A. Once again, the period here gives us a clue that this is an element-wise operation. You can also do things like log V. This is an element-wise logarithm of the element of the V. E to the V is base E exponentiation of V's elements. So this is E squared E cubed because this was V. And I can also do abs V to take the element-wise absolute value of V. So here, V was all positive, but we did abs, say minus 1, 2, minus 3. The element-wise absolute value gives me back these non-negative values. And negative V gives me the minus of V. This is the same as negative 1 times V, but usually you just write negative V instead of negative 1 times V. And what else can you do? Here's another neat trick. So let's see. Let's say I want to take V and increment each of its elements by 1. Well, one way to do it is by constructing a 3 by 1 vector that's all 1s and adding that to V. So if I do that, this increments V from 1, 2, 3 to 2, 3, 4. The way I did that was length of V is 3. So 1s, length of V by 1, this is 1s of 3 by 1. So that's 1s 3 by 1 on the right. And what I did was V plus 1s 3 by 1, which is adding this vector of all 1s to V, and so this increments V by 1. And another simpler way to do it is actually to type V plus 1, right? So here's V, and V plus 1 also means to add 1 element-wise to each of my elements of V. Now, let's talk about more operations. So here's my matrix A. If you want to write A transpose, the way to do that is to write A prime. That's the apostrophe symbol. It's the left quote. So on your keyboard, you probably have a left quote and a right quote. So this is this is actually the standard quotation mark. Is let me just type A transpose. This gives me the transpose of my matrix A. And of course, A transpose. If I transpose that again, then I should get back my matrix A. Some more useful functions. Let's say lowercase a is 1, 15 to 0.5. So it's a 1 by 4 matrix. Let's say I set val equals max of a. This returns the maximum value of a, which in this case is 15. And I can do val int max a, and this returns val and int, which are going to be the maximum value of a, which is 15, as well as the index. So it's the element number 2 of a that was 15. So int is my index into this. Just as a warning, if you do max a, where a is a matrix, what this does is this actually does the column-wise maximum. But say a little bit more about this in a second. Still using this example of the variable lowercase a, if I do a less than 3, this does the element-wise operation, element-wise comparison. So the first element of a is less than 3, so it gives 1. Second element of a is not less than 3, so this value says 0 because it's false. The third and fourth elements of a are, I meant less than 3. Third and fourth elements are less than 3, so this gives 1, 1. So this does the element-wise comparison of all 4 elements of the variable lowercase a to 3, and it returns true or false depending on whether or not it's less than 3. Now, if I do find a less than 3, this will tell me which are the elements of a, the variable a that are less than 3. And in this case, the first, third, and fourth elements are less than 3. For my next example, let me set a to be equal to magic 3. The magic function returns, let's type help magic. The magic function returns functions called returns these matrices called magic squares. they have this mathematical property that all of their rows and columns and diagonals sum up to the same thing. So it's not actually useful for machine learning as far as I know, but I'm just using this as a convenient way to generate a 3 by 3 matrix. And these magic squares, right, have the property that each row, each column, and the diagonals all add up to the same thing. So it's kind of a mathematical construct. I use this magic function only when I'm doing demos or when I'm teaching octave like this, and I don't actually use it for any useful machine learning application. But let's see, if I type RC equals find a greater than or equals 7, this finds all the elements of A that are greater than or equal to 7, and so RC sends a row and column. So the 1, 1 element is greater than 7, the 3, 2 element is greater than 7, and the 2, 3 element is greater than 7. So let's see, the 2, 3 element, for example, is A2, 3, is 7, is this element out here, and that is indeed greater than or equal to 7. By the way, I actually don't even memorize myself what these find functions do and what all of these things do myself. And whenever I use the find function, sometimes I forget myself exactly what it does. And I type help find to look up the document. Okay, just two more things I'm going to quickly show you. One is the sum function. So here's my A, and then type sum A. This adds up all the elements of A. And if I want to multiply them together, I type prod A. Prod stands for product, and this returns the product of these 4 elements of A. Floor A rounds down these elements of A, so 0.5 gets rounded down to 0, and seal or ceiling A gets rounded up, so 0.5 rounded up to the nearest integer, so 0.5 gets rounded up to 1. You can also let's see, let me type rand3. This generates a 3 by 3 matrix. If I type max rand3, what this does is it takes the element-wise maximum of 2 random 3 by 3 matrices. So you notice all of these numbers tend to be a bit on the large side because each of these is actually the max of a randomly element-wise max of 2 randomly generated matrices. This is my magic number. This was my magic square 3 by 3A. Let's say I type max A, and then this weird open close square brackets, comma 1. What this does is this takes the column-wise maximum. So the max in the first column is 8, max in the second column is 9, the max in the third column is 7. This 1 means to take the max along the first dimension of A. In contrast, if I were to type max A, this funny notation 2, then this takes the per row maximum. So the max of the first row is 8, max of the second row is 7, max of the third row is 9. And so this allows you to take maxes either per row or per column. And if you want to, remember it defaults to a column-wise element. So if you want to find the maximum element in the entire matrix A, you can type max of A, like so, which is 9, or you can turn A into a vector and type max of A colon, like so, and this treats this as a vector and takes the max element of that vector. Finally, let's set A to be a 9 by 9 magic square. So remember, the magic square has this property that every column and every row sums to the same thing, and also the diagonal. So here's a 9 by 9 magic square. So let me do sum A1. So this does a per column sum. So I'm going to take each column of A and add them up. And this lets us verify that indeed for a 9 by 9 magic square, every column adds up to 369, adds up to the same thing. Now let's do the row-wise sum. So the sum A, comma 2, and this sums up each row of A, and indeed each row of A also sums up to 369. Now let's sum the diagonal elements of A and make sure that that also sums up to the same thing. So what I'm going to do is construct a 9 by 9 identity matrix, that's I9, and I'm going to take A and construct, multiply A element-wise. So here's my matrix A. I'm going to do A dot times I9, and what this will do is take the element-wise product of these two matrices, and so this should wipe out everything in A except for the diagonal entries. And now I'm going to do sum of A of that, and this gives me the sum of these diagonal elements, and indeed it is 369. You can sum up the other diagonal as well. So instead of top left to bottom right, you can sum up the opposite diagonal from bottom left to top right. The commands for this is somewhat more cryptic. You don't really need to know this. I'm just showing you this in case any of you are curious. But let's see. Flip UD stands for flip up down. But if you do that, that turns out to sum up the elements in the opposites of the other diagonal of A, and that also sums up to 369. Here, let me show you. Whereas I9 is this matrix, flip up down of I9, takes the identity matrix and flips it vertically, so you end up with, flip UD, end up with ones on this opposite diagonal as well. Just one last command, and then that's it, and then that'll be it for this video. Let's set A to be the magic 3x3 magic square game. If you want to invert a matrix, you type P-inv A. This is technically called the pseudo-inverse, but it doesn't matter. Just think of it as basically the inverse of A, and that's the inverse of A. And so I can set, temp equals P-inv of A, and if I take temp times A, this is indeed the identity matrix with essentially ones on the diagonals and zeros on the off diagonals up to a numerical round off. So that's it for how to do different computational operations on the data and matrices. After running a learning algorithm, often one of the most useful things is to be able to look at your results, or to plot or visualize your results. And in the next video, I'm going to very quickly show you how, again, with 1 or 2 lines of code, using Octave, you can quickly visualize your data or plot your data and use that to better understand what your learning algorithms are doing. When developing learning algorithms, very often a few simple plots can give you a better sense of what the algorithm is doing and just sanity check that everything's going okay and the algorithm's doing what it's supposed to. For example, in an earlier video, I talked about how plotting the cost function j of theta can help you make sure that gradient descent is converging. Often, plots of the data or of the learning algorithm outputs will also give you ideas for how to improve your learning algorithm. Fortunately, Octave has very simple tools to generate lots of different plots, and when I use learning algorithms, I find that plotting the data, plotting the learning algorithm, and so on are often an important part of how I get ideas for improving the algorithms. And in this video, I'd like to show you some of these Octave tools for plotting and visualizing your data. Here's my Octave window. Let's quickly generate some data for us to plot. So I'm going to set t to be equal to this array of numbers. Here's t, set of numbers going from 0 up to 0.98. Let's set y1 equals sine of 2 pi 4t. And if I want to plot the sine function, it's very easy. I just type plot t comma y1 and hit enter, and up comes this plot where the horizontal axis is the t variable and the vertical axis is y1, which is the sinusoid function that we just computed. Let's set y2 to be equal to the cosine of 2 pi 4t, like so. And if I plot t comma y2, what Octave will do is it'll take my sinusoid plot and it will replace it with this cosine function that now, cosine of x starts at 1, right? Now, what if I want to have both the sine and the cosine plots on top of each other? What I'm going to do is I'm going to type plot t comma y1, so here's my sine function, and then I'm going to use the function hold on. And what hold on does is it causes Octave to now plot new figures on top of the old one. And let me now plot t, y2. I'm going to plot the cosine function in a different color. So let me put a r in quotation marks there. And instead of replacing the current figure, I'll plot the cosine function on top. And the r indicates that I want this in a red color. And here are additional commands: x label time, say to label the x-axis or the horizontal axis, and y label value, say to label the vertical axis value. And I can also label my two lines with this command, legend, sine, cosine, and this puts this legend up on the upper right, showing what the two lines are. And finally, title, my plot, puts a title at the top of this figure. Lastly, if you want to save this figure, you type print d-dpng my plot.png. So PNG is a graphics file format, and if you do this, this will actually save this as a file. If I do that, let me actually change the directory to, let's see, like that, and then I will print that out. So this will take a while, depending on how your Octave configuration is set up. This may take a few seconds, but change the directory to my desktop, and Octave is now taking a few seconds to save this. If I now go to my desktop, let's hide these windows. Here's my plot.png, which Octave has saved, and there's the figure saved as a PNG file. Octave can save files in other formats as well, so you can type help plot if you want to see the other file formats rather than PNG that it can save figures in. And lastly, if you want to get rid of a plot, the close command causes a figure to go away. So there's that figure. If I type close, that figure just disappeared from my desktop. Octave also lets you specify a figure number. So you type figure 1 plot ty1. That starts up first figure, and that plots ty1. And then if you want a second figure, you specify a different figure number. So figure 2 plots ty2, like so. And now on my desktop, I actually have two figures, figure 1 and figure 2. That's one plotting the sine function, one plotting the cosine function. Here's one other neat command that I often use, which is the subplot command. So I'm going to use subplot 1, 2, 1. What that does is it subdivides the plot into a 1x2 grid. That's what the first two parameters are. And it starts to access the first element. That's what the final parameter 1 is, right? So this divide my figure into a 1x2 grid, and I want to access the first element right now. And so if I type that in, it's brought up this figure that's on the left, and if I plot ty1, it now fills up this first element, and if I now do subplot 1, 2, 2, I'm going to start to access the second element, and plot ty2 will fill in y2 in the right hand side or in the second element. And last command, you can also change the axis scales and change axes to 0.51, -1, 1, and this sets the x range and y range for the figure on the right. And concretely, it sets the horizontal range of values in the figure on the right to range from 0.5 to 1, and the vertical axis values to range from -1 to 1. And you don't need to memorize all these commands. If you ever need to change the axis, all you need to know is that there's an axis command, and you can really get the details from the usual Octave help command. Finally, just a couple last commands. CLF clears a figure. And here's one more neat trick. Let's set A to be equal to a 5x5 matrix square, say. So A is now this 5x5 matrix. There's a neat trick that I sometimes use to visualize a matrix, which is I can use image SC of A. And what this will do is this will plot a 5x5 matrix. So I'll take my matrix, I'll plot this as a 5x5 grid of colors, where the different colors correspond to the different values in the A matrix. So concretely, I can also do color bar. Let me use a more sophisticated command. Image SCA, color bar, color map, gray. This is actually running 3 commands at a time. I'm running image SC, then running color bar, then running color map, gray. And what this does is it sets the color map to a gray color map, and on the right it also puts in this color bar. And so this color bar shows what the different shades of color correspond to. Concretely, the upper left element of the A matrix is 17, and so that corresponds to kind of a mid shade of gray. Whereas in contrast, the second element of A, so the 1, 2 element of A is 24, right? So it's A, 1, 2 is 24. So that corresponds to this square up here, which is nearly a shade of white. And the small values, say A, what is that? A45, is the value 3 over here. That corresponds, you can see on my color bar, that corresponds to a much darker shade in this image. So here's another example. I can plot a larger, here's a magic 15. That gives me a 15 by 15 magic square. And this gives me a plot of what my 15 by 15 magic squares values look like. And finally, to wrap up this video, what you've seen me do here is use comma chaining of function calls. Here's how you actually do this. If I type A equals 1, B equals 2, C equals 3, and hit enter, then this is actually carrying out 3 commands at the same time, or really carrying out 3 commands one after another. And it prints out all 3 results. And this is a lot like A equals 1, B equals 2, C equals 3, except that if I use semicolons instead of a comma, it doesn't print out anything. So this thing here we call comma chaining of commands, or comma chaining of function calls, and it's just another convenient way in Octave to put multiple commands, like ImageSC, color bar, color map, to put multiple commands on the same line. So that's it. You now know how to plot different figures in Octave, and in the next video, the next main piece I want to tell you about is how to write control statements, like if, while, for statements in Octave, as well as how to define and use functions. In this video, I'd like to tell you how to write control statements for your Octave programs. So things like for, while, and if statements, and also how to define and use functions. Here's my Octave window. Let me first show you how to use a for loop. I'm going to start by setting V to be a 10 by 1 vector of zeros. Now, here's how I write a for loop. For I equals 1 to 10. That's for I equals 1 colon 10. And let's see. I'm going to set V of I equals 2 to the power of I. And finally, end. The white space doesn't matter, so I'm putting the spaces just to make it look nicely indented, but the spacing doesn't matter. But if I do this, then the result is that V gets set to to the power 1, to the power 2, and so on. So this is syntax for I equals 1 colon 10 that makes I loop through the values 1 through 10. And by the way, you can also do this by setting your indices equals 1 to 10. And let's look at indices. This is an array from 1 to 10. You can also write for I equals indices. And this is actually the same as for I equals 1 through 10. You can do display I, and this will do the same thing. So that was a for loop. If you're familiar with break and continue, that's break and continue statements, you can also use those inside loops in Octave. But first, let me show you how a while loop works. So here's my vector V. Let's write a while loop. I equals 1. While I is less than or equal to 5. Let's set V I equals 100 and increment I by 1. End. So this says I starts off equal to 1, and then I'm going to set Vi equals 100 and increment I by 1 until I is greater than 5. And as a result of that, whereas previously V was this powers of 2 vector, I've now taken the first 5 elements of my vector and overwritten them with this value 100. So that's the syntax for a while loop. Let's do another example. I equals 1 while true. And here I want to show you how to use a break statement. Let's set V I equals 999 and I equals I plus 1. If I equals 6, break, end, end. And this is also our first use of an if statement. So I hope the logic of this makes sense. It says for I equals I equals 1 and infinite loop, while repeatedly set Vi equals 1 and increment I by 1, and then once I gets up to 6, do a break, which breaks you out of the while loop. And so the effect of this should be to take the first 5 elements of this vector V and set them to 999, And yes, indeed, we've taken v and overwritten the first 5 elements with 999. So this is the syntax for if statement and for a while statement. And notice the end. We have 2 ends here. This end here ends the if statement, and the second end here ends the while statement. Now let me show you the more general syntax for how to use the if-else statement. So let's see, v1 is equal to 999. Let's set v1 equals to 2 for this example. So let me type if v1 equals 1, display the value is 1. Here's how you write an else statement, or rather here's an else if v1 equals 2. This is going to be the case that's true in our example. Display the value is 2, else display the value is not 1 or 2. Okay, so that's a if else statement hit end, and of course here we've just set v1 equals 2, so hopefully, yep, it displays that the value is 2. And finally, I don't think I talked about this earlier, but if you ever need to exit Octave, you can type the exit command. If you hit enter, that will cause Octave to quit, or the quit command also works. Finally, let's talk about functions and how to define them and how to use them. Here's my desktop, and I have predefined a file, or pre-saved on my desktop, a file called squarethisnumber.m. This is how you define functions in Octave. You create a file called, with your function name and then ending in .m. And when Octave finds this file, it knows that this is where it should look for the definition of the function squarethisnumber.m. Let's open up this file. Notice that I'm using the Microsoft program WordPad to open up this file. I just want to encourage you, if you're using Microsoft Windows, to use WordPad rather than Notepad to open up these files. If you have a different text editor, that's fine too, but Notepad sometimes messes up the spacing. If you only have Notepad, that should work too. That could work too. But if you have WordPad as well, I would rather use that, or some other text editor if you have a different text editor for editing your functions. So here's how you define a function in Octave. Let me just zoom in a little bit. And this file has just 3 lines in it. The first line says function y equals square this number x. This tells Octave that I'm going to return a value y. And I'm going to return one value, and that value is going to be saved in the variable y. And moreover, it tells Octave that this function has one argument, which is the argument x. And the way the function body is defined, if y equals x squared. So let's try to call this function square this number 5. And this actually isn't going to work. And Octave says square this number is undefined. That's because Octave doesn't know where to find this file. So as usual, let's use pwd. Oh, I'm not in the right directory. So let's cd users ang/desktop. That's where my desktop is. Oops, a little typo there. Users ang desktop. And if I now type square this number 5, it returns the answer 25. As kind of an advanced feature, this is only for those of you that know what the term search path means. But so if you want to modify the Octave search path, and you could just think of this next part as advanced or optional material, only for those of you that are familiar with the concept of search paths in programming languages. But you can use the term add path, say c:/users/ang/desktop. to add that directory to the Octave search path, so that even if I go to some other directory, I can still Octave still knows to look in the users ang desktop directory for functions, so that even though I'm in a different directory now, it still knows where to find the square this number function. Okay, but if you're not familiar with the concept of search paths, don't worry about it. Just make sure to use the cd command to go to the directory with your function before you run it, and that should work just fine. One concept that Octave has that many other programming languages don't is that it can also let you define functions that return multiple values or multiple arguments. So here's an example of that. I've defined a function called square and cube this number x. And what this says is this function returns 2 values, y1 and y2. I'm going to set them as follows. y1 is x squared, y2 is x cubed. And what this does is this really returns, two numbers. So some of you, depending on what programming languages you use, if you're familiar with, C, C++, Java, often we think of a function as returning just one value, but this sort of syntax in Octave lets it return multiple values. Now back in the Octave window, if I type, a, b equals square and cube this number 5, then a is now equal to 25 and b is equal to the cube of 5 is equal to 125. So this is often convenient if you need to define a function that returns multiple values. Finally, I'm going to show you just one more sophisticated example of a function. Let's say I have a data set that looks like this with data points at 1, 1, 2, 2, 3, 3. And what I'd like to do is to define an Octave function to compute the cost function j of theta for different values of theta. First, let's put the data into Octave. So set my design matrix to be 1, 1, 1, 2, 1, 3. So this is my design matrix X with X0, the first column being the intercept term, and the second term being my the X values of my 3 training examples. And let me set Y to be 1, 2, 3, as follows, which were the y-axis values. So let's say theta is equal to 0, semicolon 1. Here on my desktop, I've predefined this cost function j, and if I bring up the definition of that function, it looks as follows. So function j equals cost function j, inputs x, y, theta, some comments specifying the inputs, and then via a few steps, set m to be the number of training examples, that's the number of rows in x, compute the predictions. Predictions equals x times theta. And this is a comment that's wrapped around. So this is part of the preceding comment line. Compute the squared errors by taking the difference between predictions and the y values and taking element y squaring. And then finally computing the cost function j. And Octave knows that j is the value I want to return because j appeared here in the function definition. Feel free, by the way, to pause this video if you want to look at this function definition for longer and kind of make sure that you understand the different steps. But when I run it in Octave, I run j equals cost function j, x, y, theta. It computes, oops, made a typo there, should have been capital X. It computes j equals 0 because if my data set was, 1, 2, 3, 1, 2, 3, then setting theta 0 equals 0, theta 1 equals 1, this gives me exactly the 45-degree line that fits my data set perfectly. Whereas in contrast, if I set theta equals, say, 0, 0, then this hypothesis is predicting zeros on everything. This is saying theta 0 equals 0, theta 1 equals 0, and then compute the cost function, then is 2.333, and that's actually equal to 1 squared, which is my squared error on the first example, plus 2 squared, plus 3 squared, and then divided by 2m, which is 2 times number of training examples, which is indeed 2.33. And so that sanity checks that this function here is, computing the correct cost function, at least in the couple of examples we tried out on our simple training example. And so that sanity checks that the cost function j, as defined here, that it is indeed, seeming to compute the correct cost function, at least on our simple training set that we had here with x and y being the simple training example that we saw. So now you know how to write control statements like for loops, while loops, and if statements in Octave, as well as how to define and use functions. In the next video, I'm going to just very quickly step you through the logistics of working on and submitting problem sets for this class, and how to use our submission system. And finally, after that, in the final Octave tutorial video, I want to tell you about vectorization, which is an idea for how to make your Octave programs run much faster. In this video, I'd like to tell you about the idea of vectorization. So whether you're using Octave or a similar language like MATLAB, or whether you're using Python, NumPy, R, Java, C, C++, all of these languages have either built into them or have readily and easily accessible different numerical linear algebra libraries that are usually very well written, highly optimized, often sort of developed by people that have PhDs in numerical computing or that are really specialized in numerical computing. And when you're implementing machine learning algorithms, if you're able to take advantage of these linear algebra libraries or these numerical linear algebra libraries and make subroutine calls to them rather than sort of write code yourself to do things that these libraries could be doing, if you do that, then often you get code that first is more efficient, so just run more quickly and take better advantage of any parallel hardware your computer may have and so on. And second, it also means that you end up with less code that you need to write, so a simpler implementation that is therefore maybe also more likely to be bug-free. And as a concrete example, rather than writing code yourself to multiply matrices, if you let Octave do it by typing A times B, that will use a very efficient routine to multiply the two matrices. And there's a bunch of examples like these, where if you use appropriate vectorized implementations, you get much simpler code and much more efficient code. Let's look at some examples. Here's our usual hypothesis for linear regression, and if you want to compute h of x, notice that there's a sum on the right, and so one thing you could do is compute the sum from j equals 0 to j equals n yourself. Another way to think of this is to think of h of x as theta transpose x, and what you can do is think of this as computing this inner product between two vectors, where theta is your vector, say theta 0, theta 1, theta 2, if you have two features, if n equals 2, and if you think of x as this vector, x0, x1, x2. And these two views can give you two different implementations. Here's what I mean. Here's an unvectorized implementation for how to compute h of x. And by unvectorized, I mean without vectorization. We might first initialize prediction this to be 0.0. This is going to eventually be prediction is going to eventually be h of x. And then I'm going to have a for loop for j equals 1 through n plus 1. Prediction gets incremented by theta j times xj. So it's kind of this expression over here. By the way, I should mention, in these vectors that I wrote over here, I had these vectors being 0 index. So I had theta 0, theta 1, theta 2. But because MATLAB is one index, theta 0 in MATLAB, we might end up representing as theta 1, and this second element ends up as theta 2, and this third element might end up as theta 3, just because vectors in MATLAB are indexed starting from 1, even though I wrote theta and x here starting indexing from 0, which is why here I have a for loop. J goes from 1 through n plus 1 rather than j goes through 0 up to n. Right? But so this is an unvectorized implementation in that we have a for loop that's summing up the n elements of the sum. In contrast, here's how you would write a vectorized implementation, which is that you would think of x and theta as vectors, and you just set prediction equals theta transpose times x. You're just computing it like so. So you, instead of writing all these lines of code with a for loop, you instead just have one line of code, and what this line of code on the right will do is it will use Octave's highly optimized numerical linear algebra routines to compute this inner product between the two vectors, theta and x. And not only is the vectorized implementation simpler, it will also run much more efficiently. So that was Octave, but the issue of vectorization applies to other programming languages as well. Let's look at an example in C++. Here's what an unvectorized implementation might look like. We again initialize prediction to 0.0, and then we now have a for loop for j equals 0 up to n, prediction plus equals theta j times xj, where again you have this explicit for loop that you write yourself. In contrast, using a good numerical linear algebra library in C++, you could write a function like, or rather, in contrast, using a good numerical linear algebra library in C++, you can instead write code that might look like this. So depending on the details of your numerical linear algebra library, you might be able to have an object. This is a C++ object, which is a vector theta, and a C++ object, which is a vector x, and you just take theta dot transpose times x, where this times becomes a C++ sort of overloaded operator, so you can just multiply these two vectors in C++. And depending on the details of your numerical linear algebra library, you might end up using a slightly different syntax, but by relying on the library to do this inner product, you can get a much simpler piece of code and a much more efficient one. Let's now look at a more sophisticated example. Just to remind you, here's our update rule for gradient descent for linear regression. And so we update theta j using this rule for all values of j equals 0, 1, 2, and so on. And if I just write out these equations for theta 0, theta 1, theta 2, assuming we have two features, so n equals 2, then these are the updates we perform to theta 0, theta 1, theta 2, where you might remember my saying in an earlier video that these should be simultaneous updates. So let's see if we can come up with a vectorized implementation of this. Here are my same three equations written in a slightly smaller font, and you can imagine that one way to implement these three lines of code is to have a for loop that says, for j equals 0, 1 through 2 to update theta j or something like that. But instead, let's come up with a vectorized implementation and see if we can have a simpler way to basically compress these three lines of code, or a for loop that effectively does these three steps one step at a time. Let's see if we can take these three steps and compress them into one line of vectorized code. Here's the idea. What I'm going to do is I'm going to think of theta as a vector, and I'm going to update theta as theta minus alpha times some other vector delta, where delta is going to be equal to 1 over m sum from I equals 1 through m, and then this term over on the right. Okay, so let me explain what's going on here. Here I'm going to treat theta as a vector, so there's an n plus 1 dimensional vector. And I'm saying that theta gets updated as that's a vector, Rn plus 1. Alpha is a row number, and delta here is a vector. So this subtraction operation, that's a vector subtraction, okay? Because alpha times delta is a vector, and so I'm saying theta gets, this vector, alpha times delta subtracted from it. So what is the vector delta? Well, this vector delta looks like this, and what it's meant to be is really meant to be this thing over here. Concretely, delta will be a n plus 1 dimensional vector, and the very first element of the vector delta is going to be equal to that. So if we have that delta, if we index it from 0, if it's delta 0, delta 1, delta 2, what I want is that delta 0 is equal to, this first box in green up above. And indeed, you might be able to convince yourself that delta 0 is this 1 over m sum of, h of x, xi minus yi times xi 0. So let's just make sure that we're on the same page about how delta really is computed. Delta is 1 over m times the sum over here. And, what is the sum? Well, this term over here, that's a row number. And the second term over here, xi, this term over there is a vector, right? Because xi, may be a vector that would be, say, xi0, xi1, xi2, right? And what is the summation? Well, what the summation is saying is that this term, that is this term over here, this is equal to h of x1 minus y1 times x1 plus h of x2 minus y2 times x2 plus, and so on. Okay, because this is a summation over I, so as I ranges from I equals 1 through m, you get these different terms, and you're summing up these terms here. And the meaning of each of these terms, this is a lot like, if you remember actually from the earlier quiz in this, right, you saw this equation. We said that in order to vectorize this code, we would instead set u equals 2v plus 5w. So we're saying that the vector u is equal to 2 times the vector v plus 5 times the vector w. So this is an example of how to add different vectors. And this summation is the same thing. This is saying that this summation over here is just some real number, right? That's kind of like the number 2, or some other number, times the vector x1. This is kind of like, 2 times v, instead with some other number times x1. And then plus, instead of 5 times w, we instead have some other real number plus some other vector, and then you add on other vectors, plus dot, 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 plus the other vectors, which is why overall, this thing over here, that whole quantity, that delta is just some vector. And concretely, the 3 elements of delta correspond, if n equals 2, the 3 elements of delta correspond exactly to this thing, to the second thing, and this third thing, which is why when you update theta according to theta minus alpha delta, we end up carrying exactly the same simultaneous updates as the update rules that we had on top. So I know that there was a lot that happened on this slide, but again, feel free to pause the video and I'd encourage you to sort of step through the difference. If you aren't sure what just happened, I'd encourage you to step through the slide to make sure you understand why is it that this update here with this definition of delta, right? Why is it that that's equal to this update on top? And it's still not clear. One insight is that, this thing over here, that's exactly the vector x. And so we're just taking, all 3 of these computations and compressing them into one step with this vector delta, which is why we can come up with a vectorized implementation of this step of linear regression this way. So I hope this step makes sense, and do look at the video and make sure and see if you can understand it. In case you don't understand quite the equivalence of this math, if you implement this turns out to be the right answer anyway. So even if you didn't quite understand the equivalence, if you just implement it this way, you'll be able to get linear regression to work. But if you're able to figure out why these 2 steps are equivalent, then hopefully that'll give you a better understanding of vectorization as well. And finally, if you are implementing linear regression using more than 1 or 2 features. So sometimes we'll use linear regression with tens or hundreds or thousands of features. But if you use the vectorized implementation of linear regression, usually that will run much faster than if you had, say, your own for loop that was updating theta 0, then theta 1, then theta 2 yourself. So using a vectorized implementation, you should be able to get a much more efficient implementation of linear regression. And when you vectorize later algorithms that we'll see in this class is a good trick, whether in Octave or some other language like C++, Java, for getting your code to run more efficiently. In this video, I want to just quickly step you through the logistics of how to work on homeworks in this class and how to use the submission system, which will let you verify right away that you got the right answer for your machine learning programming exercise. Here's my Octave window, and let's first go to my desktop. I saved the files for my first exercise, some of the files on my desktop in this directory, mlclass ex1. And we provide a number of files and ask you to edit some of them. So the first file, you should read the detailed PDF file for this programming exercise to get the details. But one of the files we ask you to edit is this file called warm-up exercise, where the exercise is really just to make sure that you're familiar with the submission system. And all you need to do is return the 5x5 identity matrix. So the solution to this exercise I just show you is to write A equals I5, right? So that modifies this function to generate the 5x5 identity matrix, and this function warm-up exercise now returns the 5x5 identity matrix. and I'm just going to save it. So I've done the first part of this homework. Going back to my Octave window, let's now go to my directory, user/ang/desktop/ml-class-ex1. And if I want to make sure that I've implemented this in type warm-up exercise, like so, and yep, it returns, that's the 5x5 entity matrix that we just wrote the code to create. And I can now submit the code as follows. I'm going to type submit from this directory, and I'm ready to submit part 1, so I'm going to enter choice 1. So it asks me for my email address. I'm going to go to the course website, and this lists my, this is an internal testing site, so your version of the website may look a little bit different, but that's my email address, and this is my submission password, and I'm just going to type them in here. So I have ang@cs.stanford.edu, and my submission password is 9yc75ussgf. And if I hit enter, it connects to the server and submits it, and right away it tells you, this says, congratulations, you've successfully completed homework in part 1, and this gives you a verification that you got this part right. And if you don't submit the right answer, then it'll give you a message indicating that you haven't quite gotten it right yet. And by the way, you can also you can use this submission password, and you can generate new passwords. Doesn't matter. But you can also use your regular website login password. But because this password here is typed in clear text, on your monitor, we gave you this extra submission password in case you don't want to type in your website's normal password onto a window. That depending on your operating system, this password may or may not appear as text when you type it into the Octave submission script. So that's how you submit the homeworks after you've done it. Good luck, and I hope you get, when you get around to the homeworks, I hope you get all of them right. And finally, in the next and final Octave tutorial video, I want to tell you about vectorization, which is a way to get your Octave code to run much more efficiently. In this and the next few videos, I want to start to talk about classification problems where the variable y that you want to predict is discrete valued. We'll develop an algorithm called logistic regression, which is one of the most popular and most widely used learning algorithms today. Here are some examples of classification problems. Earlier we talked about email spam classification as an example of a classification problem. Another example would be classifying online transactions. So if you have a website that sells stuff, and if you want to know if a particular transaction is fraudulent or not, whether someone has, is using a stolen credit card or has stolen the user's password, that's another classification problem. And earlier we also talked about the example of classifying tumors as cancerous, malignant, or as benign tumors. In all of these problems, the variable that we're trying to predict is a variable y that we can think of as taking on two values, either 0 or 1, either spam or not spam, fraudulent or not fraudulent, malignant or benign. Another name for the class that we denote with 0 is the negative class, and another name for the class that we denote with 1 is the positive class. So 0 may denote the benign tumor, and 1 positive class may denote a malignant tumor. The assignment of the two classes, spam, not spam, and so on, the assignment of the two classes to positive and negative, to 0 and 1, is somewhat arbitrary, and it doesn't really matter. But often there is this intuition that the negative class is conveying the absence of something, like the absence of a malignant tumor, whereas 1, the positive class, is conveying the presence of something that we may be looking for. But the designation of which is negative and which is positive is somewhat arbitrary, and it doesn't matter that much. For now, we're going to start with classification problems with just two classes, 0 and 1. Later on, we'll talk about multi-class problems as well, where the variable y may take on, say, 4 values, 0, 1, 2, and 3. This is called a multi-class classification problem. But for the next few videos, let's start with the two-class or the binary classification problem, and we'll worry about the multi-class setting later. So how do we develop a classification algorithm? Here's an example of a training set for a classification task. for classifying a tumor as malignant or benign. And notice that malignancy takes on only two values, 0 or no, 1 or yes. So one thing we could do, given this training set, is to apply the algorithm that we already know, linear regression, to this data set and just try to fit a straight line to this data. So if you take this training set and fit a straight line to it, maybe you get a hypothesis that looks like that, right? So that's my hypothesis, h of x equals theta transpose x. If you want to make predictions, one thing you could try doing is then threshold the classifier output at 0.5, that is at the vertical axis value 0.5. And if the hypothesis outputs a value that is greater than or equal to 0.5, you predict y equals 1. If it's less than 0.5, you predict y equals 0. Let's see what happens if we do that. So let's take 0.5, and so, that's where the threshold is, and thus, using linear regression this way, everything to the right of this point, we would end up predicting as the positive class because the output values is greater than 0.5 on the vertical axis, and everything to the left of that point, we will end up predicting as a negative value. In this particular example, it looks like linear regression is actually doing something reasonable, even though this is a classification task we're interested in. But now let's try changing the problem a bit. Let me extend out the horizontal axis a little bit, and let's say we got one more training example way out there on the right. Notice that that additional training example, this one out here, it doesn't actually change anything, right? It's, looking at the training set, it's pretty clear what a good hypothesis is. It's that, well, everything to the right of somewhere around here, to the right of this, we should predict as positive, and everything to the left, we should probably predict as negative, because from this training set, it looks like all the tumors larger than, a certain value around here are malignant, and all the tumors smaller than that are not malignant, at least for this training set. But once we've added that extra example out here, if you now run linear regression, you will instead get a straight line fit to the data that might maybe look like this. And if you now threshold this hypothesis at 0.5, you end up with a threshold that's around here, so that everything to the right of this point you predict as positive, and everything to the left of that point you predict as negative. And this seems a pretty bad thing for linear regression to have done, right? Because, these are our positive examples, these are our negative examples. It's pretty clear we really should be separating the two classes somewhere around there. But somehow, by adding one example way out here to the right, this example really isn't giving us any new information. I mean, it should be no surprise to the learning algorithm that the example way out here turns out to be malignant. But somehow, adding that example out there caused linear regression to change its straight line fit to the data from this magenta line out here to this blue line over here, and caused it to give us a worse hypothesis. So applying linear regression to a classification problem usually isn't, or often isn't, a great idea. In the first instance, in the first example, before I added this extra training example, previously, linear regression was just getting lucky, and it got us a hypothesis that, worked well for that particular example. But usually, applying linear regression to a data set, you might get lucky, but often it isn't a good idea. So I wouldn't use linear regression for classification problems. Here's one other funny thing about what would happen if we were to use linear regression for a classification problem. For classification, we know that y is either 0 or 1, but if you are using linear regression, well, the hypothesis can output values that are much larger than 1 or less than 0, even if all of your training examples have labels y equals 0 or 1. And it seems kind of strange that even though we know that the labels should be 0 or 1, it seems kind of strange if the algorithm can output values much larger than 1 or much smaller than 0. So what we'll do in the next few videos is develop an algorithm called logistic regression, which has the property that the output, the predictions of logistic regression, are always between 0 and 1 and doesn't become bigger than 1 or become less than 0. And by the way, logistic regression is, and we will use it as a classification algorithm, is maybe sometimes confusing that the term regression appears in his name, even though logistic regression is actually a classification algorithm, but that's just the name it was given for historical reasons. So don't be confused by that. Logistic regression is actually a classification algorithm that we apply to settings where the label y is discrete valued when it's either 0 or 1. So hopefully you now know why, if you have a classification problem, using linear regression isn't a good idea. In the next video, we'll start working out the details of the logistic regression algorithm. Let's start talking about logistic regression. In this video, I'd like to show you the hypothesis representation. That is, what is the function we're going to use to represent our hypothesis when we have a classification problem. Earlier, we said that we would like our classifier to output values that are between 0 and 1. So we like to come up with a hypothesis that satisfies this property, that its predictions are maybe between 0 and 1. When we were using linear regression, this was the form of a hypothesis where h of x is theta transpose x. For logistic regression, I'm going to modify this a little bit and make the hypothesis g of theta transpose x, where I'm going to define the function g as follows. G of z, if z is a real number, is equal to 1 over 1 plus e to the negative z. This is called the sigmoid function or the logistic function, and the term logistic function, that's what gives rise to the name logistic regression. And by the way, the terms sigmoid function and logistic function are basically synonyms and mean the same thing. So the two terms are basically interchangeable, and either term can be used to refer to this function g. And if we take these two equations and put them together, then here's just an alternative way of writing out the form of my hypothesis. I'm saying that h of x is 1 over 1 plus e to the negative theta transpose x. And all I've done is I've taken this variable z here is a real number, and plugged in theta transpose x. So I end up with, theta transpose x in place of z there. Lastly, let me show you what the sigmoid function looks like. I'm going to plot it on this figure here. The sigmoid function, g of z, also called the logistic function, it looks like this. It starts off near 0, and then it rises until it crosses 0.5 at the origin, and then it flattens out again like so. So that's what the sigmoid function looks like. And you notice that the sigmoid function, well, it asymptotes at 1, and it asymptotes at 0 as z, I guess the horizontal axis is z. As z goes to minus infinity, g of z approaches 0. And as g of z approaches infinity, g of z approaches 1. And so because g of z outputs values that are between 0 and 1, we also have that h of x must be between 0 and 1. Finally, given this hypothesis representation, what we need to do, as before, is fit the parameters theta to our data. So given a training set, we need to pick a value for the parameters theta, and this hypothesis will then let us make predictions. We'll talk about a learning algorithm later for fitting the parameters theta. But first, let's talk a bit about the interpretation of this model. Here's how I'm going to interpret the output of my hypothesis, h of x. When my hypothesis outputs some number, I am going to treat that number as the estimated probability that y is equal to 1 on a new input, example x. Here's what I mean. Here's an example. Let's say we're using the tumor classification example. So we may have a feature vector x, which is this x0 equals 1 as always, and then our one feature is the size of the tumor. Suppose I have a patient come in and they have some tumor size, and I feed their feature vector x into my hypothesis, and suppose my hypothesis outputs the number 0.7. I'm going to interpret my hypothesis as follows. I'm going to say that this hypothesis is telling me that for a patient with features x, the probability that y equals 1 is 0.7. In other words, I'm going to tell my patient that that tumor, sadly, has a 70% chance or a 0.7 chance of being malignant. To write this out slightly more formally, or to write this out in math, I'm going to interpret my hypothesis output as P of y equals 1 given x parameterized by theta. So for those of you that are familiar with probability, this equation may make sense. If you're a little less familiar with probability, here's how I read this expression. This is the probability that y is equal to 1 given x, sort of given that my patient has features x, or given my patient has a particular tumor size represented by my features x, and this probability is parameterized by theta. So I'm basically going to count on my hypothesis to give me estimates of the probability that y is equal to 1. Now, since this is a classification task, we know that y must be either 0 or 1, right? Those are the only two values that y could possibly take on, either in the training set or for new patients that may walk into my office or into the doctor's office in the future. So given h of x, we can therefore compute the probability that y is equal to 0 as well. Concretely, because y must be either 0 or 1, we know that the probability of y equals 0 plus the probability of y equals 1 must add up to 1. This first equation looks a little bit more complicated, but it's basically saying that probability of y equals 0 for a particular patient with features x, and given our parameters theta, plus the probability of y equals 1 for that same patient with features x, and given our parameters theta, must add up to 1. If this equation looks a little bit complicated, feel free to mentally imagine it without that x and theta. And this is just saying that the probability of y equals 0 plus the probability of y equals 1 must be equal to 1. And we know this to be true because y has to be either 0 or 1. And so the chance of y being equal to 0 plus the chance that y is 1, those two must add up to 1. And so if you just take this term and move it to the right-hand side, then you end up with this equation. It says probability of y equals 0 is 1 minus probability of y equals 1. And thus, if our hypothesis, if h of x gives us that term, you can therefore quite simply compute the probability, or compute the estimated probability that y is equal to 0 as well. So you now know what the hypothesis representation is for logistic regression. And we've seen what the mathematical formula is defining the hypothesis for logistic regression. In the next video, I'd like to try to give you better intuition about what the hypothesis function looks like. And I want to tell you about something called the decision boundary, and we'll look at some visualizations together to try to get a better sense of what this hypothesis function of logistic regression really looks like. In the last video, we talked about the hypothesis representation for logistic regression. What I'd like to do now is tell you about something called the decision boundary, and this will give us a better sense of what the logistic regression's hypothesis function is computing. To recap, this is what we wrote out last time, where we said that the hypothesis is represented as h of x equals g of theta transpose x, where g is this function called the sigmoid function, which looks like this. So it slowly increases from 0 to 1, asymptoting at 1. What I want to do now is try to understand better when this hypothesis will make predictions that y is equal to 1 versus when it might make predictions that y is equal to 0, and understand better what the hypothesis function looks like, particularly when we have more than one feature. Concretely, this hypothesis is outputting estimates of the probability that y is equal to 1, given x and parameterized by theta. So if we wanted to predict is y equal to 1 or is y equal to 0, here's something we might do. Whenever the hypothesis outputs that the probability of y being 1 is greater than or equal to 0.5, so this means that if it's more likely to be y equals 1 than y equals 0, then let's predict y equals 1. And otherwise, if the estimated probability of y being equal to 1 is less than 0.5, then let's predict y equals 0. And I chose a greater than or equal to here and a less than here. If h of x is equal to 0.5 exactly, then we could predict positive or negative, but I put a greater than or equal to 2 here, so we default maybe to predicting positive if h of x is 0.5, but that's a detail that really doesn't matter that much. What I want to do is understand better when is it exactly that h of x will be greater than or equal to 0.5 so that we'll end up predicting y is equal to 1. If we look at this plot of the sigmoid function, we'll notice that the sigmoid function g of z is greater than or equal to 0.5 whenever z is greater than or equal to 0. So it's in this half of the figure that g takes on values that are 0.5 and higher, right? Because this notch here, that's the 0.5. And so when z is positive, g of z, the sigmoid function, is greater than or equal to 0.5. Since the hypothesis for logistic regression is h of x equals g of theta transpose x, this is therefore going to be greater than or equal to 0.5 whenever theta transpose x is greater than or equal to 0. So what we've shown, right, because here theta transpose x takes the row of z. So what we've shown is that our hypothesis is going to predict y equals 1 whenever theta transpose x is greater than or equal to 0. Let's now consider the other case of when our hypothesis will predict y is equal to 0. Well, by a similar argument, h of x is going to be less than 0.5 whenever g of z is less than 0.5, because the range of values of z that cause g of z to take on values less than 0.5, well, that's when z is negative. So when g of z is less than 0.5, our hypothesis will predict that y is equal to 0. And by a similar argument to what we had earlier, h of x is equal to g of theta transpose x, and so we'll predict y equals 0 whenever this quantity theta transpose x is less than 0. To summarize what we just worked out, we saw that if we decide to predict whether y is equal to 1 or y is equal to 0, depending on whether the estimated probability is greater than or equal to 0.5 or whether it's less than 0.5, then that's the same as saying that we'll predict y equals 1 whenever theta transpose x is greater than or equal to 0, and we'll predict y is equal to 0 whenever theta transpose x is less than 0. Let's use this to better understand how the hypothesis of logistic regression makes its predictions. Now, let's suppose we have a training set like that shown on this slide. And suppose our hypothesis is h of x equals g of theta 0 plus theta 1 x1 plus theta 2 x2. We haven't talked yet about how to fit the parameters of this model. We'll talk about that in the next video. But suppose that via a procedure to be specified, we end up choosing the following values for the parameters. Let's say we choose theta 0 equals 3, theta 1 equals 1, theta 2 equals 1. So this means that my parameter vector is going to be theta equals minus 3, 1, 1. So given this choice of my hypothesis parameters, let's try to figure out where our hypothesis would end up predicting y equals 1 and where it would end up predicting y equals 0. Using the formulas that we worked out on the previous slide, we know that y equals 1 is more likely, that is, the probability that y equals 1 is greater than 0.5 or greater than or equal to 0.5 whenever theta transpose x is greater than 0. And this formula that I just underlined, minus 3 plus x1 plus x2, is, of course, theta transpose x when theta is equal to this value of the parameters that we just chose. So for any example with features x1 and x2 that satisfy this equation, that minus 3 plus x1 plus x2 is greater than or equal to 0, our hypothesis will think that y equals 1 is more likely, or will predict that y is equal to 1. We can also take minus 3 and bring this to the right and rewrite this as x1 plus x2 is greater than or equal to 3. And so equivalently, we've found that this hypothesis will predict y equals 1 whenever x1 plus x2 is greater than or equal to 3. Let's see what that means on the figure. if I write down the equation x1 plus x2 equals 3, this defines the equation of a straight line. And if I draw what that straight line looks like, it gives me the following line, which passes through 3 and 3 on the x1 and the x2 axes. So the part of the input space, the part of the x1, x2 plane that corresponds to when x1 plus x2 is greater than or equal to 3, that's going to be this right half plane. That is everything to the up and everything to the upper right portion of this magenta line that I just drew. And so the region where our hypothesis will predict y equals 1 is this region, is really this huge region, this half space over to the upper right. And let me just write that down. I'm going to call this the y equals 1 region. And in contrast, the region where x1 plus x2 is less than 3, that's when we will predict that y is equal to 0. And that corresponds to this region. It's really a half plane, but that region on the left is the region where our hypothesis will predict y equals 0. I want to give this line, this magenta line that I drew, a name. This line there is called the decision boundary. And concretely, this straight line, x1 plus x2 equals 3, that corresponds to the setter point. So that corresponds to the region where h of x is equal to 0.5 exactly. And the decision boundary, that is this straight line, that's the line that separates the region where the hypothesis predicts y equals 1 from the region where the hypothesis predicts that y is equal to 0. And just to be clear, the decision boundary is a property of the hypothesis, including the parameters theta 0, theta 1, theta 2. And in the figure, I drew a training set, I drew a data set in order to help the visualization. But even if we take away the data set, this decision boundary and the region where we predict y equals 1 versus y equals 0, that's a property of the hypothesis and of the parameters of the hypothesis, and not a property of the data set. Later on, of course, we'll talk about how to fit the parameters, and there we'll end up using the training set, using our data to determine the value of the parameters. But once we have particular values for the parameters, theta 0, theta 1, theta 2, then that completely defines the decision boundary, and we don't actually need to plot a training set in order to plot the decision boundary. Let's now look at a more complex example where, as usual, I have crosses to denote my positive examples and O's to denote my negative examples. Given a training set like this, how can I get logistic regression to fit this sort of data? Earlier, when we were talking about polynomial regression, or when we were talking about linear regression, we talked about how we can add extra higher order polynomial terms to the features, and we can do the same for logistic regression. Concretely, let's say my hypothesis looks like this, where I've added 2 extra features, x1 squared and x2 squared, to my features, so that I now have 5 parameters, theta 0 through theta 4. As before, we'll defer to the next video, our discussion on how to automatically choose values for the parameters theta 0 through theta 4. But let's say that via procedure to be specified, I end up choosing theta 0 equals minus 1, theta 1 equals 0, theta 2 equals 0, theta 3 equals 1, and theta 4 equals 1. What this means is that with this particular choice of parameters, my parameter vector theta looks like minus 1, 0, 0, 1, 1. Following our earlier discussion, this means that my hypothesis will predict that y is equal to 1 whenever minus 1 plus x1 squared plus x2 squared is greater than or equal to 0. This is whenever theta transpose times my theta transpose my features is greater than or equal to 0. And if I take minus 1 and just bring this to the right, I'm saying that my hypothesis will predict that y is equal to 1 whenever x1 squared plus x2 squared is greater than or equal to 1. So what does this decision boundary look like? Well, if you were to plot the curve for x1 squared plus x2 squared equals 1, some of you will recognize that that is the equation for a circle of radius 1 centered around the origin. So that is my decision boundary. And everything outside the circle, I'm going to predict as y equals 1. So out here is my y equals 1 region. I'm going to predict y equals 1 out here. And inside the circle is where I'll predict y is equal to 0. So by adding these more complex or these polynomial terms to my features as well, I can get more complex decision boundaries that don't just try to separate the positive and negative examples of a straight line, but I can get, in this example, a decision boundary that's a circle. Once again, the decision boundary is a property not of the training set, but of the hypothesis and of the parameters. So long as we're given my parameter vector theta, that defines the decision boundary, which is the circle. But the training set is not what we use to define the decision boundary. The training set may be used to fit the parameters theta. We'll talk about how to do that later. But once you have the parameters theta, that is what defines the decision boundary. Let me put back the training set just for visualization. And finally, let's look at a more complex example. So can we come up with even more complex decision boundaries than this? If I have even higher order polynomial terms, so things like x1 squared, x1 squared x2, x1 squared x2 squared, and so on. If I have much higher order polynomials, then it's possible to show that you can get even more complex decision boundaries, and logistic regression can be used to find decision boundaries that may, for example, be an ellipse like that, or maybe with a different setting of the parameters. Maybe you can get instead a different decision boundary, which may even look like, some funny shape like that. Or for even more complex examples, maybe you can also get decision boundaries that could look like, more complex shapes like that, where everything in here you predict y equals 1, and everything outside you predict y equals 0. So these higher order polynomial features, you can get very complex decision boundaries. So with these visualizations, I hope that gives you a sense of what's the range of hypothesis functions we can represent using the representation that we have for logistic regression. Now that we know what h of x can represent, what I'd like to do next in the following video is talk about how to automatically choose the parameters theta so that given a training set, we can automatically fit the parameters to our data. In this video, we'll talk about how to fit the parameters theta for logistic regression. In particular, I'd like to define the optimization objective, or the cost function, that we'll use to fit the parameters. Here's the supervised learning problem of fitting a logistic regression model. We have a training set of m training examples, and as usual, each of our examples is represented via a feature vector that's n plus 1 dimensional. And as usual, we have x0 equals 1, our first feature, or our 0 feature is always equal to 1. And because this is a classification problem, our training set has the property that every label y is either 0 or 1. This is our hypothesis, and the parameters of the hypothesis is this theta over here. And the question I want to talk about is, given this training set, how do we choose or how do we fit the parameters theta? Back when we were developing the linear regression model, we used the following cost function. I've written this slightly differently, where instead of 1 over 2m, I've taken the 1/2 and put it inside the summation instead. Now, I want to use an alternative way of writing out this cost function, which is that instead of writing out the squared error term here, let's write in here cost of h of x, comma y, and I'm going to define that term, cost of h of x, comma y, to be equal to this. It's just equal to this 1/2 of the squared error. So now we can see more clearly that the cost function is a sum over my training set, or is 1 over m times the sum over my training set of this cost term here. And to simplify this equation a little bit more, it's going to be convenient to get rid of those superscripts. So just define cos of h of x comma y to be equal to 1/2 of the squared error. And the interpretation of this cost function is that this is the cost I want my learning algorithm to, have to pay if it outputs that value, if its prediction is h of x and the actual label was y. So let's just cross off those superscripts, right? And no surprise for linear regression, the cost we've defined is that, well, the cost for this is that is 1/2 times the square difference between what it predicted and the actual value that we observed for y. Now, this cost function worked fine for linear regression, but here we're interested in logistic regression. If we could minimize this cost function that is plugged into J here, that would work okay. But it turns out that if we use this particular cost function, this would be a non-convex function of the parameters theta. Here's what I mean by non-convex. We have some cost function j of theta, and for logistic regression, this function h here has a nonlinearity, right? It says, 1/1 plus e to the negative theta transpose x. So this is a pretty complicated nonlinear function. And if you take this sigmoid function, plug it in here, and then take this cost function and plug it in there, and then plot what j of theta looks like, you find that j of theta can look like a function that's like this, with many local optima. And the formal term for this is that this is a non-convex function. And you can kind of tell, if you were to run gradient descent on this sort of function, it is not guaranteed to converge to the global minimum. Whereas in contrast, what we would like is to have a cost function j of theta that is convex, that is a single bow-shaped function that looks like this, so that if you run gradient descent, we would be guaranteed that gradient descent would converge to the global minimum. And the problem with using the squared cost function is that because of this very nonlinear sigmoid function that appears in the middle here, j of theta ends up being a non-convex function if you were to define it as the squared cost function. So what we'd like to do is to instead come up with a different cost function that is convex, and so that we can apply a great algorithm like gradient descent and be guaranteed to find the global minimum. Here's the cost function that we're going to use for logistic regression. We're going to say that the cost or the penalty that the algorithm pays if it outputs the value h of x, so if this is some number like 0.7, right? But if it predicts the value h of x and the actual clause label turns out to be y, the cost is going to be minus log h of x if y is equal to 1, and minus log 1 minus h of x if y is equal to 0. This looks like a pretty complicated function, but let's plot this function to gain some intuition about what it's doing. Let's start off with the case of y equals 1. If y is equal to 1, then the cost function is minus log h of x. And if we plot that, so let's say that the horizontal axis is h of x, so we know that our hypothesis is going to output a value between 0 and 1. Right? So h of x that varies between 0 and 1. If you plot what this cost function looks like, you find that it looks like this. One way to see why the plot looks like this is because if you were to plot log z with z on the horizontal axis, then that looks like that, and it sort of approaches minus infinity, right? So this is what the log function looks like. And this is 0, this is 1. Here, z is, of course, playing the role of h of x. And so minus log z will look like this, right? Just flipping the sign, minus log z. And we're interested only in the range of when this function goes between 0 and 1. So get rid of that. And so we're just left with, this part of the curve. And that's what this curve on the left looks like. Now, this cost function has a few interesting and desirable properties. First, you notice that if y is equal to 1 and h of x is equal to 1, in other words, if the hypothesis exactly predicts h equals 1 and y is exactly equal to what it predicted, then the cost is equal to 0, right? That corresponds to the curve doesn't actually flatten out. The curve is still going. First, notice that if h of x equals 1, if the hypothesis predicts that y is equal to 1 And if indeed y is equal to 1, then the cost is equal to 0. That corresponds to this point down here, right? If h of x is equal to 1, and we're only considering the case that y equals 1 here, but if h of x is equal to 1, then the cost is down here, is equal to 0. And that's what we'd like it to be, because if we correctly predict the output y, then the cost is 0. But now notice also that as h of x approaches 0, so as the output of a hypothesis approaches 0, the cost blows up and it goes to infinity. And what this does is this captures the intuition that if a hypothesis outputs 0, that's like saying a hypothesis saying the chance of y equals 1 is equal to 0. It's kind of like going to a medical patient and saying the probability that you have a malignant tumor, the probability that y equals 1, is 0. So it's like absolutely impossible that your tumor is malignant. But if it turns out that the patient's tumor actually is malignant, so if y is equal to 1, even after we told them that the probability of it happening is 0, so it's absolutely impossible for it to be malignant. But if we told them this with that level of certainty and we turn out to be wrong, then we penalize the learning algorithm by a very, very large cost. And that's captured by having this cost go to infinity if y equals 1 and h of x approaches 0. This slide considered the case of y equals 1. Let's look at what the cost function looks like for y equals 0. If y is equal to 0, then the cost looks like this. It looks like this expression over here. And if you plot the function minus log 1 minus z, what you get is the cost function actually looks like this. So it goes from 0 to 1, something like that. And so if you plot the cost function for the case of y equals 0, you find that it looks like this. And what this curve does is it now blows up and goes to plus infinity as h of x goes to 1, because it's saying that if y turns out to be equal to 0, but we predicted that y is equal to 1 with almost certainty, with probably 1, then we end up paying a very large cost. Let's plot the cost function for the case of y equals 0. So if y equals 0, that's going to be our cost function. If you look at this expression, and if you plot minus log 1 minus z, if you figure out what that looks like, you get a figure that looks like this, which goes from 0 to 1 with the z-axis on the horizontal axis. So if you take this cost function and plot it for the case of y equals 0, what you get is that the cost function looks like this. And what this cost function does is that it blows up, or it goes to a positive infinity as h of x goes to 1. And this captures the intuition that if a hypothesis predicted that h of x is equal to 1 with certainty, with like probably 1, it's absolutely got to be y equals 1. But if y turned out to be equal to 0, then it makes sense to make the hypothesis or make the learning algorithm pay a very large cost. And conversely, if h of x is equal to 0 and y equals 0, then a hypothesis nailed it. It predicted y is equal to 0, and it turns out y is equal to 0. So at this point, the cost function is going to be 0. In this video, we've defined the cost function for a single training example. The topic of convexity analysis is beyond the scope of this course, but it is possible to show that with our particular choice of cost function, this would give us a convex optimization problem. As our cost function, our overall cost function j of theta will be convex and local optima free. In the next video, we're going to take these ideas of the cost function for a single training example and develop that further and define the cost function for the entire training set. And we'll also figure out a simpler way to write it than we have been using so far. And based on that, we'll work out gradient descent, and that will give us our logistic regression algorithm. In this video, we'll figure out a slightly simpler way to write the cost function than we have been using so far. And we'll also figure out how to apply gradient descent to fit the parameters of logistic regression. So by the end of this video, you know how to implement a fully working version of logistic regression. Here's our cost function for logistic regression. Our overall cost function is 1 over m times sum over the training set of the cost of making different predictions on the different examples with labels yi. And this was the cost for a single example that we worked out earlier. And just want to remind you that for classification problems in our training sets, and in fact, even for examples not in our training set, y is always equal to 0 or 1, right? That's sort of part of the mathematical definition of y. Because y is either 0 or 1, we'll be able to come up with a simpler way to write this cost function. And in particular, rather than writing out this cost function on 2 separate lines with 2 separate cases for y equals 1 and y equals 0, I'm going to show you a way to take these 2 lines and compress them into one equation. And this will make it more convenient to write out a cost function and derive gradient descent. Concretely, we can write out the cost function as follows. We'll say that cost of h of x comma y, I'm going to write this as minus y times log h of x minus 1 minus y times log 1 minus h of x. And I'll show you in a second that this expression or this equation is a equivalent way or more compact way of writing out this definition of the cost function that we had up here. Let's see why that's the case. We know that there are only 2 possible cases. Y must be 0 or y or 1. So let's suppose y equals 1. If y is equal to 1, then this equation is saying that the cost is equal to, well, if y is equal to 1, then this thing here is equal to 1, and 1 minus y is going to be equal to 0, right? So if y is equal to 1, then 1 minus y is 1 minus 1, which is therefore 0. So the second term gets multiplied by 0 and goes away, and we're left with only this first term, which is y times log minus y times log h of x. Y is 1, so that's equal to minus log h of x. And this equation is exactly what we have up here for if y is equal to 1. The other case is if y is equal to 0. And if that's the case, then our writing of the cost function is saying that, well, if y is equal to 0, then this term here would be equal to 0, whereas 1 minus y, if y is equal to 0, would be equal to 1, because 1 minus y becomes 1 minus 0, which is just equal to 1. And so the cost function simplifies to just this last term here, right? Because the first term over here gets multiplied by 0 and so disappears, so we're just left with this last term, which is minus log 1 minus h of x. And you can verify that this term here is just exactly what we had for when y is equal to 0. So this shows that this definition for the cost is just a more compact way of taking both of these expressions, the cases y equals 1 and y equals 0, and writing them in a more convenient form with just one line. We can therefore write out our cost function for logistic regression as follows. It is this 1 over m of the sum of these cost functions, and plugging in the definition for the cost that we worked out earlier, we end up with this, and it just brought the minus sign outside. And why did we choose this particular function? Well, it looks like there could be other cost functions we could have chosen. Although I won't have time to go into great detail of this in this course, this cost function can be derived from statistics using the principle of maximum likelihood estimation, which is an idea in statistics for how to efficiently find parameters theta for different models. And it also has a nice property that it is convex. So this is the cost function that essentially everyone uses when fitting logistic regression models. If you don't understand the terms that I just said, if you don't know what the principle of maximum likelihood estimation is, don't worry about it, but there's just a deeper rationale and justification behind this particular cost function than I have time to go into in this class. Given this cost function, in order to fit the parameters, what we're going to do then is try to find the parameters theta that minimize j of theta. So if we try to minimize this would give us some set of parameters theta. Finally, if we're given a new example with some set of features x, we can then take the thetas that we fit to our training set and output our prediction as this. And just to remind you, the output of my hypothesis I'm going to interpret as the probability that y is equal to 1. And this is given the input x and parameterized by theta. But just think of this as just my hypothesis is estimating the probability that y is equal to 1. So all that remains to be done is figure out how to actually minimize j of theta as a function of theta so that we can actually fit the parameters to our training set. The way we're going to minimize the cost function is using gradient descent. Here's our cost function, and if we want to minimize it as a function of theta, here's our usual template for gradient descent, where we repeatedly update each parameter by updating it as itself minus the learning rate alpha times this derivative term. If you know some calculus, feel free to take this term and try to compute the derivative yourself and see if you can simplify it to the same answer that I get. But even if you don't know calculus, don't worry about it. If you actually compute this, what you get is this equation, and I'll just write it out here, is sum from I equals 1 through m of essentially the error times xij. So if you take this partial derivative term and plug it back in here, we can then write out our gradient descent algorithm as follows. And all I've done is I took the derivative term from the previous slide and plugged it in there. So if you have n features, you would have, a parameter vector theta, which with parameters theta 0, theta 1, theta 2, down to theta n, and you would use this update to simultaneously update all of your values of theta. Now, if you take this update rule and compare it to what we were doing for linear regression, you might be surprised to realize that, well, this equation was exactly what we had for linear regression. In fact, if you look in the earlier videos and look at the update rule, the gradient descent rule for linear regression, it looked exactly like what I drew here inside the blue box. So are linear regression and logistic regression different algorithms or not? Well, this is resolved by observing that for logistic regression, what has changed is that the definition for this hypothesis has changed. So whereas for linear regression, we had h of x equals theta transpose x, now the definition of h of x has changed and is instead now 1 over 1 plus e to the negative theta transpose x. So even though the update rule looks cosmetically identical because the definition of the hypothesis has changed, this is actually not the same thing as gradient descent for linear regression. In an earlier video, when we were talking about gradient descent for linear regression, we had talked about how to monitor gradient descent to make sure that it is converging. I usually apply that same method to logistic regression too, to monitor gradient descent to make sure it's converging correctly, and hopefully you can figure out how to apply that technique to logistic regression yourself. When implementing logistic regression with gradient descent, we have all of these different parameter values, theta 0 down to theta n that we need to update using this expression. And one thing we could do is have a for loop. So for I equals 0 to n, or for I equals 1 to n plus 1, to update each of these parameter values in turn. But of course, rather than using a for loop, ideally we would also use a vectorized implementation. And so that a vectorized implementation can update all of these n plus 1 parameters all in one fell swoop. And to check your own understanding, you might see if you can figure out how to do the vectorized implementation of this algorithm as well. So now you know how to implement gradient descent for logistic regression. There was one last idea that we had talked about earlier for linear regression, which was feature scaling. We saw how feature scaling can help gradient descent converge faster for linear regression. The idea of feature scaling also applies to gradient descent for logistic regression, and if you have features that are on very different scales, then applying feature scaling can also make gradient descent run faster for logistic regression. So that's it. You now know how to implement logistic regression, and this is a very powerful and probably the most widely used classification algorithm in the world, and you now know how to get to work for yourself. In the last video, we talked about gradient descent for minimizing the cost function j of theta for logistic regression. In this video, I'd like to tell you about some advanced optimization algorithms and some advanced optimization concepts. Using some of these ideas, we'll be able to get logistic regression to run much more quickly than is possible with gradient descent, and this will also let the algorithms scale much better to very large machine learning problems, such as if we have a very large number of features. Here's an alternative view of what gradient descent is doing. We have some cost function j, and we want to minimize it. So what we need to do is we need to write code that can take as input the parameters theta, and that can compute two things, j of theta and these partial derivative terms for j equals 0, 1, up to n. Given code that can do these two things, what gradient descent does is it repeatedly performs the following update, right? So given the code that we wrote to compute these partial derivatives, gradient descent plugs us in here and uses that to update our parameters theta. So another way of thinking about gradient descent is that we need to supply code to compute j of theta and these derivatives, and then these get plugged into gradient descent, which can then try to minimize the function for us. For gradient descent, I guess technically you don't actually need code to compute the cost function j of theta. You only need code to compute the derivative terms. But if you think of your code as also monitoring convergence or some such, we'll just think of ourselves as providing code to compute both the cost function and the derivative terms. So, having written code to compute these two things, one algorithm we can use is gradient descent. But gradient descent isn't the only algorithm we can use, and there are other algorithms, more advanced, more sophisticated ones, that if we only provide them a way to compute these two things, then these are different approaches to optimize the cost function for us. So conjugate gradient, BFGS, and LBFGS are examples of more sophisticated optimization algorithms that need a way to compute j of theta and need a way to compute the derivatives, and can then use more sophisticated strategies than gradient descent to minimize the cost function. The details of exactly what these three algorithms do is well beyond the scope of this course, and in fact, you often end up spending many days or a small number of weeks studying these algorithms if you take a class in advanced numerical computing. But let me just tell you about some of their properties. These three algorithms have a number of advantages. One is that with any of these algorithms, you usually do not need to manually pick the learning rate alpha. So one way to think of these algorithms is that given the way to compute the derivative and the cost function, you can think of these algorithms as having a clever inner loop. And in fact, they have a clever inner loop called a line search algorithm that automatically tries out different values for the learning rate alpha and automatically picks a good learning rate alpha, so that it can even pick a different learning rate for every iteration. And so then you don't need to choose it yourself. These algorithms actually do more sophisticated things than just pick a good learning rate, and so they often end up converging much faster than gradient descent. These algorithms actually do more sophisticated things than just pick a good learning rate, and so they often end up converging much faster than gradient descent, but a detailed discussion of exactly what they do is beyond the scope of this course. In fact, I actually have used these algorithms for a long time, like maybe over a decade, quite frequently. And it was only a few years ago that I actually figured out for myself the details of what conjugate gradient, BFGS, and LBFGS do. So it is actually entirely possible to use these algorithms successfully and apply to lots of different learning problems without actually understanding the inner loop of what these algorithms do. If these algorithms have a disadvantage, I'd say that the main disadvantage is that they're quite a lot more complex than gradient descent. And in particular, you probably should not implement these algorithms, conjugate gradient, LBFGS, BFGS, yourself, unless you're an expert in numerical computing. Instead, just as I wouldn't recommend that you write your own code to compute square roots of numbers or to compute inverses of matrices, for these algorithms also, what I would recommend you do is just use a software library. So, to take a square root, what all of us do is use some function that someone else has written to compute the square roots of our numbers. And fortunately, Octave and the closely related language MATLAB, if you're using that, Octave has a very good, has a pretty reasonable library implementing some of these advanced optimization algorithms. And so if you just use the built-in library, you get pretty good results. I should say that there is a difference between good and bad implementations of these algorithms. And so if you're using a different language for your machine learning application, if you're using like C, C++, Java, and so on, you might want to try out a couple different libraries to make sure that you find a good library for implementing these algorithms, because there is a difference in performance between a good implementation of conjugate gradient or LBFGS versus a less good implementation of conjugate gradient or LBFGS. So now let's explain how to use these algorithms. I'm going to do so with an example. Let's say that you have a problem with two parameters, or theta equals theta 0 and theta 1. And let's say your cost function is j of theta equals theta 1 minus phi squared plus theta 2 minus phi squared. So with this cost function, the value for theta 1 and theta 2, if you want to minimize j of theta as a function of theta, the value that minimizes it is going to be theta 1 equals 5, theta 2 equals 5. Now, again, I know some of you know more calculus than others, but the derivatives of the cost function j turn out to be these two expressions down here, so I've done the calculus. So if you want to apply one of the advanced optimization algorithms to minimize this cost function j, so if we didn't know the minimum was at 5, but if you want to have a cost function, find the minimum numerically, right, using something like gradient descent, but preferably more advanced than gradient descent, what you would do is implement an octave function like this. So we implement a cost function theta function like that. And what this does is it returns two arguments. The first, jval, is how we would compute the cost function j. And so this says jval equals theta 1 minus phi squared plus theta 2 minus phi squared. So it's just computing this cost function over here. And the second argument that this function returns is gradient. So gradient is going to be a 2×1 vector. And the two elements of the gradient vector correspond to the two partial derivative terms over here. Having implemented this cost function, you can then call the advanced optimization function called fminunc. It stands for function minimization unconstrained in Octave. And the way you call this is follows. You set a few options. This is options is a data structure that stores the options you want. So grad on, this sets the gradient objective parameter to on. It just means that you are indeed going to provide a gradient to this algorithm, and we're going to set the maximum number of iterations to, let's say, 100. We're going to give it an initial guess for theta. This is a 2×1 vector, and then this command calls fminunc. This @ symbol represents a pointer to the cost function that we just defined up there. And if you call this will compute. We'll use one of the more advanced optimization algorithms. And if you want, think of it as just like gradient descent, but automatically choosing the learning rate alpha for you, so you don't have to do so yourself. But it will then attempt to use these sort of advanced optimization algorithms like gradient descent on steroids to try to find the optimal value of theta for you. Let me actually show you what this looks like in Octave. So I've written this cost function of theta function exactly as we had it on the previous slide. It computes jval, which is the cost function, and it computes the gradient with the two elements being the partial derivatives of the cost function with respect to the two parameters theta 1 and theta 2. Now let's switch to my Octave window. I'm going to type in those commands that I had just now. So options equals optimset. This is the notation for setting my parameters or my options for my optimization algorithm. Grad option on, max iter 100, so that says 100 iterations, and I am going to provide the gradient to my algorithm. Let's say initial theta equals 0's 2×1, so that's my initial guess for theta. And now I have op theta function val exit flag equals fmin unconstrained, a pointer to the cost function, and provide my initial guess and the options, like so. and if I hit enter, this will run the optimization algorithm. And it returns pretty quickly. Oh, this funny formatting, that's because my line, my code wrapped around. But so this funny thing is just because my command line had wrapped around. But what this says is that it numerically ran this, think of it as gradient descent on steroids, and it found the optimal value for theta is theta 1 equals 5, theta 2 equals 5, exactly as we're hoping for. The function value at the optimum is essentially 10 to the minus 30, so that's essentially 0, which is also what we're hoping for. And the exit flag is 1. And this shows what the convergence status of this. And if you want, you can do help fmin unc to read the documentation for how to interpret the exit flag. But the exit flag lets you verify whether or not this algorithm thinks it has converged. So that's how you run these algorithms in Octave. I should mention, by the way, that for the Octave implementation, this value of theta, your parameter vector theta, must be in RD for d greater than or equal to 2. So if theta is just a row number, so if it's not at least a two-dimensional vector or some higher than two-dimensional vector, this fmin unc may not work. So if in case you have a one-dimensional function that you need to optimize, you can look in the Octave documentation for fmin unc for additional details. So that's how we optimize our toy example of this sort of simple quadratic cost function. How do we apply this to logistic regression? In logistic regression, we have a parameter vector theta, and I'm going to use a mix of Octave notation and sort of math notation, but I hope this explanation will be clear. But our parameter vector theta comprises these parameters theta 0 through theta n, because Octave indexes vectors using indexing from 1. Theta 0 is actually written theta 1 in Octave, theta 1 is going to be written so theta 2 in Octave, and that's going to be written theta n plus 1, right? And that's because Octave indexes its vectors starting from an index of 1 instead of an index from 0. So what we need to do then is write a cost function that captures the cost function for logistic regression. Concretely, the cost function needs to return jval, which is jval, so you need some code to compute j of theta. And we also need to give it the gradient. So gradient 1 is going to be some code to compute the partial derivative with respect to theta 0, the next partial derivative with respect to theta 1, and so on. And once again, this is gradient 0, this is gradient 1, gradient 2, and so on, rather than gradient 0, gradient 1, because Octave indexes its vectors starting from 1 rather than from 0. But the main concept I hope you take away from this slide is that what you need to do is write a function that returns the cost function and returns the gradient. And so in order to apply this to logistic regression, or even to linear regression, if you want to use these optimization algorithms for linear regression, what you need to do is plug in the appropriate code to compute these things over here. So now you know how to use these advanced optimization algorithms. Because for these algorithms, you're using a sophisticated optimization library, it makes the code just a little bit more opaque, and so just maybe a little bit harder to debug. But because these algorithms often run much faster than gradient descent, often, quite typically, whenever I have a large machine learning problem, I will use these algorithms instead of using gradient descent. And with these ideas, hopefully you'll be able to get logistic regression and also linear regression to work on much larger problems. So that's it for advanced optimization concepts. And in the next and final video on logistic regression, I want to tell you how to take the logistic regression algorithm that you already know about and make it work also on multi-class classification problems. In this video, we'll talk about how to get logistic regression to work for multi-class classification problems. And in particular, I want to tell you about an algorithm called one versus all classification. What's a multi-class classification problem? Here are some examples. Let's say you want a learning algorithm to automatically put your email into different folders or to automatically tag your emails. So you might have different folders or different tags for work email, email from your friends, email from your family, and emails about your hobby. And so here we have a classification problem with 4 classes, which we might assign the numbers, the classes y equals 1, y equals 2, y equals 3, and y equals 4 to. And another example, for medical diagnosis, if a patient comes into your office with maybe a stuffy nose, the possible diagnoses could be that they're not ill, maybe that's y equals 1, or they have a cold, 2, or they have a flu. And third and final example, if you are using machine learning to classify the weather, maybe you want to decide if the weather is sunny, cloudy, rainy, or snow, or if it's going to be snow. And so in all of these examples, y can take on a small number of discrete values, maybe 1 to 3, 1 to 4, and so on, and these are multi-class classification problems. And by the way, it doesn't really matter whether we index this as 0, 1, 2, 3, or as 1, 2, 3, 4. I tend to index my classes starting from 1 rather than starting from 0, but either way works, and it really doesn't matter. Whereas previously, for a binary classification problem, our data sets look like this. For a multi-class classification problem, our data sets may look like this, where here I'm using 3 different symbols to represent our 3 classes. So the question is, given a data set with 3 classes, where this is an example of one class, that's an example of a different class, and that's an example of yet a third class, how do we get a learning algorithm to work for the setting? We already know how to do binary classification. Using logistic regression, we know how to, maybe fit a straight line to separate the positive and negative classes. Using an idea called one versus all classification, we can then take this and make it work for multi-class classification as well. Here's how one versus all classification works, and this is also sometimes called one versus rest. Let's say we have a training set like that shown on the left, where we have 3 classes. So if y equals 1, we denote that with a triangle. If y equals 2, the square. And if y equals 3, then the cross. What we're going to do is take our training set and turn this into 3 separate binary classification problems. So turn this into 3 separate 2-class classification problems. So let's start with class 1, which is a triangle. We're going to essentially create a new sort of fake training set where classes 2 and 3 get assigned to the negative class, and class 1 gets assigned to the positive class. We're going to create a new training set like that shown on the right, and we're going to fit a classifier, which I'm going to call h subscript theta superscript 1 of x, where here the triangles are the positive examples and the circles are the negative examples. So think of the triangles being assigned the value of 1 and the circles the value of 0. And we're just going to train a standard logistic regression classifier, and maybe that will give us a decision boundary that looks like that. Okay? This superscript 1 here stands for class 1, so we're doing this for the triangles of the first class. Next, we do the same thing for class 2. We're going to take the squares and assign the squares as the positive class and assign everything else, the triangles and the crosses, as the negative class. And then we fit a second logistic regression classifier. We call this h of x superscript 2, where the superscript 2 denotes that we're now doing this, treating the square class as the positive class, and maybe we get the classifier like that. And finally, we do the same thing for the third class and fit a third classifier, h superscript 3 of x, and maybe this will give us a decision boundary or give us a classifier that separates the positive and negative examples like that. So to summarize, what we've done is we've fit 3 classifiers. So for I equals 1, 2, 3, we've fit a classifier h superscript I subscript theta of x that's trying to estimate what is the probability that y is equal to class I given x and parameterized by theta, right? So in the first instance, for this first one up here, this classifier was learning to recognize the triangles. So it's thinking of the triangles as a positive class. So h superscript 1 is essentially trying to estimate what is the probability that the y is equal to 1 given x and parameterized by theta. And similarly, this is treating the square class as a positive class, and so it's trying to estimate the probability that y is equal to 2 and so on. So we now have 3 classifiers, each of which was trained to recognize one of the 3 classes. Just to summarize, what we've done is we want to train a logistic regression classifier, h superscript I of x for each class I to predict the probability that y is equal to I. Finally, to make a prediction, when we're given a new input x and we want to make a prediction, what we do is we just run all, let's say run all 3 of our classifiers on the input x, and we then pick the class I that maximizes the 3. So we just, basically pick the classifier, pick whichever one of the 3 classifiers is most confident or sort of most enthusiastically says that it thinks it has the right class. So whichever value of I gives us the highest probability, we then predict Y to be that value. So that's it for multi-class classification and one versus all method. And with this little method, you can now take the logistic regression classifier and make it work on multi-class classification problems as well. By now, you've seen a couple different learning algorithms, linear regression and logistic regression. They work well for many problems, but when you apply them to certain machine learning applications, they can run into a problem called overfitting that can cause them to perform very poorly. What I'd like to do in this video is explain to you what is this overfitting problem, and in the next few videos after this, we'll talk about a technique called regularization that will allow us to ameliorate or to reduce this overfitting problem and get these learning algorithms to maybe work much better. So what is overfitting? Let's keep using our running example of predicting housing prices with linear regression, where we want to predict the price as a function of the size of the house. One thing we could do is fit a linear function to this data, and if we do that, maybe we get that sort of straight line fit to the data. But this isn't a very good model. Looking at the data, it seems pretty clear that as the size of the house increases, the housing prices plateau or kind of flattens out as we move to the right. And so this algorithm doesn't fit the training set very well, and we call this problem underfitting. And another term for this is that this algorithm has high bias. Both of these roughly mean that it's just not even fitting the training data very well. The term bias is kind of a historical or technical one, but the idea is that if we're fitting a straight line to the data, then it's as if the algorithm has a very strong preconception or a very strong bias that housing prices are going to vary linearly with their size. And despite the data to the contrary, despite the evidence to the contrary, its preconceptions still, or bias still causes it to fit a straight line, and this ends up being a poor fit to the data. Now, in the middle, we could fit a quadratic function to the data, and with this data set, we fit a quadratic function, maybe we get that kind of curve, and that works pretty well. And at the other extreme would be if we were to fit, say, a fourth order polynomial to the data. So here we have 5 parameters, theta 0 through theta 4, and with that, we can actually fit a curve that passes through all 5 of our training examples. We might get a curve that looks like this, that on the one hand seems to do a very good job fitting the training set, as it passes through all of my data at least, but this is sort of very wiggly curve, right? Sort of going up and down all over the place, and we don't actually think that's such a good model for predicting housing prices. So this problem we call overfitting, and another term for this is that this algorithm has high variance. The term high variance is another sort of historical or technical one, but the intuition is that if we're fitting such a high order polynomial, then the hypothesis can fit, it's almost as if it can fit almost any function, and the space of possible hypotheses is just too large, or it's too variable, and we don't have enough data to constrain it to give us a good hypothesis. So that's called overfitting. And in the middle, there isn't really a name, but I'm just going to write, just right, where a second degree polynomial, a quadratic function, seems to be just right for fitting this data. To recap a bit, the problem of overfitting comes when, if we have too many features, then the learned hypothesis may fit the training set very well. So your cost function may actually be very close to 0, or maybe even 0 exactly. But you may then end up with a curve like this that tries too hard to fit the training set, so that it even fails to generalize to new examples, that it fails to predict prices on new examples well. And here the term generalize refers to how well a hypothesis applies even to new examples, that is, to data, to houses that it hasn't seen in the training set. On this slide, we looked at overfitting for the case of linear regression. A similar thing can apply to logistic regression as well. Here's a logistic regression example with two features x1 and x2. One thing we could do is fit logistic regression with just a simple hypothesis like this, where, as usual, g is my sigmoid function. And if you do that, you end up with the hypothesis trying to use maybe just a straight line to separate the positive and the negative examples. And this doesn't look like a very good fit to the hypothesis. And so, once again, this is an example of underfitting or of a hypothesis having high bias. In contrast, if you were to add to your features these quadratic terms, then you could get a decision boundary that might look more like this. And that's a pretty good fit to the data. Probably about as good as we could get on this training set. And finally, at the other extreme, if you were to fit a very high order polynomial, if you were to generate lots of high order polynomial terms as features, then logistic regression may contort itself, may try really hard to find a decision boundary that fits your training data, or go to great lengths to contort itself to fit every single training example well. And if the features x1 and x2 are for predicting maybe the cancerous, malignant, benign breast tumors, this really doesn't look like a very good hypothesis for making predictions. And so once again, this is an instance of overfitting and of the hypothesis having high variance and being unlikely to generalize well to new examples. Later in this course, when we talk about debugging and diagnosing things that can go wrong with learning algorithms, we'll give you specific tools to recognize when overfitting and also when underfitting may be occurring. But for now, let's talk about the problem of, if we think overfitting is occurring, what can we do to address it? In the previous examples, we had 1 or 2 dimensional data, so we could just plot the hypothesis and see what was going on and select the appropriate degree polynomial. So earlier, for the housing prices example, we could just plot the hypothesis and maybe see that it was fitting the sort of very wiggly function that goes all over the place to predict housing prices, and we could then use figures like these to select an appropriate degree polynomial. So plotting the hypothesis could be one way to try to decide what degree polynomial to use, but that doesn't always work. And in fact, more often, we may have learning problems where we just have a lot of features. And there is not just a matter of selecting what degree polynomial, and in fact, when we have so many features, it also becomes much harder to plot the data and becomes much harder to visualize it, to decide what features to keep or not. So concretely, if we're trying to predict housing prices, sometimes we can just have a lot of different features, and all of these features seem, maybe they seem kind of useful. But if we have a lot of features and very little training data, then overfitting can become a problem. In order to address overfitting, there are 2 main options for things that we can do. The first option is to try to reduce the number of features. Concretely, one thing we could do is manually look through the list of features and use that to try to decide which are the more important features, and therefore which are the features we should keep and which are the features we should throw out. Later in this class, we'll also talk about model selection algorithms, which are algorithms for automatically deciding which features to keep and which features to throw out. This idea of reducing the number of features can work well and can reduce overfitting. And when we talk about model selection, we'll go into this in much greater depth. But the disadvantage is that by throwing away some of the features is also throwing away some of the information you have about the problem. For example, maybe all of those features are actually useful for predicting the price of a house, so maybe we don't actually want to throw some of our information or throw some of our features away. The second option, which we'll talk about in the next few videos, is regularization. Here, we're going to keep all the features, but we're going to reduce the magnitude or the values of the parameters theta j. And this method works well, we'll see, when we have a lot of features, each of which contributes a little bit to predicting the value of y, like we saw in the housing price prediction example, where we could have a lot of features, each of which are somewhat useful, so maybe we don't want to throw them away. So this describes the idea of regularization at a very high level, And I realize that all of these details probably don't make sense to you yet. But in the next video, we'll start to formulate exactly how to apply regularization and exactly what regularization means. And then we'll start to figure out how to use this to make our learning algorithms work well and avoid overfitting. In this video, I'd like to convey to you the main intuitions behind how regularization works, and we'll also write down the cost function that we'll use when we're using regularization. With the hand-drawn examples that we'll have on these slides, I think I'll be able to convey part of the intuition, but an even better way to see for yourself how regularization works is if you implement it and sort of see it work for yourself. And if you do the programming exercises after this, you get a chance to sort of see regularization in action for yourself. So here's the intuition. In the previous video, we saw that if we were to fit a quadratic function to this data, it gives us a pretty good fit to the data. Whereas if we were to fit an overly high order degree polynomial, we end up with a curve that may fit the training set very well, but really not overfit the data poorly and not generalize well. Consider the following. Suppose we were to penalize and make the parameters theta 3 and theta 4 really small. Here's what I mean. Here's our optimization objective, or here's an optimization problem where we minimize our usual squared error cost function. Let's say I take this objective and I modify it and add to it plus 1000 theta 3 squared plus 1000 theta 4 squared. 1000 I'm just writing down as some huge number. Now, if we were to minimize this function, well, the only way to make this new cost function small is if theta 3 and theta 4 are small, right? Because otherwise, if you have 1000 times theta 3, this new cost function is going to be big. So when we minimize this new function, we're going to end up with theta 3 close to 0 and theta 4 close to 0. And that's as if we're getting rid of these two terms over there. And if we do that, well then, if theta 3 and theta 4 are close to 0, then we're basically left with a quadratic function, and so we'll end up with a fit to the data that's, a quadratic function plus maybe tiny contributions from small terms, theta 3, theta 4, that are maybe very close to 0. Well, maybe. And so we end up with essentially a quadratic function, which is good because it's a much better hypothesis. In this particular example, we looked at the effect of penalizing two of the parameter values being large. More generally, here's the idea behind regularization. The idea is that if we have small values for the parameters, then having small values for the parameters will usually correspond to having a simpler hypothesis. So for our last example, we penalized just theta 3 and theta 4, and when both of these were close to 0, we wound up with a much simpler hypothesis that was essentially a quadratic function. But more broadly, if we penalize all the parameters, usually that we can think of that as trying to give us a simpler hypothesis as well, because when these parameters are close to 0, in this example, that gave us a quadratic function. But more generally, it's possible to show that having smaller values of the parameters corresponds to usually smoother functions as well that are simpler, and which are therefore also less prone to overfitting. I realized that the reasoning for why having all the parameters be small, why that corresponds to a simpler hypothesis, I realized that reasoning may not be entirely clear to you right now, and it is kind of hard to explain unless you implement it yourself and see it for yourself. But I hope that the example of having theta 3 and theta 4 be small and how that gave us a simpler hypothesis, I hope that helps explain why, at least give some intuition as to why this might be true. Let's look at a specific example. For housing price prediction, we may have our 100 features that we talked about, where maybe x1 is the size, x2 is the number of bedrooms, x3 is the number of floors, and so on, and we may have 100 features. And unlike the polynomial example, we don't know, right? We don't know that theta 3, theta 4 are the high-order polynomial terms. So if we have just a set of 100 features, it's hard to pick in advance which are the ones that are less likely to be relevant. So we have, 100 or 101 parameters, and we don't know which ones to pick. We don't know which parameters to pick to try to shrink. So in regularization, what we're going to do is take our cost function. Here's my cost function for linear regression. And what I'm going to do is modify this cost function to shrink all of my parameters, because I don't know which one or two to try to shrink. So I'm going to modify my cost function to add a term at the end, like so. Let me add square brackets here as well. I'm going to add an extra regularization term at the end to shrink every single parameter. And so this term will tend to shrink all of my parameters, theta 1, theta 2, theta 3, up to theta 100. By the way, by convention, the summation here starts from 1, so I'm not actually going to penalize theta 0 being large. That's sort of a convention that the sum is from I equals 1 through n rather than I equals 0 through n. But in practice, it makes very little difference. And whether you include theta 0 or not, in practice, it'll make very little difference to the results. But by convention, usually we regularize only theta 1 through theta 100. Writing down our regularized optimization objective, our regularized cost function again, here it is. Here's j of theta, where this term on the right is the regularization term, and lambda here is called the regularization parameter. And what lambda does is it controls a trade-off between two different goals. The first goal, captured by the first term in the objective, is that we would like to fit the training data well. We would like to fit the training set well. And the second goal is we want to keep the parameters small, and that's captured by the second term, by the regularization objective, and by the regularization term. And what lambda, the regularization parameter, does is it controls the trade-off between these two goals, between the goal of fitting the training set well and the goal of keeping the parameters small, and therefore keeping the hypothesis relatively simple to avoid overfitting. For our housing price prediction example, whereas previously if we had fit a very high order polynomial, we may have wound up with a very sort of wiggly or curvy function like this. If you still fit a high order polynomial with all the polynomial features in there, but instead you just make sure to use this sort of regularized objective, then what you can get out is in fact a curve that isn't quite a quadratic function, but is much smoother and much simpler, and maybe a curve like the magenta line that fits, that gives a much better hypothesis for this data. Once again, I realize it can be a bit difficult to see why shrinking the parameters can have this effect, but if you implement this algorithm yourself with regularization, you will be able to see this effect firsthand. In regularized linear regression, if the regularization parameter lambda is set to be very large, then what will happen is we will end up penalizing the parameters theta 1, theta 2, theta 3, theta 4 very highly. That is, if our hypothesis is this one down at the bottom. And if we end up penalizing theta 1, theta 2, theta 3, theta 4 very heavily, then we'll end up with all of these parameters close to 0, right? Theta 1 will be close to 0, theta 2 will be close to 0, theta 3 and theta 4 will end up being close to 0. And if we do that, it's as if we're getting rid of these terms in our hypothesis, so that we're just left with a hypothesis that looks like that. It says that, well, housing prices are equal to theta 0, and that is akin to fitting a flat horizontal straight line to the data. And this is an example of underfitting. And in particular, this hypothesis, this straight line, it just fails to fit the training set well. It's just a flat straight line. It doesn't go, it doesn't go anywhere near most of our training examples. And another way of saying this is that this hypothesis has too strong a preconception or too high a bias that housing prices are just equal to theta 0. And despite the clear data to the contrary, it chooses to fit this sort of flat line, just a flat horizontal line. I didn't draw that very well. Fits just a horizontal flat line to the data. So for regularization to work well, some care should be taken to choose a good choice for the regularization parameter lambda as well. And when we talk about model selection later in this course, we'll talk about a variety of ways for automatically choosing the regularization parameter lambda as well. So that's the idea behind regularization and the cost function we'll use in order to use regularization. In the next two videos, let's take these ideas and apply them to linear regression and to logistic regression so that we can then get them to avoid overfitting problems. For linear regression, we had previously worked out two learning algorithms, one based on gradient descent and one based on the normal equation. In this video, we'll take those two algorithms and generalize them to the case of regularized linear regression. Here's the optimization objective that we came up with last time for regularized linear regression. This first part is our usual objective for linear regression, and we now have this additional regularization term where lambda is our regularization parameter, and we like to find parameters theta that minimizes this cost function, this regularized cost function j of theta. Previously, we were using gradient descent for the original cost function without the regularization term, and we had the following algorithm. For regular linear regression without regularization, we will repeatedly update the parameters theta j as follows for j equals 0, 1, 2, up through n. Let me take this and just write the case for theta 0 separately. So, I'm just going to write the update for theta 0 separately then for the update for the parameters 1, 2, 3, and so on up to n. And this is, I haven't changed anything yet, right? This is just writing the update for theta 0 separately from the updates for theta 1, theta 2, theta 3, up to theta n. And the reason I want to do this is you may remember that for our regularized linear regression, we penalize the parameters theta 1, theta 2, and so on up to theta n, but we don't penalize theta 0. So when we modify this algorithm for regularized linear regression, we're going to end up treating theta 0 slightly differently. Concretely, if we want to take this algorithm and modify it to use the regularized objective, all we need to do is take this term at the bottom and modify it as follows. I'm going to take this term and add minus lambda over m times theta j. And if you implement this, then you have gradient descent for trying to minimize the regularized cost function j of theta. And concretely, I'm not going to do the calculus to prove it, but concretely, if you look at this term that written in square brackets, if you know calculus, it's possible to prove that that term is the partial derivative with respect to j of theta using the new definition of j of theta with the regularization term. And similarly, this term up on top, which I guess I'm drawing the cyan box, that's still the partial derivative with respect to theta 0 of j of theta. If you look at the update for theta j, it's possible to show something pretty interesting. Concretely, theta j gets updated as theta j minus alpha times, and then you have this other term here that depends on theta j. So if you group all the terms together that depend on theta j, you can show that this update can be written equivalently as follows. And all I did was that theta j here is theta j times 1, and this term is lambda over m. There's also an alpha here, so you end up with alpha lambda over m multiplied into theta j. And this term here, 1 minus alpha times lambda m, is a pretty interesting term. It has a pretty interesting effect. Concretely, this term 1 minus alpha times lambda over m is going to be a number that's, usually it's a number that's usually like a little bit less than 1, right? Because alpha times lambda over m is going to be positive, and usually, if your learning rate is small and if m is large, this is usually pretty small. So this term here is going to be a number that's usually, a little bit less than 1. So think of it as a number like 0.99, let's say. And so the effect of our update to theta j is we're going to say that theta j gets replaced by theta j times 0.99, right? So theta j times 0.99 has the effect of shrinking theta j a little bit towards 0. So this makes theta j a bit smaller, or more formally, this makes, the squared norm of theta j a little bit smaller. And then after that, the second term here, that's actually exactly the same as the original gradient descent update that we had before we added all this regularization stuff. So hopefully this gradient descent, hopefully this update makes sense. When we're using regularized linear regression, what we're doing is on every iteration, we're multiplying theta j by a number that's a little bit less than 1, so we're shrinking the parameter a little bit, and then we're performing, similar update as before. Of course, that's just the intuition behind what this particular update is doing. Mathematically, what it's doing is exactly gradient descent on the cost function j of theta that we defined on the previous slide that uses the regularization term. Gradient descent was just one of our two algorithms for fitting a linear regression model. The second algorithm was the one based on the normal equation, where what we did was we created the design matrix X, where each row corresponded to a separate training example, and we created a vector Y. So this is a vector that's an m-dimensional vector, and that contained the labels from a training set. So whereas X is an m by n plus 1 dimensional matrix, Y is a m-dimensional vector. And in order to minimize the cost function j, we found that one way to do so is to set theta to be equal to this, right? We had X transpose X inverse X transpose Y. I'm leaving room here to fill in stuff, of course. And what this value for theta does is this minimizes the cost function j of theta when we were not using regularization. Now that we are using the regularization, if you were to derive what the minimum is, and just to give you a sense of how to derive the minimum, the way you derive it is you take partial derivatives with respect to each parameter, set this to 0, and then do a bunch of math, and you can then show that it's a formula like this that minimizes the cost function. And concretely, if you are using regularization, then this formula changes as follows. Inside this parenthesis, you end up with a matrix like this: 0, 1, 1, 1, and so on, 1 until the bottom. So this thing over here is a matrix whose upper leftmost entry is 0, there are 1s on the diagonals, and then there's 0s everywhere else in this matrix, because I'm drawing this a little bit sloppily. But as a concrete example, if n equals 2, then this matrix is going to be a 3 by 3 matrix. More generally, this matrix is a n plus 1 by n plus 1 dimensional matrix. So if n equals 2, then that matrix becomes something that looks like this. It will be 0, and then 1s on the diagonals, and then 0s on the rest of the off diagonals. And once again, I'm not going to show this derivation, which is frankly somewhat long and involved, but it's possible to prove that if you are using the new definition of j of theta with the regularization objective, then this new formula for theta is the one that would give you the global minimum of j of theta. So finally, I want to just quickly describe the issue of non-invertibility. This is relatively advanced material, so you should consider this as optional, and feel free to skip it, or if you listen to it and parts of it don't really make sense, don't worry about it either. But earlier when I talked about the normal equation method, we also had an optional video on the non-invertibility issue. So this is another optional part that's sort of an add-on to that earlier optional video on non-invertibility. Now, consider a setting where m, the number of examples, is less than or equal to n, the number of features. If you have fewer examples than features, then this matrix, X transpose X, will be non-invertible, or singular, or the other term for this is the matrix will be degenerate. And if you implement this in octave anyway, and you use the pin function to take the pseudo-inverse, it'll kind of do the right thing, but it's not clear that it'll give you a very good hypothesis, even though numerically, the octave pin function will give you a result that kind of makes sense. But if you were doing this in a different language, and if you were taking just the regular inverse, which in octave is denoted with the function inv, if you're trying to take the regular inverse of x transpose x, then in this setting, you find that x transpose x is singular, is non-invertible. And if you're doing this in a different programming language, and using some linear algebra library to try to take the inverse of this matrix, it just might not work because that matrix is non-invertible or singular. Fortunately, regularization also takes care of this for us. And concretely, so long as the regularization parameter lambda is strictly greater than 0, it is actually possible to prove that this matrix, x transpose x plus lambda times this funny matrix here, is possible to prove that this matrix will not be singular and that this matrix will be invertible. So using regularization also take care of any non-invertibility issues of the x transpose x matrix as well. So you now know how to implement regularized linear regression. Using this, you'll be able to avoid overfitting even if you have lots of features in a relatively small training set, and this should let you get linear regression to work much better for many problems. In the next video, we'll take this regularization idea and apply it to logistic regression so that you'll be able to get logistic regression to avoid overfitting and perform much better as well. For logistic regression, we previously talked about two types of optimization algorithms. We talked about how to use gradient descent to optimize this cost function j of theta, and we also talked about advanced optimization methods, ones that require that you provide a way to compute the cost function j of theta and that you provide a way to compute the derivatives. In this video, we'll show how you can adapt both of those techniques, both gradient descent and the more advanced optimization techniques, in order to have them work for regularized logistic regression. So here's the idea. We saw earlier that logistic regression can also be prone to overfitting if you fit it with a very sort of high order polynomial features like this, where g is the sigmoid function, and in particular you may end up with a hypothesis whose decision boundary is this sort of a overly complex, extremely contorted function that really isn't such a great hypothesis for this training set. And more generally, if you have logistic regression with a lot of features, not necessarily polynomial ones, but just with a lot of features, you can end up with overfitting. This was our cost function for logistic regression, and if we want to modify it to use regularization, all we need to do is add to it the following term plus lambda over 2m, sum from j equals 1, and as usual, from 1, sum from j equals 1 rather than sum from j equals 0 of theta j squared, and this has the effect, therefore, of penalizing the parameters theta 1, theta 2, and so on, up to theta n from being too large. And if you do this, then it will have the effect that even though you're fitting a very high order polynomial with a lot of parameters, so long as you apply regularization and keep the parameters small, you're more likely to get a decision boundary that maybe looks more like this and looks more reasonable for separating out the positive and the negative examples. So when using regularization, even when you have a lot of features, the regularization can help take care of the overfitting problem. How do we actually implement this? Well, for the original gradient descent algorithm, this was the update we had. We would repeatedly perform the following update to theta j. This slide looks a lot like the previous one for linear regression, but what I'm going to do is write the update for theta 0 separately. So the first line is my update for theta 0, and the second line is now my update for theta 1 up to theta n, because I'm going to treat theta 0 separately. And in order to modify this algorithm to use the regularized cost function, all I need to do is pretty similar to what we did for linear regression, is actually to just modify this second update rule as follows. And once again, this cosmetically looks identical to what we had for linear regression, but of course is not the same algorithm as we had, because now the hypothesis is defined using this. So this is not the same algorithm as regularized linear regression, because the hypothesis is different. Even though this update that I wrote down, it actually looks cosmetically the same as what we had earlier when working out gradient descent for regularized linear regression. And of course, just to wrap up this discussion, this term here in the square brackets, so this term here, this term is, of course, the new partial derivative with respect to theta j of the new cost function j of theta, where j of theta here is the cost function we defined on the previous slide that does use regularization. So that's gradient descent for regularized linear regression. Let's talk about how to get regularized linear regression to work using the more advanced optimization methods. And just to remind you, for those methods, what we needed to do was to define a function that's called the cost function that takes as input a parameter vector theta. And once again, in the equations we've been writing here, we use zero index vectors. So we had theta 0 up to theta n. But because octave indexes the vectors starting from 1, theta 0 is written in octave as theta 1. Theta 1 is written in octave as theta 2, and so on, down to theta n plus 1. And what we needed to do was provide a function called cost function that we would then pass into what we saw earlier. We would use the f min u and c, and then at cost function and so on, right? But the f min u and c was the f min unconstrained, and this was what would, and f min u and c was what would take the cost function and minimize it for us. So the two main things that the cost function needed to return were first j-val, and for that we need to write code to compute the cost function j of theta. Now when we're using regularized logistic regression, of course the cost function j of theta changes, and in particular now our cost function needs to include this additional regularization term at the end as well. So when you compute j of theta, be sure to include that term at the end. And then the other thing that this cost function thing needs to provide were the gradients. So gradient 1 needs to be set to the partial derivative of j of theta with respect to theta 0. Gradient 2 needs to be set to that, and so on. And once again, the index is off by 1, right, because of the indexing from 1 that octave uses. And looking at these terms, this term over here, we actually worked this out on the previous slide. It's actually equal to this. It doesn't change because the derivative for theta 0 doesn't change compared to the version without regularization. And the other terms do change, and in particular, the derivative with respect to theta 1, we worked this out on the previous slide as well, is equal to the original term and then minus lambda over m times theta 1. Just so we make sure we pause this correctly, if we can add parentheses here, right, so the summation doesn't extend. And similarly, this other term here looks like this with this additional term that we had on the previous slide that corresponds to the gradient from the regularization objective. So if you implement this cost function and pass this into f min u and c, or to one of those advanced optimization techniques, that will minimize the new regularized cost function j of theta, and the parameters you get out will be the ones that correspond to logistic regression with regularization. So now you know how to implement regularized logistic regression. When I walk around Silicon Valley, I live here in Silicon Valley, there are a lot of engineers that are frankly making a ton of money for their companies using machine learning algorithms. And I know we've only been studying this stuff for a little while, but if you understand linear regression, logistic regression, the advanced optimization algorithms, and regularization, by now, frankly, you probably know quite a lot more machine learning than many, certainly not all, but you probably know quite a lot more machine learning right now than, frankly, many of the Silicon Valley engineers that are out there having very successful careers, making tons of money for the companies, or building great products using machine learning algorithms. So congratulations, you've actually come a long ways, and you actually know enough to apply this stuff and get it to work for many problems. So congratulations for that. But of course, still a lot more that we want to teach you, and in the next set of videos after this, we'll start to talk about a very powerful class of nonlinear classifiers. So whereas linear regression, logistic regression, you can throw in polynomial terms, but it turns out that there are much more powerful nonlinear classifiers that can than sort of polynomial regression. And in the next set of videos after this one, I'll start telling you about them so that you have even more powerful learning algorithms than you have now to apply to different problems. In this and in the next set of videos, I'd like to tell you about a learning algorithm called a neural network. We're going to first talk about the representation, and then in the next set of videos talk about learning algorithms for it. Neural networks is actually a pretty old idea, but had fallen out of favor for a while, but today it is the state-of-the-art technique for many different machine learning problems. So why do we need yet another learning algorithm? We already have linear regression and we have logistic regression, so why do we need neural networks? In order to motivate the discussion of neural networks, let me start by showing you a few examples of machine learning problems where we need to learn complex nonlinear hypotheses. Consider a supervised learning classification problem where you have a training set like this. If you want to apply logistic regression to this problem, one thing you could do is apply logistic regression with a lot of nonlinear features like that. So here, g as usual is a sigmoid function, and we can include lots of polynomial terms like these. And if you include enough polynomial terms, then maybe you can get a hypothesis that separates the positive and negative examples. This particular method works well when you have only, say, two features, x1 and x2, because you can then include all those polynomial terms of x1 and x2. But for many interesting machine learning problems, we have a lot more features than just two. We've been talking for a while about housing prediction, and suppose you had a housing classification problem rather than a regression problem. Like maybe if you have different features of a house, and you want to predict what are the odds that a house will be sold within the next 6 months. So that would be a classification problem. And as we saw, we can come up with quite a lot of features, maybe 100 different features of different houses. For a problem like this, if you were to include all the quadratic terms, all of these, even all the quadratic, that is the second order polynomial terms, there would be a lot of them. There would be terms like x1 squared, x1, x2, x1, x3, x1, x4, up to x1, x100, and then you have x2 squared, x2, x3, and so on. And if you include just the second order terms, that is the terms that are a product of two of these terms, x1 times x4 and so on, then for the case of n equals 100, you end up with about 5,000 features. And asymptotically, the number of quadratic features grows roughly as order n squared, where n is the number of the original features, like x1 through x100 that we had, and it is actually closer to n squared over 2. So including all the quadratic features doesn't seem like maybe a good idea, because that's a lot of features, and you might end up overfitting the training set, and it can also be computationally expensive to have to be working with that many features. One thing you could do is include only a subset of these. So if you include only the features x1 squared, x2 squared, x3 squared, up to maybe x100 squared, then the number of features is much smaller. Here you have only 100 such quadratic features, but this is not enough features and certainly won't let you fit a data set like that on the upper left. In fact, if you include only these quadratic features together with the original x1 and so on up to x100 features, then you can't actually fit very interesting hypotheses. You can fit things like axis-aligned ellipses like these, but you certainly cannot fit a more complex data set like that shown here. So 5,000 features seems like a lot. If you were to include the cubic or third order polynomial features, the x1, x2, x3, x1 squared, x2, x10, x11, x17, and so on, you can imagine there are going to be a lot of these features. In fact, they're going to be order n cubed such features, and if n equals 100, you can compute that you end up with on the order of about 170,000 such cubic features. And so including these higher order polynomial features when your original feature set n is large. This really dramatically blows up your feature space, and this doesn't seem like a good way to come up with additional features with which to build nonlinear classifiers when n is large. For many machine learning problems, n will be pretty large. Here's an example. Let's consider the problem of computer vision. And suppose you want to use machine learning to train a classifier to examine an image and tell us whether or not it is the image is a car. Many people wonder why computer vision could be difficult. I mean, when you and I look at this picture, it's so obvious what this is. You wonder how is it that the learning algorithm could possibly fail to know what this picture is. To understand why computer vision is hard, and let's zoom into a small part of the image, like that area where the little red rectangle is. It turns out that where you and I see a car, the computer sees that. What it sees is this matrix, or this grid of pixel intensity values that tells us the brightness of each pixel in the image. So the computer vision problem is to look at this matrix of pixel intensity values and tell us that these numbers represent the door handle of a car. Concretely, when we use machine learning to build a car detector, what we do is we come up with a labeled training set with, let's say, a few labeled examples of cars and a few labeled examples of things that are not cars. Then we give our training set to the learning algorithm, train a classifier, and then we may test it and show the new image and ask, what is this new thing? And hopefully it'll recognize that that is a car. To understand why we need nonlinear hypotheses, let's take a look at some of the images of cars and maybe non-cars that we might feed to our learning algorithm. Let's pick a couple pixel locations in our images. So that's pixel 1 location and pixel 2 location, and let's plot this car at the location at a certain point depending on the intensities of pixel 1 and pixel 2. And let's do this with a few other images. So let's take a different example of a car and look at the same 2 pixel locations, and that image has a different intensity for pixel 1 and a different intensity for pixel 2, so it ends up at a different location on the figure. And then let's plot some negative examples as well. That's a non-car, that's a non-car. And if we do this for more and more examples, using the pluses to denote cars and minuses to denote non-cars, what we'll find is that the cars and non-cars end up lying in different regions of this space, and what we need therefore is some sort of nonlinear hypothesis to try to separate out the two classes. What is the dimension of the feature space? Suppose we were to use just 50 by 50 pixel images. That is, suppose our images were pretty small ones, just 50 pixels on the side. Then we would have 2500 pixels, and so the dimension of our feature size will be n equals 2500, where our feature vector x is a list of all the pixel intensities, the pixel brightness of a pixel 1, the brightness of pixel 2, and so on, down to the pixel brightness of the last pixel, where in a typical computer representation, each of these may be values between, say, 0 to 255, if it gives us maybe the grayscale value. So we have n equals 2500. And that's if we were using grayscale images. If we were using RGB images with separate red, green, and blue values, we'd have n equals 7500. So if we were to try to learn a nonlinear hypothesis by including all the quadratic features, that is, all the terms of the form xi times xj, well, with 2500 pixels, we will end up with a total of 3 million features, and that's just too large to be reasonable. It will be computationally very expensive to find and to represent all of these 3 million features per training example. So simple logistic regression, together with adding in maybe the quadratic or the cubic features, that's just not a good way to learn complex nonlinear hypotheses when n is large, because you just end up with too many features. In the next few videos, I would like to tell you about neural networks, which turns out to be a much better way to learn complex hypotheses, complex nonlinear hypotheses, even when your input feature space, even when n is large. And along the way, I'll also get to show you a couple fun videos of historically important applications of neural networks as well, that I hope those videos that we'll see later will be fun for you to watch as well. Neural networks are a pretty old algorithm that was originally motivated by the goal of having machines that can mimic the brain. Now, in this class, of course, I'm teaching neural networks to you because they work really well for different machine learning problems, and certainly not just because they're biologically motivated. But in this video, I'd like to give you some of the background on neural networks so that we can get a sense of what we can expect them to do, both in the sense of applying them to modern day machine learning problems, as well as for those of you that might be interested in maybe the big AI dream of someday building truly intelligent machines, also how neural networks might pertain to that. The origins of neural networks was as algorithms that try to mimic the brain, and there was the sense that if we want to build learning systems, well, why not mimic perhaps the most amazing learning machine we know about, which is perhaps the brain. Neural networks came to be very widely used throughout the 1980s and 1990s, and for various reasons, its popularity diminished in the late 90s. But more recently, neural networks have had a major recent resurgence. One of the reasons for this resurgence is that neural networks are a computationally somewhat more expensive algorithm, and so it was only, maybe somewhat more recently that computers became fast enough to really run large-scale neural networks. And because of that, as well as a few other technical reasons, which we'll talk about later, modern neural networks today are the state-of-the-art technique for many applications. So when you think about mimicking the brain, well, the human brain does so many amazing things, right? The brain can learn to see, process images, learn to hear, learn to process our sense of touch. It can, learn to do math, learn to do calculus. And the brain does so many different amazing things. It seems like if you want to mimic the brain, it seems like you have to write lots of different pieces of software to mimic all of these different fascinating, amazing things that the brain does. But there's this fascinating hypothesis that the way the brain does all of these different things is not with like 1,000 different programs, but instead the way the brain does it is with just a single learning algorithm. This is just a hypothesis, but let me share with you some of the evidence for this. This part of the brain, that little red part of the brain, is your auditory cortex. And the way you're understanding my voice now is your ear is taking the sound signal and routing the sound signal to your auditory cortex, and that's what's allowing you to understand my words. Neuroscientists have done the following fascinating experiment where you cut the wire from the ears to the auditory cortex, and you rewire, in this case, an animal's brain, so that the signal from the eyes, from the optic nerve, eventually gets routed to the auditory cortex. If you do this, it turns out the auditory cortex will learn to see. And this is in every single sense of the word see as we know it. So if you do this to the animals can perform visual discrimination tasks, and that is, they can look at images and make appropriate decisions based on the images, and they're doing it with that piece of brain tissue. Here's another example. That red piece of brain tissue is your somatosensory cortex. That's how you process your sense of touch. If you do a similar rewiring process, then the somatosensory cortex will learn to see. Because of this and other similar experiments, these are called neural rewiring experiments, there's this sense that if the same piece of physical brain tissue can process sight or sound or touch, then maybe there's one learning algorithm that can process sight or sound or touch. And instead of needing to implement 1,000 different programs or 1,000 different algorithms to do the 1,000 wonderful things that the brain does, maybe what we need to do is figure out some approximation or to whatever the brain's learning algorithm is, and implement that, and let the brain learn by itself how to process these different types of data. To a surprisingly large extent, it seems as if we can plug in almost any sensor to almost any part of the brain, and so that within reason, the brain will learn to deal with it. Here are a few more examples. On the upper left is an example of learning to see with your tongue. The way it works is this is actually a system called BrainPort undergoing FDA trials now to help blind people see. But the way it works is you strap a grayscale camera to your forehead facing forward, that takes a low resolution grayscale image of what's in front of you, and you then run a wire to an array of electrodes that you place on your tongue, so that each pixel gets mapped to a location on your tongue where maybe a high voltage corresponds to a dark pixel and a low voltage corresponds to a bright pixel. And even as adults today, with this sort of system, you and I will be able to learn to see, in tens of minutes with our tongues. Here's a second example of a human echolocation or human sonar. So there are two ways you can do this. You can either snap your fingers or click your tongue. Can't do it very well. And but there are blind people today that are actually being trained in schools to do this and learn to interpret the pattern of sounds bouncing off your environment as sonar. So if afterward you search on YouTube, there are actually videos of this amazing kid who tragically, because of cancer, had his eyeballs removed. So this is a kid with no eyeballs. But by snapping his fingers, he can walk around and never hit anything. He can ride a skateboard. He can shoot a basketball into a hoop. And this is a kid with no eyeballs. Third example is the haptic belt, where if you have a strap around your waist, a ring of buzzers, and always have the northmost one buzzing, you can give a human a direction sense, similar to maybe how birds can just sense where north is. And somewhat bizarre example, but if you plug a third eye into a frog, the frog will learn to use that eye as well. So it's pretty amazing to what extent it's as if you can plug in almost any sensor to the brain, and the brain's learning algorithm will just figure out how to learn from that data and deal with that data. And there's a sense that if we can figure out what the brain's learning algorithm is and implement it or implement some approximation to that algorithm on a computer, maybe that would be our best shot at making real progress towards the AI, the artificial intelligence dream of someday building truly intelligent machines. Now, of course, I'm not teaching neural networks, just because they might give us a window into this far-off AI dream, even though that's one of the things that I personally work on in my research life. But the main reason I'm teaching neural networks in this class is because it's actually a very effective state-of-the-art technique for modern-day machine learning applications. So in the next few videos, I'm going to start diving into the technical details of neural networks so that you can apply them to modern-day machine learning applications and get them to work well on problems. But for me, one of the reasons they excite me is that maybe they give us this window into what we might do if we're also thinking of what algorithms might someday be able to learn in manners similar to humans can. In this video, I want to start telling you about how we represent neural networks. In other words, how we represent our hypothesis or how we represent our model when using neural networks. Neural networks were developed as simulating neurons or networks of neurons in the brain. So to explain the hypothesis representation, let's start by looking at what a single neuron in the brain looks like. Your brain and mine is jam-packed full of neurons like these, and neurons are cells in the brain. And the two things to draw attention to are that first, the neuron has a cell body like so, and moreover, the neuron has a number of input wires, and these are called the dendrites. You think of them as input wires, and these receive inputs from other locations. And the neuron also has an output wire called the axon, and this output wire is what it uses to send signals to other neurons, or to send messages to other neurons. So at a simplistic level, what a neuron is a computational unit that gets a number of inputs through its input wires, does some computation, and then it sends outputs via its axon to other nodes or to other neurons in the brain. Here's an illustration of a group of neurons. The way that neurons communicate with each other is with little pulses of electricity. They're also called spikes, but that just means a little pulse of electricity. So here's one neuron, and what it does is, if it wants to send a message, what it does is it sends a little pulse of electricity via its axon to some different neuron. And here, this axon, that is this output wire, connects to the input wire, connects to the dendrite of this second neuron over here, which then accepts this incoming message, does some computation, and may in turn decide to send out its own messages on its axon to other neurons. And this is the process by which all human thought happens, is these neurons doing computations and passing messages to other neurons as a result of what other inputs they got. And by the way, this is how our sensors and our muscles work as well. If you want to move one of your muscles, the way that works is that the neuron may send these pulses of electricities to your muscle, and that causes your muscles to contract. And your eyes, if some sensor like your eye wants to send a message to your brain, what it does is it sends these pulses of electricity to a neuron in your brain, like so. In a neural network, or rather in an artificial neural network that we implement in a computer, we're going to use a very simple model of what a neuron does. We're going to model a neuron as just a logistic unit. So when I draw a yellow circle like that, you should think of that as playing a role analogous to maybe the body of a neuron, and we then feed the neuron a few inputs via its dendrites or its input wires. And the neuron does some computation and outputs some value on its output wire, or in a biological neuron, this was the axon. And whenever I draw a diagram like this, what this means is that this represents a computation of h of x equals 1 over 1 plus e to the negative theta transpose x, where as usual, x and theta are our parameter vectors, like so. So this is a very simple, maybe vastly oversimplified model of the computation that the neuron does, where it gets a number of inputs, x1, x2, x3, and it outputs some value computed like so. When I draw a neural network, usually I draw only the input nodes x1, x2, x3. Sometimes when it's useful to do so, I draw an extra node for x0. This x0 node is sometimes called the bias unit, or the bias neuron. But because x0 is always equal to 1, sometimes I draw it and sometimes I won't, just depending on whatever is more notationally convenient for that, for that example. Finally, one last bit of terminology. When we talk about neural networks, sometimes we'll say that this is a neuron, or an artificial neuron, with a sigmoid or a logistic activation function. So this activation function in the neural network terminology, this is just another term for that function, for that nonlinearity g of z, equals 1 over 1 plus e to the negative z. And whereas so far I've been calling theta the parameters of the model, I'll mostly continue to use that terminology to call theta the parameters. But in neural networks, in the neural network literature, sometimes you might hear people talk about weights of a model, and weights just means exactly the same thing as parameters of a model. But I'll mostly continue to use the terminology parameters in these videos, but sometimes you may hear others use the weights terminology. So this little diagram represents a single neuron. What a neural network is just a group of these different neurons strung together. Concretely, here we have input units x1, x2, x3, and once again, sometimes we can draw this extra node x0 and sometimes not, so just draw that in here. And here we have 3 neurons, which I've written, A21, A22, A23. I'll talk about those indices later. And once again, we can, if we want, add in this A0 and add an extra bias unit there. As always, outputs the value of 1. And then finally, we have this third node at the final layer, and there's this third node that outputs the value that our hypothesis h of x computes. To introduce a bit more terminology, in a neural network, the first layer, this is also called the input layer, because this is where we input our features, x1, x2, x3. The final layer is also called the output layer, because that layer has the neuron, this one over here, that outputs the final value computed by a hypothesis, and then layer 2 in between. This is called the hidden layer. The term hidden layer isn't a great terminology, but the intuition is that, in supervised learning, you get to see the inputs and you get to see the correct outputs, whereas the hidden layer are values you don't get to observe in the training set. So if it's not X, then it's not Y, and so we call those hidden. And later on, we'll see neural networks with more than one hidden layer, but in this example, we have one input layer, layer 1, one hidden layer, layer 2, and one output layer, layer 3. But basically, anything that isn't an input layer and isn't an output layer is called a hidden layer. So I want to be really clear about what this neural network is doing. Let's step through the computational steps that are embodied by this, represented by this diagram. To explain the specific computations represented by a neural network, here's a little bit more notation. I'm going to use A superscript J subscript I to denote the activation of neuron I, or of unit I, in layer J. So concretely, this A superscript 2 subscript 1, that's the activation of the first unit in layer 2, in our hidden layer. And by activation, I just mean, the value that is computed by and that is output by a specific. In addition, our neural network is parameterized by these matrices theta superscript j, where theta j is going to be a matrix of weights controlling the function mapping from one layer, maybe the first layer to the second layer, or from the second layer to the third layer. So here are the computations that are represented by this diagram. This first hidden unit here has its value computed as follows. A21 is equal to the sigmoid function, or the sigmoid activation function, also called the logistic activation function, applied to this sort of linear combination of its inputs. And then this second hidden unit has its activation value computed as sigmoid of this, and similarly for this third hidden unit is computed by that formula. So here we have 3 input units and 3 hidden units, and so the dimension of theta 1, which is the matrix of parameters governing our mapping from our 3 input units to our 3 hidden units, theta 1 is going to be a 3 theta 1 is going to be a 3 by 4 dimensional matrix. And more generally, if a network has Sj units in layer J and Sj plus 1 units in layer J plus 1, then the matrix theta j, which governs the function mapping from layer J to layer J plus 1, that will have dimension Sj plus 1 by Sj plus 1. Just be clear about this notation, right? This is S subscript j plus 1, and that's S subscript j, and then this whole thing plus 1. This whole thing Sj plus 1. Okay, so that's S subscript j plus 1 plus by so that's S subscript j plus 1 by Sj plus 1, where this plus 1 is not part of the subscript. Okay, so we've talked about what the 3 hidden units do to compute their values. Finally, this final, in the output layer, we have one more unit which computes h of x, and that's equal, can also be written as A31, and that's equal to this. And you notice that I've written this with a superscript 2 here, because theta superscript 2 is the matrix of parameters, or the matrix of weights, that controls the function that maps from the hidden units, that is the layer 2 units, to the 1 layer 3 unit, that is the output unit. To summarize, what we've done is shown how a picture like this over here defines an artificial neural network which defines a function h that maps from x's input values to hopefully to some space of predictions y. And these hypotheses are parameterized by parameters that I'm denoting with capital theta, so that as we vary theta, we get different hypotheses, so we get different functions mapping, say, from x to y. So this gives us a mathematical definition of how to represent the hypothesis in a neural network. In the next few videos, what I'd like to do is give you more intuition about what these hypothesis representations do, as well as go through a few examples and talk about how to compute them efficiently. In the last video, we gave a mathematical definition of how to represent or how to compute the hypothesis used by a neural network. In this video, I'd like to show you how to actually carry out that computation efficiently, and that is show you a vectorized implementation. And second, and more importantly, I want to start giving you intuition about why these neural network representations might be a good idea and how they can help us to learn complex nonlinear hypotheses. Consider this neural network. Previously, we said that the sequence of steps we need in order to compute the output of a hypothesis is these equations given on the left, where we compute the activation values of the 3 hidden units, and then we use those to compute the final output of our hypothesis, h of x. Now, I'm going to define a few extra terms. So this term that I'm underlining here, I'm going to define that to be z superscript 2 subscript 1, so that we have that a21, which is this term, is equal to g of z21. And by the way, these superscript 2, what that means is that the z2 and this a2 as well, the superscript 2 in parentheses means that these are values associated with layer 2, that is with the hidden layer in the neural network. Now, this term here, I'm going to similarly define as z22, and finally this last term here that I'm underlining, let me define that as z23, so that similarly we have a23 equals g of z23. So these z values are just a linear combination, a weighted linear combination of the input values x0, x1, x2, x3 that go into a particular neuron. Now, if you look at this block of numbers, you may notice that that block of numbers corresponds suspiciously similar to the matrix vector operation, matrix vector multiplication of x1 times the vector x. Using this observation, we're going to be able to vectorize this computation of the neural network. Concretely, let's define the feature vector x as usual to be the vector of x0, x1, x2, x3, where x0 as usual is always equal to 1. And let's define z2 to be the vector of these z values of z21, z22, z23. Notice that there z2, this is a 3-dimensional vector. We can now vectorize the computation of a21, a22, a23 as follows. We can just write this in 2 steps. We can compute z2 as theta1 times x, and that would give us this vector z2. And then a2 is g of z2. And just to be clear, z2 here, this is a 3-dimensional vector, and a2 is also a 3-dimensional vector, and thus this activation g, this applies the sigmoid function element-wise to each of z2's elements. And by the way, to make our notation a little more consistent with what we'll do later, in this input layer we have the inputs x, but we can also think of this as the activations of the first layer. So if I define a1 to be equal to x, so the a1 is a vector, I can now take this x here and replace this with z2 equals theta1 times a1, just by defining a1 to be activations in my input layer. Now, with what I've written so far, I've now gotten myself the values for a1, a2, a3, and really I should put the superscripts there as well. But I need one more value, which is I also want this a0 to, and that corresponds to a bias unit in the hidden layer that goes to the output layer. Of course, there was a bias unit here too that I just didn't draw on earlier. But to take care of this extra bias unit, what we're going to do is add an extra a0 superscript 2 that's equal to 1. And after taking this step, we now have that a2 is going to be a 4-dimensional feature vector because we just added this extra, a0, which is equal to 1, corresponding to the bias unit in the hidden layer. And finally, to compute the actual value output of our hypothesis, we then simply need to compute z3. So z3 is equal to this term here that I'm just underlining. This inner term here is z3, and z3 is theta 2 times a2, and finally my hypothesis outputs h of x, which is a3. That's the activation of my one and only unit in the output layer. So that's just a real number. You can write this as a3 or as a31, and that's g of z3. This process of computing h of x is also called forward propagation, and it's called that because we start off with the activations of the input units, and then we sort of forward propagate that to the hidden layer and compute the activations of the hidden layer, and then we sort of forward propagate that and compute the activations of the output layer. But this process of computing the activations from the input, then the hidden, then the output layer, that's also called forward propagation. And what we just did was we worked out a vectorized implementation of this procedure. So if you implement it using these equations that we have on the right, this will give you an efficient way, a relatively efficient way of computing h of x. This forward propagation view also helps us to understand what neural networks might be doing and why they might help us to learn interesting nonlinear hypotheses. Consider the following neural network, and let's say I cover up the left part of this picture for now. If you look at what's left in this picture, this looks a lot like logistic regression, where what we're doing is we're using that node, that's just a logistic regression unit, and we're using that to make a prediction h of x. And concretely, what the hypothesis is outputting is h of x is going to be equal to g, which is my sigmoid activation function, times theta 0 times a0, which is equal to 1, plus theta 1 plus theta 2 times a2 plus theta 3 times a3, where the values a1, a2, a3 are those given by these three hidden units. Now, to be actually consistent with our earlier notation, I actually would need to fill in these superscript 2's here. I guess need to fill in these superscript 2's everywhere. And I also have these indices 1 there because I have only one output unit. But if you focus on the blue parts of the notation, this is, this looks awfully like the standard logistic regression model, except that I now have a capital theta instead of lowercase theta. But and what this is doing is just logistic regression, but where the features fed into logistic regression are these values computed by the hidden layer. Just to say that again, what this neural network is doing is just like logistic regression, except that rather than using the original features x1, x2, x3, is using these new features a1, a2, a3. Again, could put the superscripts there to be consistent with the notation. And the cool thing about this is that the features a1, a2, a3, they themselves are learned as functions of the input. Concretely, the function mapping from layer 1 to layer 2, that is determined by some other set of parameters, theta 1. So it's as if the neural network, instead of being constrained to feed the features x1, x2, x3 to logistic regression, it gets to learn its own features, a1, a2, a3, to feed into logistic regression. And as you can imagine, depending on what parameters it chooses for theta 1, you can learn some pretty interesting and complex features, and therefore you can end up with a better hypothesis than if you were constrained to use the raw features x1, x2, x3, or if you were constrained to, say, choose the polynomial terms, x1, x2, x2, x3, and so on. But instead, this algorithm has the flexibility to try to learn whatever features it wants using these a1, a2, a3 in order to feed into this last unit that's essentially a logistic regression unit. I realize this example is described at a somewhat high level, and so I'm not sure if this intuition of the neural network having more complex features will quite make sense yet. But if it doesn't yet, in the next two videos, I'm going to go through a specific example of how a neural network can use its hidden layer to compute more complex features to feed into its final output layer, and how that can learn more complex hypotheses. So in case what I'm saying here doesn't quite make sense, stick with me for the next two videos, and hopefully after working through those examples, this explanation will make a little bit more sense. But just to point out, you can have neural networks with other types of diagrams as well. And the way that neural networks are connected, that's called the architecture. So the term architecture refers to how the different neurons are connected to each other. This is an example of a different neural network architecture. And once again, you may be able to get this intuition of how the second layer, here we have three hidden units that are computing some complex function maybe of the input layer, and then the third layer can take the second layer's features and compute even more complex features in layer 3, so that by the time you get to the output layer, layer 4, you can have even more complex features of what you were able to compute in layer 3, and so get very interesting nonlinear hypotheses. By the way, in a network like this, layer 1, this is called an input layer, layer 4 is still our output layer, and this network has two hidden layers. So anything that's not an input layer or an output layer is called a hidden layer. So hopefully from this video you've gotten a sense of how the feed-forward propagation step in a neural network works, where you start from the activations of the input layer and forward propagate that to the first hidden layer, then the second hidden layer, and then finally the output layer. And you also saw how we can vectorize that computation. In the next, I realized that some of the intuitions in this video of how other certain layers are computing complex features of the early layers, I realized some of that intuition may be still slightly abstract and kind of at a high level. And so what I'd like to do in the next two videos is work through a detailed example of how a neural network can be used to compute nonlinear functions of the input, and hopefully that will give you a good sense of the sorts of complex nonlinear hypotheses we can get out of neural networks. In this and the next video, I want to work through a detailed example showing how a neural network can compute a complex nonlinear function of the input, and hopefully this will give you a good sense of why neural networks can be used to learn complex nonlinear hypotheses. Consider the following problem where we have input features x1 and x2 that are binary values, so either 0 or 1, so x1 and x2 can each take on only one of two possible values. In this example, I've drawn only two positive examples and two negative examples, but you can think of this as a simplified version of a more complex learning problem where we may have a bunch of positive examples to the upper right and the lower left, and a bunch of negative examples denoted by the circles. And what we'd like to do is learn a nonlinear decision boundary that maybe separates the positive and the negative examples. So how can a neural network do this? And rather than using the example on the right, I'm going to use this maybe easier to examine example on the left. Concretely, what this is really computing the target label y equals x1 xor x2, or actually this is actually the x1 xnor x2 function, where xnor is the alternative notation for not x1 or x2. So x1 xor x2, that's true only if exactly one of x1 or x2 is equal to 1. It turns out that the specific example I'm going to use works out a little bit better if we use the xnor example instead. These two are the same, of course. It means not x1 xor x2, and so we're going to have positive examples if either both are true or both are false, and we'll have that's y equals 1, and we're going to have y equals 0 if only one of them is true. And we want to figure out if we can get a neural network to fit this sort of training set. In order to build up to a network that fits the xnor example, and we're going to start with a slightly simpler one and show a network that fits the AND function. Concretely, let's say we have input x1 and x2 that are again binary, so it's either 0 or 1, and let's say our target labels y are is equal to x1 and x2. This is a logical AND. So can we get a one-unit network to compute this logical AND function? In order to do so, I'm going to actually draw in the bias unit as well, the +1 unit. Now, let me just assign some values to the weights or the parameters of this network. I'm going to write down the parameters on this diagram, right? -30 here, +20, and +20. And what this means is that I'm assigning a value of -30 to the value associated with x0, that is this +1 going into this unit, and a parameter value of +20 that multiplies into x1, and a value of +20 for the parameter that multiplies into x2. So concretely, this is saying that my hypothesis h of x is equal to g of -30 plus 20x1 plus 20x2. So sometimes it's just convenient to draw these weights, or draw these parameters up here, in the diagram with the neural network. And of course, this -30, this is actually theta 1 of 1, 0. This is theta 1 of 1, 1, and that's theta 1 of 1, 2. But it's just easier to think about it as associating these parameters with the edges of the network. Let's look at what this little single neuron network will compute. Just to remind you, the sigmoid activation function g of z looks like this. It starts from 0, rises smoothly, crosses 0.5, and then it asymptotes at 1. And to give you some landmarks, if the horizontal axis value z is equal to 4.6, then the sigmoid function is equal to 0.99. This is very close to 1. And kind of symmetrically, if it's negative 4.6, then the sigmoid function there is equal to 0.01. This is very close to 0. Let's look at the 4 possible input values for x1 and x2 and look at what our hypothesis will output in that case. If x1 and x2 are both equal to 0, if you look at this, if x1 and x2 are both equal to 0, then the hypothesis will output g of -30. So it's going to be very far to the left of this diagram, so it'll be very close to 0. If x1 equals 0 and x2 equals 1, then this formula here evaluates to g, that is the sigmoid function applied to -10. And again, that's to the far left of this plot, and so that's again very close to 0. This is also g of -10, that is if x1 is equal to 1 and x2 is 0, this is -30 plus 20, which is -10. And finally, if x1 equals 1, x2 equals 1, then you have g of -30 plus 20 plus 20. So that's g of +10, which is therefore very close to 1. And if you look in this column, this is exactly the logical AND function. So this is computing h of x is, approximately x1 and x2. In other words, it outputs 1 if and only if x1 and x2 are both equal to 1. So by writing out our little truth table like this, we managed to figure out what's the logical function that our little neural network computes. This network shown here computes the OR function. Just to show you how I worked that out, if you write out the hypothesis, you find that it's computing g of -10 plus 20x1 plus 20x2, and so if you fill in these values, you find that that's g of -10, which is approximately 0, g of 10, which is approximately 1, and so on. And these are approximately 1, and approximately 1, and these numbers is essentially the logical OR function. So hopefully with this, you now understand how single neurons in a neural network can be used to compute logical functions like AND and OR and so on. In the next video, we'll continue building on these examples and work through a more complex example. We'll get to show you how a neural network now with multiple layers of units can be used to compute more complex functions like the XOR function or the XNOR function. In this video, I'd like to keep working through our example to show how a neural network can compute complex nonlinear hypotheses. In the last video, we saw how a neural network can be used to compute the functions x1 and x2 and the function x1 or x2 when x1 and x2 are binary, that is, when they take on values in 0, 1. We can also have a network to compute negation, that is, to compute the function not x1. Let me just write down the weights associated with this network. We have only one input feature, x1 in this case, and the bias unit plus 1. And if I associate this with the weights plus 10 and minus 20, then my hypothesis is computing this. H of x equals sigmoid of 10 minus 20 times x1. So when x1 is equal to 0, my hypothesis would be computing g of 10 minus 20 times 0, which is just 10. And so that's approximately 1. And when x is equal to 1, this would be g of minus 10, which is therefore approximately equal to 0. And if you look at what these values are, that's essentially the not x1 function. So to include negations, the general idea is to put a large negative weight in front of the variable you want to negate. So if there's minus 20 multiplied by x1, and that's the general idea of how you end up negating x1. And so in an example that I hope you really figure out yourself, if you want to compute a function like this, not x1 and not x2, well, part of that would probably be putting large negative weights in front of x1 and x2, but it should be feasible to get a neural network with just one output unit to compute this as well. Right? And so this logical function not x1 and not x2 is going to be equal to 1 if and only if x1 equals x2 equals 0, right? So this is a logical function that says not x1, that means x1 must be 0, and not x2, that means x2 must be equal to 0 as well. So this logical function is equal to 1 if and only if both x1 and x2 are equal to 0. And hopefully you should be able to figure out how to make a small neural network to compute this logical function as well. Now, taking the three pieces that we have put together, that is the network for computing x1 and x2, and the network for computing not x1 and not x2, and one last network for computing x1 or x2, we should be able to put these three pieces together to compute this x1, x0, x2 function. And just to remind you, if this was x1, x2, this function that we want to compute would have negative examples here and here, and we'd have positive examples there and there. And so clearly this will need a nonlinear decision boundary in order to separate the positive and negative examples. Let's draw the network. I'm going to take my input plus 1, x1, x2, and create my first hidden unit here. I'm going to call this A21 because that's my first hidden unit, and I'm going to copy the weights over from the red network, the x1 and x2 networks, and I have minus 30, 20, 20. Next, let me create a second hidden unit, which I'm going to call A22. That is the second hidden unit of layer 2. And I'm going to copy over the cyan network in the middle. So I have the weights 10, minus 20, minus 20. And so let's fill in some of the truth table values. For the red network, we know that was computing the x1 and x2, and so this will be approximately 0, 0, 0, 1, depending on the values of x1 and x2. And for A22, this the cyan network, well, we know the function not x1 and not x2, that outputs 1, 0, 0, 0 for the four values of x1 and x2. Finally, I'm going to create my output node, my output unit, that is A31. This is what will output h of x. And I'm going to copy over the OR network for that. And I'm going to need a +1 bias unit here, so draw that in. And I'm going to copy over the weights from the green network, so that's minus 10, 20, 20. And we know earlier that this computes the OR function. So let's fill in the truth table entries. For the first entry is 0 or 1, which is only 1. Then next 0 or 0, which is 0, 0 or 0, which is 0, 1 or 0, and that ors to 1. And thus, h of x is equal to 1 when either both x1 and x2 are 0, or when x1 and x2 are both 1. And concretely, h of x outputs 1 exactly at these two locations, and it outputs 0 otherwise. And thus, with this neural network, which has an input layer, one hidden layer, and one output layer, we end up with a nonlinear decision boundary that computes this x-nor function. And the more general intuition is that in the input layer, we just had our raw inputs. Then we had our hidden layer, which computed some slightly more complex functions of the inputs that is shown here. So slightly more complex functions. And then by adding yet another layer, we end up with an even more complex nonlinear function. And this is the sort of intuition about why neural networks can compute pretty complicated functions. That when you have multiple layers, you have a relatively simple function of the input to the second layer, but the third layer can build on that to compute even more complex functions, and then the layer after that can compute even more complex functions. To wrap up this video, I want to show you a fun example of an application of a neural network that captures this intuition of the deeper layers computing more complex features. I want to show you a video that I got from a good friend of mine, Jan Kuhn. Jan is a professor at New York University at NYU, and he was one of the early pioneers of neural network research and is sort of a legend in the field now, and his ideas are used in sort of all sorts of products and applications throughout the world now. So I want to show you a video from some of his early work in which he was using a neural network to recognize handwriting, to do handwritten digit recognition. You might remember early in this class, at the start of this class, I said that one of the early successes of neural networks was trying to use it to read zip codes to help to help us send mail along, so read postal codes. So this is one of the attempts. This is one of the algorithms used to try to address that problem. In the video that I'll show you, this area here is the input area that shows a handwritten character shown to the network. This column here shows a visualization of the features computed by sort of the first hidden layer of the network. And so the first hidden layer, this visualization shows different features, different edges and lines and so on detected. This is a visualization of the next hidden layer. It's kind of harder to see, kind of harder to understand the deeper hidden layers, and that's a visualization of what the next hidden layer is computing. You probably have a hard time seeing what's going on, much beyond the first hidden layer. But then finally, all of these learned features get fed to the output layer, and shown over here is the final answer, is the final predicted value for what handwritten digit the neural network thinks that is being shown. So let's take a look at the video. So I hope you enjoyed the video, and that this hopefully gave you some intuition about the sorts of pretty complicated functions neural networks can learn, in which it takes as input this image, just takes as input the raw pixels, and the first inner layer computes some set of features, the next inner layer computes even more complex features and even more complex features, and these features can then be used by essentially the final layer of logistic regression classifiers to make accurate predictions about what are the numbers that the network sees. In this video, I want to tell you about how to use neural networks to do multi-class classification, where we may have more than one category that we're trying to distinguish amongst. In the last part of the last video, where we had the handwritten digit recognition problem, that was actually a multi-class classification problem because there were 10 possible categories for recognizing the digits from 0 through 9. And so here I want to fill you in on the details of how to do that. The way we do multi-class classification in a neural network is essentially an extension of the one versus all method. So let's say that we have a computer vision example where instead of just trying to recognize cause, as in the original example that I started off with, but let's say that we're trying to recognize 4 categories of objects. So given an image, we want to decide if it's a pedestrian, a car, a motorcycle, or a truck. If that's the case, what we would do is we would build a neural network with 4 output units, so that our neural network now outputs a vector of 4 numbers. So the output now is actually going to be a vector of 4 numbers. And what we're going to try to do is get the first output unit to classify, is the image a pedestrian, yes or no? The second unit to classify, is the image a car, yes or no? This unit to classify, is the image a motorcycle, yes or no? And this to classify, is the image a truck, yes or no? And thus, when the image is of a pedestrian, we would ideally want the network to output 1000. When there's a car, we want it to output 0100. When there's a motorcycle, we get it to, or rather we want it to output 0010, and so on. So this is just like the one versus all method that we talked about when we were describing logistic regression. And here we have essentially 4 logistic regression classifiers, each of which is trying to recognize one of the 4 classes that we want to distinguish amongst. So rearranging the slide a bit, here's our neural network with 4 output units, and those are what we want h of x to be when we have the different images. And the way we're going to represent the training set in these settings is as follows. So when we have a training set with different images of pedestrians, cars, motorcycles, and trucks, what we're going to do in this example is that whereas previously we had written out the labels as y being an integer from 1, 2, 3, or 4, instead of representing y this way, we're going to instead represent y as follows, namely yi will be either 1000 or 0100 or 010 or 001, depending on what the corresponding image xi is. And so one training example will be one pair xi comma yi, where xi is an image with one of the 4 objects, and yi will be one of these vectors. And hopefully we can find a way to get our neural network to output some value so that h of x is approximately y. And both h of x and yi, both of these are going to be, in our example, 4-dimensional vectors when we have 4 classes. So that's how you get a neural network to do multi-class classification. This wraps up our discussion on how to represent neural networks, that is on our hypothesis representation. In the next set of videos, let's start to talk about how to take a training set and how to automatically learn the parameters of the neural network. Neural networks are one of the most powerful learning algorithms that we have today. In this and in the next few videos, I'd like to start talking about a learning algorithm for fitting the parameters of a neural network given a training set. As with the discussion of most of our learning algorithms, we're going to begin by talking about a cost function for fitting the parameters of the network. I'm going to focus on the application of neural networks to classification problems. So suppose we have a network like that shown on the left, and suppose we have a training set like this of xi comma yi pairs of m training examples. I'm going to use uppercase L to denote the total number of layers in this network. So for the network shown on the left, we would have capital L equals 4. And I'm going to use S subscript L to denote the number of units, that is the number of neurons, not counting the bias unit in layer L of the network. So for example, we would have S1, which is the input layer, has 3 units, S2 in my example has 5 units, and the output layer S4, which is also equal to SL because capital L is equal to 4, the output layer in my example on the left has 4 units. We're going to consider 2 types of classification problems. The first is binary classification, where the labels y are either 0 or 1. In this case, we would have 1 output unit. So this neural network on top has 4 output units, but if we had binary classification, we would have only 1 output unit that computes h of x. And the output of the neural network would be h of x is going to be a real number. And in this case, the number of output units SL, where L is again the index of the final layer, because that's the number of layers we have in the network. But so the number of units we have in the output layer is going to be equal to 1. In this case, to simplify notation later, I'm also going to set k equals 1. So you can think of k as also denoting the number of units in the output layer. The second type of classification problem we'll consider will be multi-class classification problem, where we may have k distinct classes. So our early example had this representation for y if we had 4 classes, and in this case we would have capital K output units, and our hypothesis will output vectors that are k-dimensional, and the number of output units will be equal to k. And usually we would have k greater than or equal to 3 in this case, because if we had 2 classes, then we don't need to use the 1 versus all method. We need to use the 1 versus all method only if we have k greater than or equal to 3 classes. So if we had only 2 classes, we would need to use only 1 output unit. Now let's define the cost function for our neural network. The cost function we use for the neural network is going to be a generalization of the one that we use for logistic regression. For logistic regression, we used to minimize the cost function j of theta that was minus 1 over m of this cost function, and then plus this extra regularization term here, where this was a sum from j equals 1 through n, because we did not regularize the bias term theta 0. For a neural network, our cost function is going to be a generalization of this, where instead of having basically just 1 logistic regression output unit, we may instead have k of them. So here's our cost function. Our neural network now outputs vectors in Rk, where k might be equal to 1 if we have a binary classification problem. I'm going to use this notation h of x subscript I to denote the ith output. That is, h of x is a k-dimensional vector, and so this subscript I just selects out the ith element of the vector that is output by my neural network. My cost function j of theta is now going to be the following, is minus 1 over m of a sum of a similar term to what we had for logistic regression, except that we have this sum from k equals 1 through k. This summation is basically a sum over my k output unit. So if I have 4 output units, that is, if the final layer of my neural network has 4 output units, then this is a sum from k equals 1 through 4 of basically the logistic regression algorithm's cost function, but summing that cost function over each of my 4 output units in turn. And so you notice in particular that this applies to yk hk, because we're basically taking the kth output unit and comparing that to the value of yk, which is one of those vectors saying what class it should be. And finally, the second term here is the regularization term, similar to what we had for logistic regression. This summation terms looks really complicated, but all it's doing is just summing over these terms theta, j, I, l for all values of I, j, and l, except that we don't sum over the terms corresponding to these bias values like we had for logistic regression. Concretely, we don't sum over the terms corresponding to where I is equal to 0. So That is because when we're computing the activation of a neuron, we have terms like these, theta I0 plus theta I1 x1 plus and so on, where I guess we could have a 2 there if this is the first hidden layer. And so the values with a 0 there, that corresponds to something that multiplies into an x0 or an a0. And so this is kind of like a bias unit. And by analogy to what we were doing for logistic regression, we won't sum over those terms in our regularization term because we don't want to regularize them and string their values to 0. But this is just one possible convention, and even if you were to sum over, I equals 0 up to SL, it'll work about the same, and it doesn't make a big difference. But maybe this convention of not regularizing the bias term is just slightly more common. So that's the cost function we're going to use to fit our neural network. In the next video, we'll start to talk about an algorithm for trying to optimize the cost function.